So we are going to start this this one-day symposium on Twistronics and Moiré patterns in van der Waals heterostructure. So I request our Dean of International Relations to inaugurate and say a few remarks about our institute's overall these international programs and other things.
So I'm here at the request of Shankar, but really I feel out of place being an academician. I know how deep the subject is, and I am absolutely out of my depths on this topic of Twistronics and Moiré patterns in van der Waals heterostructures. So, I'm here to kind of talk more about how things happen, and SPARC being one of the ways in which we collaborate with international institutes. So I've been told by Professor Shankalpa that we are actually doing this in memory of Professor Assa Auerbach, and he was a professor at Technion, Israel Institute of Technology, and it's quite unfortunate that he passed away and he can't be with us today. This is actually supported. SPARC is supported by the Ministry of Education, and it's a scheme by which we have the opportunity of inviting very eminent physicists or scientists from other parts of the world to come and stay with us and kind of participate in our research and also contribute, as well as enrich us with the cross cultural as well as the cross interdisciplinary research that goes on. So it is really my pleasure to welcome all the delegates. Some of them will be online from Weizmann Institute, and from the TIFR, ISC Bangalore, and from Calcutta. And unfortunately, I know that this is SNBNC CVC, but I don't know the full form of it. I didn't get time to look at it actually.
She's not coming because she has developed some medical issues.
Oh, okay. And but all of you who are here, and the students and the PhD students as well as the other scholars who are here, I welcome you all to this wonderful symposium. I will just speak a little bit about being the Dean of International Programs, just to let you know the background of how things happen here and how things are brought together for collaboration. So we've actually had from Israel, we've had two institutes that have been actively working with us. That is the Weizmann Institute and the Bar Ilan. And through the Dean of Research and Development, there's the Hebrew University that has also been, of Jerusalem, has also been actually working with us. And there have been different kinds of programs. So the way this whole thing works is that, that we at the very bottom level, when we are all, if I were not the dean, I would be in my Kusuma School of Biological Sciences, and I would be also like a participant here. And at the first level, we would like the researchers on both sides to come together and kind of work together on a certain theme or themes, and come up with an idea that they can work together as a problem that they have defined together. And once that is done, then what the international office can do is to kind of help with the students going back and forth, kind of help with the support of their residents in a different country, or invite students from another country, and how we can take care of them here. So that is one of the things we do. The other thing that we do is, we kind of, if this symposium, if Shangalpo needed some more financial assistance, I would have helped out from our office. We could have actually done a little bit more. So that kind of support we also give. Suppose, the faculty is trying to do something which is, bringing together researchers from different institutes, and there is a little bit of shortage of finances, then our office can help kind of strengthen that. Then also what we do is, we have through Rajender's office, we have what is called the seed grants. And this is now kind of, among the IITs, this is something that is done quite regularly. And I think also IIC Bangalore also does that, is that you give a seed grant that is for a project. So you decide on a topic and you said, we'll have so many seed grants on this topic. And so researchers from both sides will kind of pitch and write a proposal together on that topic, and then it's peer reviewed, and the best ones are selected for support for 1 or 2 years. And there's a nominal seed grant money which helps you to write bigger grants and bring in more people together. So that's one of the things. But in general, our office here would be very happy to help out in terms of organizing winter schools, summer schools, have immersion programs of students from international or from other institutes within India to come and stay with us, and likewise for our students to go there and the research scholars to kind of interact. So this is one of the things, and last thing that is there is really the ecosystem for startups. So now I think there are so many new ideas that are coming up that if somebody has a startup idea that is something that could change the way we look at the same kind of application of physics, for example, then there is a whole well-tuned, well-oiled machinery which is there, which kind of takes the idea from the student or the faculty together and takes it all the way to the market, helps them to do that. So that's another thing that we could explore. So with these brief comments about the international program, I'll leave the technical discussions and topics about how this would go forward to Shankalpo and to Rajendra. So I hand over back to Shankalpo.
Thank you, Professor Gomes, for giving us an overview of how the institute is dealing with the various international collaborations and the programs. I will now ask my colleague and in the physics department and also the associate dean of IRD, Professor Rajendra Singh, to say a few words how our research ecosystem works. He will be able to tell a bit more on that.
So thanks Professor Sankalp Ghosh for inviting me here for this very important, like let's say, the SPARC Symposium, which is jointly organized with IIT Delhi and Institute from Israel. So this topic, like let's say, Twistronics and Moiré patterns in van der Waals heterostructures. So I also, like let's say, I don't work in Twistronics, but at least the van der Waals heterostructure. So it's very, very important from fundamental physics point of view, as well as, like let's say, the applications. So what I will do is two things I will talk about: what we are doing at the institute level on 2D materials, and about the National Quantum Mission. What is the vision of National Quantum Mission on 2D materials? So at the institute level, we have more than, I think, 10 or 15 faculty members who are working in various aspects of 2D materials. And at IIT Delhi, we have various facilities like pulse laser deposition, chemical vapor deposition, and also we have the only molecular beam epitaxy in India which is dedicated for the growth of 2D materials and van der Waals heterostructure. So it's a very, very unique facility under the CRF, Central Research Facility, which is located in the Sonipat campus. Apart from that one, there are, like let us say, computational materials aspect, also theoretical aspects. Various faculty are working on 2D materials, or we are now saying it 2D quantum materials. And my group is working on van der Waals like heterostructures more from photodetector point of view, like 2D, 3D heterojunctions and its applications in photodetectors, UV as well as visible photodetectors. Apart from that one, in IIT Delhi, we have a central research facility, and the main, like let us say, we have it in the Hodgkins campus also. The main facility is located in the Sonipat campus. So if I will request actually our visitors from outside, like let us say Mandir, Manish and Avi, if you get a chance, do visit. We will organize this visit for you. But you have to have half a day at least for that one. So we have number of material characterization facilities there. All the sophisticated, like including XPS, HRTM, and AFM, cathodoluminescence. Recently, we have installed a facility there, and KPFM, ellipsometry, PL. Many things are there actually, which can be used for the characterization of definitely the 2D materials also. And apart from that one, at the national level, like because since I have to be a little bit brief, so at the national level, most of you might be knowing that there is a National Quantum Mission which is now, like let us say, working, and there are various projects which have been sanctioned, and it is primarily working under 4 verticals. One is this quantum communication, quantum computing, sensing and metrology, and there is one vertical on quantum materials and devices. And this whole mission is going to work in hub and spoke model. Okay. And in first round of, like let us say, the call for proposals, So IIT Delhi has been chosen as the hub, which we call the thematic hub on quantum materials and devices. And under this hub, 3 technology groups, what we call the TGs, have been sanctioned. And among these three TGs, one of the TGs is on 2D materials. Okay, it's almost like, let us say, more than $10 million kind of like, let us say, in funding for this TG, which is like, let us say, various groups are working. The main lead PI is in IIT Bombay, and there are other, like, let us say, the member PIs which are distributed across various institutes. The main idea of this TG is for the development of technology based on 2D materials for single photon emitters and single photon detectors. So it is more technology driven, but also there will be a component of growth, component of characterization, and then, like, let us say, leading to the technology, which is like, let us say, these single photon emitters and detectors, specifically in the visible range, which will be used for, like, let us say, quantum communication application or quantum sensing and metrology. So, like, let us say, in the coming time, so you will be getting to know more about these, like, let us say, because we also will be organizing workshops, dedicated workshop. But this is already a very good, like, let us say, kickstart in that direction. And a lot of prominent speakers you have invited here, Professor Sankalp Ghosh, and Professor Suresh Marathe is also there, and Professor Rohit Nerula. So definitely it's going to be very, very exciting session today, and we are looking forward to have the speakers both from within India and from Israel, and like, wish you all the best for all the students also. Okay, thank you, Sankalp.
Okay. So thanks, Professor Rajendra Singh, for giving this opening remarks, and just. We have some small gifts for both of you for
thank you.
coming and spending some time with us. And
Photograph.
yes, a photograph.
You want to get? Thank you. Okay.
Okay, so we'll start very soon with Professor Mandar Deshmukh's talk, but just before that I wanted to make few comments. So as you can see that this name of the theme of the symposium is Twistronics and Moiré patterns in van der Waals heterostructure. I believe most of the people who gathered here, they know about the van der Waals heterostructures, stacked two-dimensional materials, and after this very important discovery in the twisted graphene layers was made, this particular field. So there are some interesting theoretical prediction, and with a gap of 6 years, there is important experimental discovery which sort of confirmed that theoretical prediction. That the field got a huge boost, and there is a huge amount of activity both in the theory experiment and on the technological front. So one of the idea of this particular symposium is to bring top-notch researchers from various parts of India to come here and share with us their knowledge. Of course, it's a one-day symposium, so we don't have much logistics for this. So most of the student participants, they are from the local regions of the Delhi, but one of the purpose was to so to encourage this activity of the students in this particular direction through these inspiring talks which are going to take place throughout the day. So that is one thing which I just wanted to point out. Other important thing what I just wanted to point out is Professor Assa Auerbach and myself, who were started originally planning for this workshop, and then some very terrible thing happened. And I would like to spend a few minutes in talking about Professor Assa Auerbach, because he made a tremendous contribution apart from his scientific contribution to the Indian physics community. So he nurtured 4 postdocs, and I am the second one. So I have some type of current knowledge about the rest of the, and out of the 6 postdocs, 4 are already placed in various, they are placed in various research institutes of India, including myself. So one, of course, was our friend Venkatesh Pai, who also prematurely died at a few years back, who was a faculty in the Harishchandra Research Institute. One is Abhishek Samanto, who is currently in the IIT Gandhinagar, and other is Ravi Chandra, who is in NICER Bhubaneswar, and even at this point of time, he's one more Indian postdocs, and so in that way, and he has traveled to India many times. Of course, he is very well known for his phenomenal book on the interacting electrons and quantum magnetism, which is considered globally as an standard text in that particular subject. And of course, he has his famous research contributions, and he, of course, mentored very famous physicists who are placed in University of California, Berkeley, Weizmann Institute, Technion, and various other places. But what I wanted to point out, that is the reason why we are here to pay respect to Assa's memory, that he made a tremendous impact to the Indian physics community by nurturing a series of postdocs over the years and visiting India many times, giving talks, and this time he was supposed to give a series of lectures under the SPARC scheme, which are all cancelled because of this particular, and so we'll be missing him, those who particularly know him very closely, but his impact will be remembered for a generation of physicists through this work. So with this very brief introduction, we'll now get into the actual this thing, so of the program of this conference and symposium, and I invite Professor Mandar Deshmukh from TIFR so you can just take now. Yes. So I request my colleague Professor Rahul Marathe to chair this particular session. So it will be first Mandar and then Dipanshu.
Okay.
You can just start introducing him.
Priya,
She's not coming.
Not in Ajaz. So
She's not coming. She has an health issue, so she has to cancel this thing.
So next is
Dipanshu. But you can just introduce her.
Sure.
You can just.
So it's a great pleasure to have Professor Mandar Deshmukh to give the first talk of this symposium. And the title of his talk is Moiré Materials for Probing Berry Curvature Physics. So I think all of you know that Professor Deshmukh is a professor at TIFR Mumbai, and he has been working on this amazing physical systems for almost for 15 years or so. And Mandar, please.
Sure. Thank you very much for the kind invitation and having been part of this interesting meeting. So I have been to this room before, and I have some traumatic memories of DST reviewers asking tough questions, but I am in a different situation, hopefully more pleasant memories. So I'm happy to be here. I gratefully acknowledge the support that we get from the Department of Atomic Energy and Department of Science and Technology to make this work possible. Okay, so let me get started. So the first thing is, I want to acknowledge the people who do the work because I'm really fortunate to have some outstanding students. Sorry, there's no pointer here, but outstanding students who led this work, which really makes this exciting for me on a day-to-day basis. Subhajit, Pratap, Surat, and Ayushi, they're really smart students, and I'm fortunate to have students smarter than me. Umesh, my collaborator, Umesh Wagmare from JNC, Amit Agarwal from IIT Kanpur, and we get some nice materials from HBN from NIMS. Okay, so this is my outline. So it's going to be fairly pedagogical with the students and young researchers in mind. I'm going to talk about berry curvature physics in a very general terms, what is interesting about it, and why it can lead to interesting physics, and how it connects to the Moiré materials is sort of the next part of my talk. Berry physics is general, it doesn't care about Moiré, but having Moiré makes life more even exciting. Then I'm actually going to dive into some two experiments, which one of it is already published, and the last one is something that we're working on, very excited about it, which is modulation of berry curvature in real time. So let me get started. Okay, so most of the physics that we know is easy to understand if you think about the honeycomb lattice of graphene, which is very unique in the sense that it has honeycomb symmetry. It is not a Bravais lattice. It is a triangular lattice with a 2-atom basis. What this means is that to construct this lattice, you need to start with a scaffolding of triangular lattice and then put 2 atoms or 2 sites per Bravais lattice, and then you can build this honeycomb lattice. Fundamental here is the fact that there are 2 sites in a honeycomb lattice, which are A and B, which look like they're basically the same thing. But it turns out there is a fundamental symmetry which distinguishes site A and site B. Site A and site B are not the same, even though they may at a first glance look the same. And the way to think about it is site A, if you ask the question, is there a site on the left of site A, and the answer is no. Whereas on the if you ask the same question of site B, is there a site on the right side of site B, and the answer is no. So the fact that there is a left and right inbuilt into the lattice is key to the physics. It is sort of related to this deeper idea of chirality that is there in the system. Okay, so in case of graphene, it's site A and site B are occupied by the same chemical species, but site A and site B are kind of flipped around. Okay, so these two values are inequivalent, and they kind of are very key to understanding the physics, and it will become clear in the Moiré. So simple symmetry properties distinguish materials. For example, graphene, which is occupied, again honeycomb lattice, but occupied by carbon species, is a semi-metal, whereas its cousin, which is hexagonal boron nitride, pairwise it's isoelectronic. 2 carbon atoms has the same electrons as 1 boron and 1 nitrogen. It's on either boron and nitrogen are on either side of carbon. But one is a semi-metal, other is an insulator with a band gap of about 7 electron volts. So this happens because the inversion symmetry of the lattice is broken. Inversion means if around the symmetry point, if you make the transformation R goes to minus R, and if the lattice doesn't come back to the original lattice, then that symmetry is broken. So for the honeycomb lattice, that symmetry is broken. For the case of graphene, you have a gapless system, gapless bands. For boron nitride or molybdenum disulfide, it's basically a kind of a version of a massive Dirac fermions with a gap. Okay, so inversion symmetry is an important symmetry, and it's kind of key. One system that I love is bilayer graphene, which is 2 layers of graphene in AB stacking. So bilayer graphene is a semi-metal in its sort of pristine state because it has this inversion symmetry in the system. However, in this very nice paper, they showed for the first time that if you break the inversion symmetry by applying a perpendicular electric field, so if you look at the cross section of this lattice, it looks like upper layer A1, B1, A2, B2. In the absence of electric field, inversion symmetry is protected. Okay, so you can do the inversion center and get the same lattice back. However, if you apply an electric field, this system breaks inversion symmetry and you open up a band gap. So bilayer graphene is a kind of a unique metal. It goes from metal or semi-metal to a semiconductor with a band gap of about 300 MeV with electric field. And as I will show later, this opening up of the band gap accompanies interesting physics, topological physics, which is the emergence of Berry curvature. Okay, so the fact that you can apply these knobs in situ in the same device is really powerful, and you can do a lot of interesting physics to understand different aspects. So Berry curvature related ideas come from the electronic bands, the block bands that we know, that we are all familiar with and we study in solid state physics. But in some systems, these electron packets or wave packets, if you like, have this unique property that there is a kind of a self-rotation of these packets about their axis. So as the electron is kind of moving around in these bands, there is a self-rotation. And that self-rotation is key to the Berry physics. Okay, and I will qualify which materials host these kind of self-rotation of wave packets. But this self-rotation has a sense of kind of a Magnus deflection on one side. As the electrons are kind of moving around, they will experience a deflection much like the Magnus force, that you experience. And we know how electrons move around semi-classically in bands. We can write it down in the presence of electric field. But in the presence of this self-rotation in these materials, there's an important term which comes in, which is right here. This term is not there in materials which don't have this self-rotation. And that symbol omega is the Berry curvature. So once you have this self-rotation of wave packets, there is this Berry curvature that is sort of an important aspect. And there are also higher order terms which immediately we're not going to worry about. So Berry curvature, when is it there? Berry curvature is non-zero when you break either one of the symmetries, time reversal or inversion symmetry, okay? And in the case of honeycomb system, which we're going to worry about for this Moiré system, the Berry curvature is valley contrasting. The Berry curvature has opposite signs in the two valleys that I will show in a couple of minutes. So one consequence of it, which is related to this idea of topology, is this the summation of the Berry curvature over the whole Brillouin zone gives rise to an invariant, which is the Chern number. So if I look at the Brillouin zone, I can kind of integrate out this Berry curvature, and because I have this periodic boundary condition and it's a two-dimensional system, for example, I will get a kind of a torus over which I kind of integrate out this Berry curvature for the system. I will get the Chern number. Now the Chern number is non-zero only when time reversal symmetry is broken, but in Moiré systems that I will show you, you can have Chern number for individual valleys which are equal and opposite, so that the total Chern number is zero when time reversal symmetry is not broken. So later part of my talk will emphasize this aspect that you can have valley Chern numbers which are kind of topological properties of the system, and then you can actually sense it using transport properties. So there is a lot of buzz in the field about this connection of Berry curvature to ideas of what are called quantum geometry. So quantum geometry basically is asking some fundamental questions that are related to this idea that you have a bunch of different states parameterized by some parameter k. Now you can ask some questions are how different are these states by kind of two different metrics. These are different states of the system. You can ask how much has the phase evolved between state 1 and 2, for example. Or you can ask what is the distance, okay, when the state 1 and state 2 are identical, the projection is 1, then this distance becomes 0. So there are these two aspects to how much has the state evolved, and this is connected to this idea of what is the distance of the state evolution, and this is connected by this quantum metric, quantum geometric metric, quantum geometric tensor, and the real part of this tensor is the quantum metric, and there has not been a lot of work on probing these particularly, but there's now increasing interest in trying to see the consequence of this in Moiré systems and other systems. And the imaginary part of this is well known, which I described to you earlier. It's the Berry curvature. So it's related to this idea of quantum geometry, and quantum metric may have some very important role to play in the superconductivity, which people are just beginning to scratch this fundamental new idea. Okay, so idea of topology may be central to many of the concepts that we are trying to unravel in condensed matter physics and solid state physics. So for particularly the young people, this is a very exciting time, because some of the fundamental ideas that we kind of swept under the carpet for many decades may actually finally be the carpet may actually be removed, and the dirty things that we thought could actually be the really precious things. Okay, so let me get started to the connection with the sort of focus of today's symposium, which is Moiré materials and 2D heterostructures. So, there has been a kind of a rapid growth in this field, starting from early 2005, where people isolated 2D materials, to sort of very complex heterostructures created. Heterostructures are peeling off and layering it. It's really an example of immense creativity of not necessarily the PIs, but the students in assembling these kind of, or the younger researchers in making these kind of complex heterostructures, which are peeling one layer and assembling an 11-layer stack. So this is not really easy, but it has been done. And every time you see papers coming out, you really are amazed at the creativity of people in handling something which maybe 20 years ago people didn't think actually was possible to isolate a single layer. So it's really remarkable. So people assemble materials which have very different functionalities without, you can put a superconductor next to it, you put a magnet. This is not possible by any other method. It's not possible by MB, it's not possible by any other physical method. So it's really unique to this system. So now one new knob that came in, and Sankalp already kind of alluded to it, is this idea of twisting. Again, when you twist two layers, you are actually creating structures which are metastable, which don't exist in nature, because we look at long time scales of materials which relax to find a minimum ground state. When you twist structures and you look at layers which are twisted with respect to each other, importantly, you get a new length scale in the problem. So this is exactly the same idea if you have, on a hot summer day, if you have looked out of the window and there are two jalis in your room, which is looking out, you can see there's a beating pattern between the two jalis. It's exactly the square lattice of the jali. This is the kind of moiré of honeycomb lattice, that is the moiré of square lattice, which is also an increasingly interesting area that people are working about. Moiré of square lattice rather than honeycomb lattice. So it introduces a new length scale in the problem, and it leads to interesting physics. So when you start with a simple layer of, let's say, graphene, and you twist it in real space, you also actually cause a twist in the momentum space or the K space. And the way to think about this is that you have, if you look at one of these points, you have two Dirac cones, if you like, at the low energy, and they overlap with each other at some higher energies, which is a function of the twist angle. Now, if the two layers were not electronically coupled, so that the electron were not hopping back and forth, this is all you need to worry about. There is no interesting things. However, the moment you allow electrons to tunnel from one layer to another, these points where they're degenerate, they actually hybridize, much like in the sense of chemistry. You get a hybridization of bands, you will get an opening up of the gaps, and there will be these bands, new bands, emergent bands, which are going to be flatter. And so at some point, some angle where the hopping between the layers is comparable to the hopping between these moiré lattices, you get this extremely flat bands, and which is sort of interest to a lot of people for correlations, but it's also interesting for topological properties. So it all started with twisted bilayer graphene. Alan MacDonald and Rafi Britsitzer predicted this, and many others. There were actually a slew of papers. They were not the first ones to do it, but they're of course known, and they have consistent work. And experimentally, people saw superconductivity very quickly. Then a magnetism, a unique kind of magnetism, very different from the magnetism of iron, cobalt, nickel. These are orbital magnets. So one thing I want to point out is that you see superconductivity here in all carbon systems, or magnetism in all carbon systems. This is completely antithetical to our conventional view of solid state physics, that you need some other ingredients to see magnetism or superconductivity. Here it's a different kind of, I would say fundamentally different kind of superconductivity and magnetism because of this Moiré physics. So there has been a lot of work, but what I like about this system is that it has very tunable, pliable. You have a kind of a clay that you can do a lot of fun things with it. And one is that you can break symmetries of the system. Like you have graphene-like system, you break inversion symmetry, you will get gaps in the spectrum, but your Chern number is still 0. Then you make a Moiré, you twist it, and you create another periodicity, what you do is you end up isolating these Moiré valleys, and you can get valley churn numbers which are not possible in a normal system. But the valley churn numbers are equal and opposite. And you, on top of it, if you add time reversal symmetry, either by magnetic field or some internal interaction-induced time reversal symmetry breaking, you can actually get a non-zero churn number in the system. One additional knob is if you break some spatial symmetry, that the Berry curvature distribution is no longer isotropic in the system, then you can also get something fun, which we like personally, is this Berry curvature dipole, which is a kind of a dipole of Berry curvature which lives in the lattice, because this threefold rotational symmetry is broken, for example, by strain. Okay, so there are lots of interesting knobs which make a playground very fun for interesting physics. There are experimental tools like you can dope it electrically, you can apply perpendicular electric field from the example of bilayer graphene, you can change the twist angle, you can change strain. That makes it really a very nice system to play around with lots of different things. So there has been a lot of work. Every day you log into arXiv and try to see. The rainfall of papers is immense, and you just have to keep walking in and learning from this immense rainfall. So this is a kind of a short timeline from 2007 and some really breathtaking experiments in the last year on fractional quantum anomalous Hall, which is essentially fractional quantum Hall like physics, but at zero magnetic field. So it doesn't really stop, which is a good thing for us. It keeps us in business and thinking about the physics. So how am I doing on time?
You have about 13 minutes.
Okay, all right, yeah, I think I should be okay. All right, so now you might say, fine, you're talking about, for last 15 minutes about Moiré. Is it just some rehash of physics that we already knew for many years? And, this is another revision of what we already knew, okay? And what I want to argue is that that's not really the case, that there is an opportunity to explore physics which were not possible earlier. And for example, if you look at what 2D atomic lattices or real atomic lattices already gave us, you have an atomic spacing, you have some band gap, you have Berry curvature in regular 3D materials, you have Berry curvature dipole as well. But some aspects like tunability is a little bit trickier in 3D materials. Now, what does Moiré give us is that because of this twisting length scale, it gives you a whole different length scale, energy scales. On top of it, Berry curvature physics is sort of amplified because the Berry curvature goes as the inverse of the length scale square, roughly. So now, if you have Berry curvature in your system, they're going to be much larger, and that's kind of nice for seeing some physics. Then if you want to see physics of Berry curvature dipole, it scales roughly as the periodicity in their system. So now Berry curvature dipole related physics can also be seen much more easily in your experiments. So it's not really kind of an old wine in a new bottle again, but something new that this Moiré system is offering in the exploration, and that's what I like personally. Okay, so this is sort of my broad introduction. Let me now, in the next 10, 12 odd minutes, I'm going to show you some examples of experiments that we have been doing. This will be a little bit faster than the pedagogical introduction, but hopefully what I told you already will kind of fortify you for the next 12 minutes or so, okay? All right, so the material that we like is bilayer graphene. Which has this unique property that it's a material whose band gap is tunable by applying an electric field perpendicular to it. Okay, that's really nice. And the reason is that breaking of inversion symmetry. So what we work with, we work with twisted double bilayer graphene, which is essentially take bilayer graphene, cut it into two pieces, twist it, and put it back. So it effectively is 4 layers of graphene. Okay. And the reason we do it is that we want to get the bands which are flat, but we want to have control of the band gap and bandwidth with electric field, which doesn't exist in twisted bilayer graphene. Okay, So we want a system where we can tune parameters and measure the response of those parameters. And here also you get these new bands similar to what I explained to you earlier. But now this gap is tunable with electric field, and this bandwidth, which is the width of the bands, is tunable with electric field. That's not the case for twisted bilayer graphene. So these are sort of how devices are constructed, and you'll hear some talks later which will also talk about this sort of devices, which has these two gates, top gate, bottom gate. You have the material and they're sandwiched between boron nitride layers. And then you can do transport by applying voltage, measuring current. So if you measure the properties of twisted double bilayer graphene, they look something like this. Blue region, this is color indicating the value of the resistance measured. This blue is low resistance, it's actually metallic or semi-metal, depending on how you want to be more precise in your statement. And this is low resistance, and when you see these large regions, these are the large resistance regions, red colored are the regions where you start opening up gaps in your electronic spectrum. These are measurements done around 1.5 Kelvin. These gaps and these band gaps and the bandwidths, they're roughly about order of a few milli-electron volts. Okay, so what we are seeing might seem like, what am I looking at and what does it physically mean? So let me kind of handhold. So if I look at this region, which when I have applied no electric field, the system behaves like a metal, and this is sort of tight binding calculations, but the one that I like the most is this cartoon depiction of what's happening to the band structure. So you have two overlapping flat bands, a red dashed line is the Fermi energy, and then you have these dispersing remote bands. As I apply an electric field, what it does is it actually separates out the two flat bands and creates two flat bands with band gaps in between, and some gaps with remote bands, which are called the Moiré gaps. Then you can apply more electric field, and eventually you will close out these gaps, and the bands will touch the remote bands and exchange Berry curvature and begin to close. And then you go further, eventually you will destroy the flat bands completely, and they will merge with remote bands. So you are having, in the same device, you can tune the band structure continuously. Okay, so that's sort of the picture that you should keep in mind. You have a system who has electronic bands which I can tune with in the same device. And these bands have Berry curvature, hotspots, which is distribution of,
What is the width of your flat band? At
few MeV. It's tunable with electric field. We can talk more later. Sorry, I'm running short of time, but we'll talk more. Or in the questions, okay? So there is Berry curvature, which you can sample by different experiments. And you can tune this Berry curvature. So the perpendicular electric field also tunes the Berry curvature. Okay. So one of the ways to tune probe Berry curvature is what are called experiments called non-local experiments. This is something that we did because of the Berry curvature. This term for electrons belonging to one valley and the other valley are opposite in sign. So if you send a charge current, because the valley contrasting Berry curvature, electrons of one valley get deflected here, and electrons of another valley get deflected in the opposite direction, and that creates a valley current. And that there can be an inverse effect, which is called the inverse valley Hall effect, and then you can sense the magnitude of the Berry curvature down the line. Okay, I can talk more about this if you have questions, but this is one experiment to probe the Berry curvature. I'm going to skip this right now just to save some time to go to the sort of more juicier bits of the talk. So people saw this Berry curvature, and they saw this valley churn numbers in the system, that you have two valleys which have opposite churn, equal and opposite churn number, because the total churn number has to be 0 as the time reversal symmetry is protected. But what they saw, these are different works, but they show similar things, that with the electric field you can cause a valley churn transition, the valley churn number of the changes, and that was interesting. And we wanted to kind of see whether there are ways to probe this valley churn transitions in the absence of magnetic field. So in the presence of magnetic field, people have been seeing churn transition, which are non-zero churn numbers, using Landau fan diagrams like these, and by using Streda formula to extract out the churn numbers. But valley churn transitions cannot be probed by this method. So we wanted to use detect these kind of valley churn transitions, and we showed for the first time experimentally that this you can actually probe it using Berry curvature dipole. So what is Berry curvature dipole? So if you have a completely C3 symmetric, so threefold rotationally symmetric. So if I rotate this kind of hexagon threefold, I get the same thing back over and over again. However, if there is, sorry. If you look at the Berry curvature, in all the three directions, principal directions, it's the same. However, if you have some strain in the system, I mean, here I'm exaggerating it, the Berry curvature is no longer the same along the principal directions. And that's sort of the key. That basically tells me that I can ask a question about this distribution of Berry curvature and ask a first moment of the Berry curvature. Like you have a moment of inertia, similarly you can think of a moment of Berry curvature, and that is the Berry curvature dipole. So when there is strain, you get it to be non-zero. So the expression is a little bit complicated looking, but it basically measures anisotropy in the space. This is the Berry curvature, and this is the velocity, if you like. So in the presence of strain, what you get is a non-zero Berry curvature. So Berry curvature itself doesn't change much with strain. So these are strain and unstrained sort of calculations. But in the absence of strain, the Berry curvature dipole is uniformly zero, which is this dashed line. But the moment you strain it even a little bit, you get these lumpiness, which is the Berry curvature dipole peaks out of one sign and other sign as a function of energy. And that's sort of what we exploit using this work of Inti Sodeman and Liang Fu. Okay, so what Inti Sodeman and Liang Fu said was, if in a time reversal symmetry protected system, if you have Berry curvature dipole, that is non-uniform distribution of Berry curvature in the system, then you can kind of get a nonlinear response from the system, which is the dipole interacts with the electric field sort of through a Valley Hall kind of effect, then again interacts with the electric field to generate a second order response. Or it's like a second order correction to the transport, if you like, which is a Hall response. So a Hall response we are used to thinking of, you apply a magnetic field and you see Hall response. This Hall response arises from the Berry curvature dipole and does not need the magnetic field to be there. So you apply a current, and in the perpendicular direction you get the 2 omega component. And that's sort of our experimental geometry which we use to do these experiments. And we can measure nonlinear Hall response and linear Hall response, all of these quantities, while changing the density and the electric field. And much like I told you, as I apply an electric field, which is this y-axis, I can measure the longitudinal resistance and also this Berry curvature induced nonlinear Hall response in my experimental parameter space. So indeed there is Berry curvature dipole, and so to extract out the effect of Berry curvature dipole, this is a experimentally and theoretically an ongoing area of research. There are many sources of nonlinear Hall response, which some of them arise away from Berry curvature dipole, but something like skew scattering. So to extract out the Berry curvature dipole, if you measure a kind of scaling relation in your experiment like this, then this quantity B gives you a measure of the Berry curvature dipole, and that's sort of the approach that we use in our experiment. So we measure the left-hand side, which is this, all of these quantities are measurable independently. So this is the numerator here, and the red is the denominator. We measure it, and then we establish the scaling relation. And we see that when you establish the scaling relation at a particular point in electric field, you see a sudden change in the intercept, and that sudden change in the intercept is a reflection of the change in the Berry curvature dipole of the system. So physically what's happening is that around this electric field, displacement field, as you tune the electric field, you have some Berry curvature distribution, and on the lower side, the Berry curvature distribution is very different. And in between, you are basically seeing a band touching. This band touches and exchanges Berry curvature, and as a result, the valley churn number goes from 1 to -2. So this band touching changes the Berry curvature distribution and the valley churn number, but that's also reflected in the Berry curvature dipole. That's sort of the take-home message.
So these coefficients are unquantified.
Sorry?
These coefficients are unquantified.
Yeah, there's no quantity. So Berry curvature dipole itself changes sign in our experiments. We don't have a watertight way to say that every valley churn transition the Berry curvature dipole should change sign, but we have observed that it does indeed change sign. So that's sort of the main message, that you can actually see these kind of valley churn transitions independently. Some other people using different techniques also see these kind of valley churn transitions in their experiments. So in the next minute or two, do you have a minute?
Yeah. We can have some time because we started a bit early. So
No, that's okay. I want to finish. If there are questions, I'm happy to answer those questions. So now, in the next couple of minutes, I'm going to talk about some experiments that we have been doing for the last year or so, which are still going on. Because there are some aspects of the underlying physics that we are trying to fill out some of the kind of holes in our theoretical understanding, which is to modulate the Berry curvature in time. Okay. Now, how does one do it? And the way I like to say it's essentially like a Moiré system, but on a trampoline. So I'm hoping at least some of you have been on a trampoline before, or know of kids jumping on a trampoline. So it's the same thing. You make a Moiré device, but you put it on a trampoline and make the trampoline go up and down. So as it goes up and down, there will be strain, and the lattice will kind of breathe, and that will modulate the Berry curvature structure. So this is the device structure. We make the Moiré, and we can train the device as a function of time and simultaneously do electrical measurements. So this is sort of the device geometry. It's a square trampoline of silicon nitride, which is only about 100 nanometers thick. So that as the silicon nitride moves up and down, or we stretch it, we will strain the device on top to some extent. And this is the standard Moiré device. So as we can apply piezo voltages, which essentially stretches it, and we can see that the resistance changes. Controllably straining 2D materials and Moiré is a challenging field, and only now one or two groups have some handle on this. And this is a kind of evidence that you can tune the strain state of the system controllably. So when you strain it, what you should think of is that you have some valley and some structure in your Berry curvature in the K space. As you strain it, you will kind of wobble it a little bit. If you're familiar with the idea of Berry curvature dipole, the toy model that describes it is kind of a tilted Dirac cone. So you should think of the Dirac cone, which is tilted, kind of wobbling a little bit as you modulate it in time. And that's the spirit in which we do these experiments. So as you strain it, you will modulate the Berry curvature, and you can look at the response of this modulation in your experiments. And this is done using a lock-in detection, where you can detect signals of mixing, which is, if you're an electrical engineer, some and different frequencies, you can listen to that, which is measuring the consequence of the strain. So it's not the frequency at which the strain is being modulated, but it interferes with the electric field that you have applied, and so it gives rise to some frequency, which is omega m plus omega c. So you look at the signal, and precisely where the Berry curvature is large, where you expect Berry curvature dipole to be there, you get this mixed signal.
If you could finish in 2 minutes.
Yeah, I'm one.
Okay.
I'll be done in one. So we can confirm that these experiments are kind of agree with the scaling expected. And not just that, just in the Berry curvature, but the Berry curvature dipole also gives a nonlinear Hall response, which we can also measure in a much similar way, where now the signals will be at omega m, which is sort of the elastic strain, and twice the electric field frequency, modulation frequency, and that is consistent. There are some open questions that we don't really understand, and which is exact magnitudes. There could be some way to sense higher order transport processes, which we hope will shed some newer ideas about Berry curvature structure in these Moiré systems. Okay, so that's really what I promised. I'm going to say more on this. Let me ask, so this kind of question that I like to ask, okay, so what? I mean, what next? Okay, so there are lots of interesting possibilities which are sort of exciting to us, and asking questions about chirality. You can have Moiré structures which have inherent chirality inbuilt into it. So you can twist a structure by 2 layers by theta angle or 180 degrees minus theta. Okay, they turn out that they can have similar band structure, but the Valley Churn numbers are different. So there is the sense of chirality, which is for me personally very exciting, and some things we have already sort of done some experiments on. The fact that you have chiral structures and that chirality can be sensed by electrical measurements is personally very interesting for me. So thank you very much for your kind attention.
We have about 5 minutes for question and answers. Please.
I was wondering, what was the strain percentage roughly in those BNC structures?
So the strain is very small. Typically, the devices wake up in the way they are fabricated. They wake up in about 0.1% or strain. The modulation is even smaller. Okay, it's some strain state of the system, but you wobble it. So exactly measuring what is in the device is a little bit tricky, but it's a fraction of it. I would say 1/10 of that is the modulation, which we are temporarily modulating.
And how did you measure the uniformity of the strain?
That's a good question. So the way the community does the strain measurements is you do transport measurements. Typically the electrical probes are about a micron apart. So you measure electrical transport and you see the Moiré gaps. And the Moiré gaps can be backtracked to what the twist angle is. So inherent issue with the Moiré is that there is a strain gradient. That it's not like through a 10 micron device you don't get the same angle, but some variation on a length scale of about 1.5 microns or so. So the way the strain is measured is through these Moiré gaps by measuring transport.
How do you apply the same amount of strain on the top and the bottom layer?
A very good question. So it's impossible to know if there is a differential strain. Okay, I would say that if there is a way to measure, let's say if I have a bilayer and another bilayer and I strain upper one differentially, if I know controllably, that is an interesting knob because we don't know. That's the short answer. Okay, we assume right now that you've clamped it and the whole trampoline is kind of moving up and down, then the same strain is transferred to the whole system. It may turn out, that's I would say a reasonable, simplest assumption. It may turn out that needs to be amended, but right now we have no evidence. Yeah.
Sir, you have twisted 2 layers while theta is equal to 1.18 degree, right? Mm-hmm. So how did we decide if we are actually twisting by 1.18 degree, or is there anything which lead us to this angle?
Okay, excellent question. Some things that I sort of glossed over. So let me explain this a little bit better. What happens is that the way these devices are made is you take a layer of bilayer graphene, you cut it into 2 pieces because you need to know the angle between the 2 layers precisely You cannot take any two random exfoliated flakes because determining their relative angular orientation to that accuracy is impossible. So you take the same single crystal of bilayer graphene, you cut it, okay? I hope it's okay to tear this. Let's say I've made 2 pieces. Then I pick one up and I rotate the other, it's on a rotatable stage, and I twist by the angle I want. It's a mechanical rotator or a piezo rotator, and then I bring it back together. Okay, then I know the angle. Now, often, as I told you, these twisted systems are metastable states. So I might dial an angle of 1.5 degrees, but I often don't get 1.5 degrees, but I'll get some 1.4, even sometimes 2, because the relaxation when you drop the second layer on top is not predictable. So we measure it. So we don't characterize the twist angle of the device by just saying what I dialed, but by transport measurements, by the procedure that I just explained, by electrical transport, I can infer the angle. And so now you're coming back to your question about why 1.18. Okay, so we didn't really. So you can do simple tight binding calculations, which are a guidance, which say that the physics around 1.8, 1.2 degrees is interesting. So we aim for that angle. We don't aim for 1.18 because we're never going to get 1.18. But if you make many devices, then some will hit the angle that is of interest to you. That angular sort of aiming is not so important for the physics that I talked about, but for systems like twisted bilayer graphene, where the superconductivity is seen, the angular relative alignment or twist is very crucial, and people see a very narrow width. People don't fully understand it, but that's how it is. For the physics that I talked about, 1.18 is not crucial, but that is what I got. But I can understand the physics that comes out of it. Did that answer your question?
Yes, sir. Sir, is there
excuse me, if you ask a question, please switch on the mic in front of, that will be then, because we are recording everything, so it will come.
Hello. Sir, so my next question is there any angle dependent study on the bandwidth and the band gap?
Yeah, it cannot be done as continuously as one might expect, because you have to do discrete devices. So far, maybe at the end of today's symposium, Shahal Ilani will talk about an experiment which you can continuously rotate the graphene devices. That is one way to probe the bandwidth. There are lots of subtle issues there, interactions, how important they are, how they renormalize the bandwidth. So by discrete devices, people have done and they have tracked it, but people don't fully understand all of it. This connection between theory, some aspects, tight binding, and whether physics of relaxation, all of this is still a bit of a complicated mess. Maybe Manish will probably, are you going to talk about relaxation a bit? Yeah, so he's an expert, he might mention. And so experimentally, the tight binding calculations are a guidance. They are a very good guidance, but they are not all the physics. There is still some physics that remains to be understood, particularly at some angles which are large angles where there can be relaxation. At small twist angles, relaxation contribution is small as far as my understanding goes, and Manish can have a different opinion. So tight binding works very well at relatively small twist angles. At large angles, you need to account for relaxation because otherwise the physics is incomplete. Yeah.
Before you talked about putting strain into the system. You talked about putting strain in the system. So is there a particular critical limit as to what you can apply the strain?
So right now, we can apply very small strains, relatively small strains, but there can be improved. As I said, it's fraction of a 0.1%, so very small strains. But our goal is not to have a static strain, but modulation of strain. kind of wobble it, pull it, push it continuously at some frequency. So we don't really care so much about the absolute amplitude of that modulation. Does that answer your question?
Okay, so we are almost at that time. So we request Professor Rohit to present.
Great, thank you.
Okay, our next talk was supposed to be by Professor Priya Mahadevan, but unfortunately she is unwell. So Mr. Dipanshu Agarwal, who is a PhD student here with Professor Sankalpa Ghosh and Professor Rohit Narula, will present his study on emergent fractality in graphene-based van der Waals heterostructures. So Dipanshu, you have 18 minutes and then 18 then? Full, okay, fine. So you have 35 minutes.
So very good morning everyone. I'm very thankful to my supervisors for giving me the chance to give a very nice talk on my thesis work. So this is my thesis work which I did obviously with my supervisors Professor Sankalpa Ghosh and Professor Rohit Narula. So this is about the emergent fractality in twisted graphene based van der Waals heterostructure, and so I'll be very briefly introducing twisted bilayer graphene just to the next slide. But before that I would like to let me recap from Professor Deshmukh's talk about the honeycomb lattices. So honeycomb lattices, for example graphene, the underlying lattice is honeycomb, and obviously for hexagonal boron nitride, which is also known as white graphene, is also honeycomb. So if we talk about the symmetries in graphene, let's say, so there are two symmetries where the Dirac cone is protected by. So the two symmetries, the inversion symmetry, the other is the time reversal symmetry. While in case of hexagonal boron nitride, the inversion symmetry is absent. So there is broken inversion symmetry due to the different chemical potential of the boron and nitrogen atoms sitting on the two inequivalent sites A and B. So Professor Deshmukh showed very nice slides about the honeycomb lattice. Therefore, I will directly start from the twisted bilayer graphene. So twisted bilayer graphene is constructed by stacking two layers of graphene. So the left figure which you are seeing, so there are two layers. I am indexing those layers in layer 1 and layer 2, and those A1, B1, A2, B2 which you are seeing here in the figure are the four inequivalent sublattices. The 2 is coming from the one layer, the A1, B1, and the 2 are coming from the other layer A2, B2. Now, how do you create twisted bilayer graphene? So when you rotate one graphene layer by theta by 2, say anti-clockwise, and when you rotate the other graphene layer by theta by 2 by the same angle, which is the clockwise, the relative misorientation will be the theta because of theta by 2 and minus theta by 2. So what you are seeing here is the corresponding Moiré pattern. So Moiré pattern is a very large wavelength pattern that is emerging because of the twist of the two graphene layers. So as Professor Deshmukh showed about the twisted bilayer graphene, it is known as the Moiré superlattice because the length scale which we get after twisting one graphene layer over another, the length scale lambda theta, which is also known as the lattice constant of the Moiré superlattice or the Moiré wavelength, is given by this formula Ag over 2 sine theta by 2. And if we see about the numerics, the lambda theta will be greater than or equal to the graphene's lattice constant, which is Ag. So at theta equal to 60 degree, this is going to be the case where lambda theta will be equal to Ag, and this is the simpler case of the bilayer graphene, so-called Bernal-Steck bilayer graphene. But if you see at the formula, it is not defined at theta equals to 0. But in between, for any twist angle, lambda is always going to greater than the lattice constant of graphene, Ag, and therefore this is known as the Moiré superlattice. So this is an periodic pattern in the real space. Corresponding to this periodic pattern in the real space, we get a corresponding Brillouin zone in the reciprocal space, which we call as the Moiré Brillouin zone, where this Moiré Brillouin zone is actually defined through the momentum shift of the two Dirac cones in the graphene layer, and the momentum shift between these two graphene layers, the Dirac cones, is actually proportional to the twist angle theta itself. So when we increase the twist angle continuously between the two graphene layer, the Brillouin zone itself increases its size, the length scale continuously increases, while if we decrease the twist angle, the Brillouin zone becomes as small as possible. Continuously decreases, the length scale continuously decreases. So what happens to the physics of this twisted bilayer graphene? So as we do the tight binding calculation of twisted bilayer graphene, we have the continuum model of twisted bilayer graphene, which we write in the sublattice space A1, B1, A2, B2 of the twisted bilayer graphene, and this is the real space Hamiltonian of the twisted bilayer graphene, where the two diagonal terms capture the physics of the two graphene layers, while the two off diagonal terms contains the details of the Moiré potential in the twisted bilayer graphene. So the usual, we have the Hamiltonian, which is translationally symmetric, where the translation operator T is the linear combination of the two Moiré vectors, and the Moiré pattern which you are seeing at a particular twist angle. The various AA, BA and AB, those are the labels that are because of the corresponding interlayer stacking configuration of the two graphene layer. So the AA is when we have the A coincides over the A of the other graphene layer, while in the case of B and AB, the scenario is different. The one layer A and the other layer B comes just below the A, and that's why we have the AB and the BA. Those RBA and the RAB, they both are representable in terms of the A1M and the A2M, which are the lattice primitive vectors of the Moiré pattern. Okay, so I'll be directly coming to the band structure, where I'm going to bring your attention about what actually we were looking at, and from that particular scenario we entered into the regime of the fractals. So I would like to very briefly point out about the magic angle twisted bilayer graphene. So we can have obviously a continuous range of angles, because we know that the lattice length scale in the real space lambda theta was given by A sine theta by 2, which is a continuous function of theta. So for every angle, twist angle, we will have the corresponding lambda theta. But what is magic angle twisted bilayer graphene? So there are certain angles, specifically the angles, discrete set of angles predicted by the Bistritzer and McDonald model was the first largest magic angle was 1.08 degree, which is nearest to 1.1 degree. The other was 0.44. There are other angles 0.35 and so on. So those angles are actually a little different. So when you will read many papers in specifically for twisted bilayer graphene, you will see little variations on those magic angles, because those magic angles are because the tight binding model of the twisted bilayer graphene involves various parameters. Specifically, I am talking about the interlayer hopping parameters, and when you take different values, you will get slightly different values for those angles, but they are more or less in the quite same range. So for example, the figure which you are seeing, the graph here, is between the band velocity, which is known as the Fermi velocity here, because the Fermi level passes through the graph point itself, with the twist angle theta. So the two angles which I am showing on the top, if you look at the Fermi velocity figure here, you can see there is a sudden, there are nodes. The Fermi velocity becomes 0, and because of this Fermi velocity 0, this is something behind those angles, and this is referred to as the magic angles. So what is happening at those angles? I am specifically pointing out the first largest twist angle, which is 1.08 degree. So why is this important? Experimentally, this was the only angle which was observed, while the other angles predicted by the Bistritzer-McDonald model in twisted bilayer graphene were not experimentally observed. As Professor Deshmukh pointed out, at smaller twist angle, what happens? The lattice reconstruction takes place. So because of those process in twisted bilayer graphene, the tight binding model which was given by Bistritzer and McDonald model do not capture the small angle physics in twisted bilayer graphene. So now what is the point which we were looking at? So if you look at this figure at theta equals to 1.08 degree, we have the two flat bands. The yellow one which you are seeing is the conduction band, and the below just is the valence band, and the two other purple and orange, they are the remote bands. So the two bands which you are seeing are obviously the flat bands, because if you calculate, so I already calculated the Fermi velocity which is equals to 0, this is the approximately flat band. So if I zoom in the flat bands in the next figure, you can see here they are not actually as flat as we are referring to. They are there is specific is a particular sort of band gap. So if you look at the gamma point, at the gamma point itself, we have near to 8.5 millielectron volt gap. So is there any possibility by which we can reduce this gap, or can we make those bands even more flatter? Okay, so even at that particular angle, we have many phases which has already been observed in twisted bilayer graphene. So it's a very large set of papers which have already been observed, various correlated phases in twisted bilayer graphene. But as I pointed out, we were looking at the flattening of the bands even further. Okay, so this is something which has already been tried or attempted. So in order to do this, to decrease the bandwidth of those flat bands even more, people have used the various things such that hydrostatic pressure, optical illumination, but with such processes, what happened? Only the magic angle changed. So for example, it from 1.08 degree, it shifted to slightly lesser, but the overall thing, the band gap is still at the gamma point remains same. The other processes is to by breaking some symmetries in the system and getting the gap. So for example, twisted metal dicharge, this transition metal chalcodenides based system, and this CMDC, the spin orbit coupling is very so strong, and you get the gap system. So it is about the using different system. But what we tried is that we actually used the other possibility by applying something called as Moiré potential. So this is already been looked at. So the figure which you are seeing here, so it contains the whole array, which is the each silicon dioxide. So because of this array of those holes, what happens? The electric field that is being applied in this system actually creates a very sparsely distributed periodic potential, which is as symmetric as of the Moiré potential or the inbuilt Moiré potential in twisted bilayer graphene. So when we do the Fourier decomposition of that potential, the contour plot shows that Fourier decomposition. So the hexagon which you are seeing is the Moiré coming from the Moiré cell itself, and the blue color and those dark colors shows the spatial distribution of that potential that is coming because of this each array of those holes. So correspondingly, the real space Hamiltonian looks like this. So we have already the inbuilt potential, the Moiré potential, which is sitting into the off diagonal elements, while the potential that is coming because of this arrangement is sitting into the diagonal, which is VR. So this is multiplied by the 2 times of the identity matrix because it is written in the 2 sublattice space of graphene A1 B1. Okay, so even after doing that, when one applies a potential which is as symmetric as of the inbuilt Moiré potential, only those flat bands shift, and also one of the bands changes its curvature. The bandwidth obviously changes, either of the conduction band or the valence band, depending upon the strength of the potential. But at the gamma point, the band gap still remains same of the order of 8.5 MeV. So obviously, this is also not working as it was supposed to. But what we did, so we also introduced a Moiré symmetric potential in twisted bilayer graphene, but we rotated that potential as relative to the Moiré potential, the inbuilt Moiré potential. So when we did that, so for example, here you are seeing the UR, which is the inbuilt Moiré potential, and the Moiré potential which we are introducing. So this is a model Hamiltonian. So I'll be later showing you some realistic super Moiré structure where we can actually see the various effects of this particular model Hamiltonian. So when we do that, so we are not introducing actually a single potential, we will be introducing a series of potential in this Hamiltonian, and when we do that, what happens? Okay, so the first problem after introducing such a potential, because we introduced an incommensuration between the applied potential and the inbuilt Moiré potential, and because of this incommensuration, what happens? We get a system where we have the 2 potential, and those 2 potentials are periodic with a different set of periodic vectors. So as compared with, as we know from the textbook problems, we have the electron and a periodic potential, we know usual block theory or the block bands, but this is a little bit different because the 2 potentials which you are seeing in the Hamiltonian, they have the different periodicity. So this is therefore a 2 potential problem. So how do we get rid of this 2 potential problem? So we actually introduced the commensuration again, because this, without this, we cannot solve for the usual, we cannot apply the usual block theory or to get the block bends out of this Hamiltonian. So when we do that, it's when we introduce the commensuration between the two set of potential. So what happens, we get this particular equation which you are seeing this on the slide. So this particular equation relates the two set of primitive vectors in the two different potentials, and the various integers which you are seeing, the P1, P2 and the others, they become the function of Q and P. So that actually happens in twisted bilayer graphene also. We do have commensurate twisted bilayer graphene, where we have infinitely, it's a discrete infinite set of the commensurate angles, and all those angles actually satisfy a particular equation. So for example, if we consider the commensuration of a square lattice, the equation will be this is for the honeycomb, sorry, this is for the square and this is for the triangular lattice. So honeycomb is obviously two interpenetrating triangular lattices. So this theta satisfy a particular equation. So all those angles, twist angles which satisfies this particular equation for given P and Q values are known as the commensurate angles. So introducing such commensuration between the two Moiré potentials, all those twist angles where the two set of primitive vectors satisfies the angle between them satisfies such an equation are characterized by Q and P. So for example, the table which shows you for the triangular lattices for various twist QP values 3, 1, 2, 1 and so on, you are getting all those series of twist angles which are commensurate angles. So we introduce the same concept in those potentials. So what we actually get, we get something we were introducing as the Moiré fractals. So I'd like to tell you a little bit story behind this. So this is not as simple as it may look, but so for example, we started with the simple twisted bilayer graphene, and then we started adding on the potentials. So when we do that, we continuously, so when we do add one potential, so for example, you are looking at this particular structure that shows the twisted bilayer graphene Brillouin zone plus one potential, we solve that equation, we get the another super mini Brillouin zone, we again add a potential, we again solve the equation and so on. So the J, which is the index characterizing the iteration level. So those are the two scales in the real space and the reciprocal space, which are correspondingly, obviously the reciprocity is showing this one is actually decreasing, other is increasing. So what we did, so when we trace out the boundary of the Brillouin zone of the original Moiré Brillouin zone, what we get is something like this particular structure. Now why this structure is at all important? So when you zoom in into this particular structure, you get the same structure, which is obviously the property we know as the self-similarity, and therefore it shows the self-similarity is known. Therefore we gave this name as the Moiré fractal. So I'll introduce you what will be the corresponding effects of the such Moiré fractals in the band structure and others. Okay, so I'll obviously introduce you about the DF also, what is the fractal dimension, or in a little bit of mathematics services, Hausdorff dimension. Okay, so those Moiré fractals are actually the iterated fractals. So as I pointed out, those structures can be generated by actually iteratively applying some sort of basic generator over and over. So these are some of the structure which we get for various QP values. So I'm showing particularly for the two QP values. So for two QP values, if we again trace the boundary of the Brillouin zone, we get these two structure with the DF as the fractal dimension. As you can see, the two different fractal dimensions. So those generators of those fractals are actually coming after applying some of the transformations. So in mathematics, those are iterated fractal system. IFS is nothing but a set of affine transformation, and you can with the number of transformations just give the cardinality of the set and all those, which is the theory of all this. Okay, so what we further did, so we actually derived the various set of generators generating all those fractals for various QP values. Okay, so now what happens at the band structure level? So this is the most important thing. So the other first important thing obviously was the geometric aspect of these structures. The other is at the band structure level. So the band structure level, we first considered the rotation of the potential, the Moiré potential, which have this, which is the same. So I am introducing the angle theta r for the rotation of the potential with respect to the Moiré potential, and the Moiré potential twist angle is still theta. So when theta equals to theta r, so for example, if I concentrate a twist angle, let's say 21.79 degree, which is a commensurate twist angle in twisted bilayer graphene, and if I consider the theta r, which is same as of theta, then what we get, this is the band structure which we get. And the most important thing out of this band structure which we get is that if you look at the either the conduction band or the valence band, in the absence of the potential, which is the orange one, within the bandwidth of those bands, either the conduction or the valence band, and after adding the first iteration of the potential, which is j equals to 2 here, we get obviously many more bands which are coming because of the adding of those potential. So those bands which are getting inserted into this bandwidth of those bands can be controlled via the fractal dimension, or can be related to the number df, which we actually derived for the various QP values in those Moiré structures. So what happens when the twisted bilayer graphene, which we consider at the magic angle? So at the magic angle twisted bilayer graphene itself, when we add those potential, you can see by introducing the incommensuration between those two potential, the inbuilt Moiré potential and the potential that we are applying. When we do that, we actually get a number of those newly inserted bands, those blue which you are seeing. Correspondingly, we have the density of states. And those numbers are very well controlled by the fractal dimension, and the formula which we derived here is the eta, which is the number of band within the bandwidth of either the conduction or valence band in the absence of the potential, can be directly linked to the fractal dimension of the structure itself. Okay, so can we see something on the super Moiré structures? Also, as I pointed out initially, that this is something which we can realize in the super Moiré structure. So I'd like to very briefly introduce first what are the multi-layer heterostructure and what is the super Moiré concept. So in van der Waals heterostructure, we construct the van der Waals heterostructure by stacking the individual two-dimension layer over one another. So we stack the same layers. It will be homo bilayer, homo trilayer, homo n layer. And if we do stacking of the different layers, it will be heterostructure, which is the name coming from the van der Waals heterostructure itself. So what we are doing, so one can consider such a structure where we have let's say the n layer stacked over one another. Consequent to this particular structure, we'll have n minus 1 twist angle. So there can be independent n minus 1 twist angle, and through this n minus 1 twist angle, we can create a parameter space of those twist angles. So for example, I'd like to this one. So for example, in case of tri-layer structure, so the two structure which we are going to look at are the HBN encapsulated single layer graphene, which is a tri-layer system. The other structure which we are going to look at is the HBN encapsulated bilayer graphene, which is a quad layer structure. In both the cases, for example, the figures which you are looking here, so the plots are nothing but the parameter space of these structure. So for example, if I consider graphene layer, I put HBN on the top, I put HBN at the bottom. There are two different interfaces, and there are two independent interfaces, graphene HBN interface and the other the bottom graphene HBN interface. There will be two twist angles. So I'm let's say the top the twist angle in the top interface is theta 12 and the twist angle in the bottom interface is theta 32. So the two figures which you are seeing here is actually the calculation of the characteristic length scale in this system. So when we started with the Moiré system, so we knew that the twist angle the twist angle itself changes the lattice length scale. But what happens when we actually stack more and more layers? So for example, I am showing the picture of the for the 3-layer case. So now what is the delta here? So for example, if I consider the graphene over HPN, which is the case of hetero bilayer, in case of graphene HPN interface, the Moiré length scale is controlled by the two parameters. So one is the twist angle of the graphene and HPN, the other is the lattice mismatch, which is the delta here I am showing. and it is approximately 1.8% as compared to the twisted bilayer graphene, where there was no lattice mismatch because we were stacking one graphene layer over another. So in that case, the length scale is purely controlled by the twist angle, but in case of graphene HBM, the length scale is controlled by the two parameters, the twist angle and the lattice mismatch. So let's say if we stack graphene, the tri-layer graphene, we will have, with the tri-layer graphene, we will have two interfaces, we will have two Moiré interfaces, and one can solve for the Moiré of Moiré. So which is the super Moiré? So the problem here is the two twist angle can be so different such that the two length scale will be very different. For example, if I talk in this way, I choose a particular twist angle in one interface, I get a particular length scale, say L. And in another interface, I choose a particular twist angle, let's say I do a twist and I get a length scale of twice of that L. But you have about 8 minutes. Okay. So when we do that, so the thing is, the calculation of the Moiré includes the two separate integers also, which is m and n. So those m and n also now becomes the two parameters which decides the super Moiré length scale. So the figure which you are seeing is actually a numerical calculation of the dominant or the characteristic length scale in such a tri-layer system with zero lattice mismatch, a tri-layer graphene case, and HBN encapsulated graphene or bilayer graphene case, where we will have the two Moiré interfaces with the lattice mismatches with delta is not equal to 0. So in these two cases, we will have a very vast parameter space, and the major problem which we are facing that one cannot access any one cannot access any arbitrary point from this parameter space. So what we did, so we introduced again the concept of the two potentials that are coming from the two interfaces, and we chose a commensuration between them. So what that particular give you, so that commensuration idea which we introduced in the Moiré fractal, that gives you access of a particular line in this parameter space. So for example, this is the case of HBN encapsulated single layer graphene. So this is the full Hamiltonian, the intralayer as well as the interlayer. So this Hamiltonian can be reduced, or one can actually derive an effective Hamiltonian by incorporating or by making use of the broken inversion symmetry in HBN layers. So when we get this particular Hamiltonian, so we again, because of the two potentials, two Moiré interfaces, we get the two potentials that again gives the two potential problem. So we introduce the commensuration to solve for such an Hamiltonian. So we get the band structure for HBN graphene HBN. So when we do that, we do the calculation for the band structure. So we keep only one potential. So let's say the top interface only, we get one type of band structure. But when we keep both the potentials and do the commensuration and then calculate the band structure, we see this particular band structure. Now what is so important? Since the commensuration between those two potentials is characterized by the two integers q and p, so we choose q and p equals to 3,1, which corresponds to 21.79 degree as the commensurate angle. So this is the figure because with only the top HBN graphene interface. So within the bandwidth of this particular band, we can see a particular number of bands or a particular peak in the density of states, the one of singularities, that is splitting into the 7. So what is 7? So 7 I have already, so that was the number which we introduced in the fractal dimension formula. So the main thing is from this particular slide is that those band structure again in this particular tri-layer system for all the line in the parameter space where we can introduce such a commensuration idea for such twist angles, all those number of bands similarly satisfy the same formula which we introduced in the Moiré fractal. The same happens for the HBN bilayer graphene HBN case also in the parameter space. So because of the bilayer or the parabolic bands, we'll have the two singularities in the band structure, the density of states, and those two singularity again splits up into the 7. That 7 can be a different number depending on the q and p value which we are choosing. Okay, so can we look at those bands? So we did actually analysis of the single particle electronics Green's function. So the RPS is one of the study where we can directly probe the single particle electronic Green's function. So when we did that, so I'll directly come to this particular plot. So in this particular plot which we did for the HBN graphene HBN case, so those center point which are seeing is the primary Dirac point which comes into the HPN graphene HPN case, but the other 6 which we are seeing at the around, so those are coming because of the 6 bands, inserting bands because of the other Moiré potential. And so this particular calculation captures the C3 symmetry or the higher order second terms in the EK dispersion of the Dirac cone. So the Dirac cone we get when we only keep the linear order term in the Kx, Ky, but when we increase or when we actually go for other orders, we get all those trigonal warping and all. So this is the figure which seems to capture those in the Dirac cone. So the primary figure, sort of this contour or this structure which we are getting at the center is because of the primary Dirac point, or the other 6 which we are getting around or that's on center because of the secondary Dirac points. So this is the very basic concept in superlattices. So for example, in graphene superlattices, when we introduce a potential of large periodicity in graphene, we have the primary Dirac point, and because of the potential we get the secondary Dirac point. So therefore we are seeing the secondary Dirac points. But the main feature from this particular plots to note that those numbers are actually coinciding with the number which we introduced in the Moiré fractal. So this we have taken the plot for the 2 different polarization of the incident light, X and the Y polarized, that is being captured by the electromagnetic vector potential of the light is the incident wave. The same sort of figure for the HPN bilayer HPN case as well. In the HPN bilayer HPN case, the very different isotropic means the very different property of those loops which you are seeing here because of the parabolic bands. And again, the main point is to get from there is the number which we have. The center is coming from the primary Dirac point, and the contribution, for example, the extra feature which we are getting in the plots, right, is because of the coming from the other bands. For example, at the high symmetry point, which is the X point in this case, the corner of the Brillouin zone, the additional contribution is coming from the other bands, while the other points are coming, other contributions coming from the one other bands.
You should please finish in 2 minutes.
Okay, so we also did the calculation for the relaxation in twisted bilayer graphene. So when we did do the relaxation, so we actually include the strain in the twisted bilayer graphene. So this was the model for the twisted bilayer graphene introduced by Oscar Wafek in 2023. So this is the continuum model which captures the strain in twisted bilayer graphene. So when we add again the series of potential into this, so what we get is the concept remains same, the Moiré fractal idea remains same, the band formula which we introduced in terms of the fractal dimension remains same, even after including so many non-linear terms in the Hamiltonian. Okay, so this is the conclusion slide where we have, so what we actually get is the axis of a particular line in the parameter space, and one can obviously control the states or the number of bands in a particular energy range. And we also introduce some sort of spectroscopic technique by which one can verify those additional states in the band structure. Thank you.
You're open for questions?
Yes, sir.
It is very interesting what you have shown. I was just wondering that when you talk about the magic angle, and what is the experiment that people have demonstrated to find the magic angle, or superconductivity itself is a signature of the magic angle. What is your comment?
Okay, so this is the Hamiltonian itself is from the single particle picture. This is a single particle picture first of all. So when we introduce another energy scale in the sense of, for example, the interaction. So what happens? So for example, if we consider twisted bilayer graphene from the BM model, or maybe the later on the Wafek model, the Dirac cones persisted. So it is in the semi-metallic phase. But when we introduce the additional energy scale in the system, those additional scales drive the system into various phases. So the single particle picture explains the magic angle in terms of the vanishing of the Fermi velocity, which is a basic concept behind the flatness of the band.
Yeah.
So this is what I answer.
Okay, probably superconductivity is
Yeah, this is the superconductivity phase is
conducting
obviously
states you can get.
after doping the system to a particular. So, for example, n equals to half or third half. So all those.
One more query that the HBN twisted bilayer graphene HBN that you have made this sample or?
No, so we just did sort of theoretical calculation, so we do not make any sample. Yeah.
Because you have shown RPS results, so I was wondering.
Those RPS results were the analysis from the single particle states. So we get after diagonalizing the Hamiltonian and all.
Oh, okay. Thank you.
Thank you.
Okay.
You talked about commensuration.
Please switch on the mic.
Yeah. So you were discussing commensuration. So I was wondering that is there a standard way we commensurate or some like from A1, A2, we reached a formula of tan inverse P by, so was it derived or like?
It actually is coming from the derivation after solving the Diophantine equation. So what you do, you can, you start with the two set of primitive vectors. So let's say the A1, A2 in the graphene, and then you look for a twist angle which satisfy a particular Diophantine equation.
Okay.
And those are the solutions of the
P
Diophantine
and
equation.
Q are solution of that equation.
Q and P are the two parameters which characterize that formula, but those are the solution for the twist angle itself.
Okay.
In terms of the
another doubt I had was like we had periodic potential here. Earlier you told like you take edged SiO2 and that was there they did something in the previous. In this one we have, so how is there a way we can realize this also?
See, the SiO2 means that etching is to create a potential which is same as of the Moiré potential. So there was no incommensuration between the two potentials. So this etching was happening to make sure that every time that etching is being done, the primitive vectors remain same of the potential. So those potential is coming because of the tuning of the electric field. So that spatial distribution of the potential comes because of that. All those holes, because that will have different dielectric and so on.
Okay.
So that's why.
So initially in the initial slides you saw there is a almost 8 MeV band gap in the flat band, right? So after applying the series of potential, how much amount of band gap you suppressed?
Yeah, so we actually did a Hubbard calculation. So we did calculated the U over W ratio, and that was so I slightly forgot what exactly, but I guess it was more than 40% or so.
More than 40%. Okay, because in the last lecture I have seen almost initially in the atomic layer we are having one electron volt, and I think after in the Moiré layer we are having almost 0.1. I think
the bandwidth you're talking about.
I think band gap.
Band gap at the gamma point.
In the last lecture.
At the gamma point.
I don't know.
Okay, so we were specifically interested in the high symmetry gamma point because it was the highest at that point, and because at the Dirac point it was obviously the 0, but yeah, at the gamma point it was 8.5 MeV. So, but see, if we do another additions, so for example the strain, so the last calculation which we did was the strain induced or lattice relaxation induced strain fields. So when we include that, there will be a change in the bandwidth, but still those bands are not perfectly flat. So for example, one idea was obviously put forward by the Ashwin Vishwanath in 2019, where they were explaining the origin of the magic angle and twisted bilayer graphene. So they showed that if you suppress completely the interlayer hopping parameter in the AA region, you will be getting the perfectly flat band. Perfectly flat means everywhere throughout the brilliant zone you will be getting a perfectly flat band, but it was obviously not the scenario. You cannot completely suppress. So it was a theoretical model to explain how the origin means the magic angles are actually is coming into this system, twisted bilayer graphene.
One more.
Yeah.
So magic angles are fixed or they can be varied?
It's a good question. So it's not. It's coming from the calculation first of all. So they satisfy. So for example, in those prediction of the magic angle, actually a series of magic angle were from the tight binding calculation or the container model itself. So all those you do the diagonalization of the Hamiltonian, then what you do, you can project those state to the conduction valence band, and then what you can do, you can expand around the Dirac point to find out the Fermi velocity. And that angle where that Fermi velocity vanishes, that is actually the magic. So this is the whole.
Okay, so it can be varied, no?
Yeah.
So maybe the time is up, and we can take the discussion outside.
I just had a quick question. Just one quick question.
Quick. Okay.
Yeah. So I missed the form of the potential you were using.
That was the. So that includes the cosine of the G vectors dot R, where the G vectors are the first 6 vectors in the Moiré zone.
Okay.
Yeah. And multiplies by the 2 times of the strength V naught.
So I don't know. As far as I understood that you use the potential on the individual layers. So how the potential was contributing to the interlayer hopping? I mean, you used some VR with the kinetic term of the graphene potential, right?
But that was those potentials which we added that were added in the diagonal. So they were not added in the off diagonal terms.
Yes.
The hopping actually was in the off diagonal.
So I was just wondering how this is contributing to the interlayer part. Like interlayer part was in the off diagonal term.
Yeah, sure. True. So the interlayer part, we are not touching the interlayer hopping.
Then how are you influencing the flat bands?
Okay, please.
All right.
Discussion outside because it's a right till whatever. So 11. And I would like to give this to the consumer as a token of appreciation.
Thank you very much.
Let me start by thanking the organizers, Shankalpa and others for this invitation. So I'll be today talking about some of our recent experiments on quantum engineering graphene boron nitride moiré. So this is a different kind of moiré than what you have been hearing. What Mandar told you about. Mandar told you about what are known as homobilayers, graphene on graphene. I will talk to you about heterobilayers, graphene on boron nitride. So this is our group. We work on topological phases in graphene based heterostructures, and what we try to do is we try to modify the band of graphene to induce new functionalities. You see, when graphene was first discovered, we were very happy with it. It's a perfect semi-metal, no band gap, no spin orbit scattering, fantastic. But we are never happy, we are never satisfied, and after 20 years of living with it, we think, what if it had a band gap, what if I could have spin orbit coupling, and what if I had magnetic interactions? And that is what we try to do. We induce spin orbit coupling, we put this Moiré superlattice to modulate the bands, we try to introduce exchange interactions, see fractional quantum Hall. These are all the people who have worked with. For this work that I am doing, talking to you about, Manish was a key player. Okay, so just to give you a one-page introduction, and I have tried to keep this talk as pedagogical as possible. What is our objective in condensed matter physics? So we try to find new constituents of matter, and in the condensed matter we look for the fundamental states of matter. Okay, so we have metals, insulators, superconductors, magnets, and these are phases differentiated by broken symmetry. Crystal has different broken symmetry. A lattice translational magnet has rotational symmetry broken. Superconductor has the gauge symmetry broken. So, and we will also in this talk break several symmetries, and because that's the name of the game. Now these are all quantum matters, but they're not topological in nature, and that's the buzzword today, right? So what is topological matter? A topological quantum system is, in simple words, you cannot change its ground state by a local perturbation, and that in some sense is it's some sort of a protection, and that inherently comes from its symmetry properties. And they are of course often characterized by a number of topological properties. As we heard today, they can have some topological numbers, like for example, as Mandar said, the Chern numbers. Examples are quantum Hall, quantum anomalous Hall, quantum Valley Hall, quantum spin Hall states, and so on and so forth. And that is what is of interest to us. So why graphene? Graphene is of course very interesting because it has several degrees of freedom. Of course, the obvious ones, I have charge positive and negative. I have spin up and down. I have valleys, the two inequivalent points in the Brillouin zone, K and K prime. I have site in the singular graphene, site A and site B. If it's a bilayer graphene, I have either the blue layer or the orange layer. So, there are many of these dichotomous spin-like degrees of freedom. Okay, and I can play with all of them. So I have, of course, no band gap, and we will use interactions and broken symmetries to change this. There are important symmetries of the system. I have time reversal symmetry, I have inversion symmetry, and the mirror symmetry. And I can break all of these or tune them using some external parameters like electric field, magnetic field, proximity effect, like I can induce spin-orbit coupling, exchange interactions, and the effect of the substrate in some sense. And this is the last thing that I'm going to, in this talk, I'll focus on this. How do I modulate the band properties of graphene using the substrate? So, geometrically. So this we already heard from a very extensive introduction. Just to recap, think of electrons in a periodic potential. Okay, just the basic electrons in a periodic potential, and you can write out its dispersion relation, and you know that if a band gap has to appear, it will appear at plus minus pi by a and its multiples, where a is the lattice constant. Okay, now for graphene the lattice constant is very, very small. Okay, it's 2. So the energy scales at which these gaps appear are very large. They are beyond my experimental range. So what can I do to increase A so that I can have these band reconstructions at lower and lower energies? So for example, this is the band. The gaps come at plus minus 2 pi by A, and of course I can write it in the folded zone scheme. And then these bands fold, and these energy scales of course are determined by what is the value of A. If I can increase A, this will shift to lower and lower energies. Okay, so in the case of graphene, it is around 2 nanometers. If I can make it now 20 nanometers, the energy scales come down by a factor of 10, and they come within my experimental range. That's one of the major motivations. Okay, so if I can control the periodicity of this graphene lattice potential, it gives me a knob to modulate the band. Okay, and I can achieve it using a Moiré superstructure. So what's a Moiré superstructure? As we learned that I can have two materials which can either have exactly the same lattice constant or slightly different lattice constants, and I can just slightly twist them. And when you twist it, you see this Moiré patterns where the potential which the device faces now depends very sensitively on the angle between them. Okay, so for example, you can have this twisted homobilayers, which is the twisted bilayer graphene that Mandar spoke to you about. I will talk of twisted heterobilayers, where one of these layers is graphene, the other one is boron nitride. Okay, they are almost homoelectronic, but in one case I have only carbon atoms, in another case I have the A and B sublattices. In A I have boron, and on the B I have nitrogen, and that's my system of interest. So what do? We take boron nitride, we place a graphene on top, and we place another boron nitride on top, and we try to align the edges such that the angle between these layers is as close to 0 degree as possible. Now, unlike in the case of bilayer graphene, twisted bilayer graphene, there is superconductivity here, there is no magic angle here. But the closer, as we heard in the previous talk, the closer you can come to the smaller angle, the larger the reconstruction of the bands. Okay, so we try to make the angle as small as possible. So what do? So suppose this is my graphene and that layer and the boron nitride. This is the band structure of graphene, just pristine single layer graphene. These are your so-called Dirac points near which I have the linear dispersion. I put a boron nitride on top and align it at a small angle. This calculation is for I think 0.1 degree. And what you see is that now around at 120 or 130 millielectron volts, which is experimentally accessible to me very easily, on the whole side, I open up a band gap. Okay, and then I have all these Van Hoff singularities. I open gaps here which are K dependent. You can of course not access them through transport, but you can study all these properties here. The Van Hoff singularities, gaps, so on and so forth. Okay, so you can drastically modulate the band structure by aligning graphene with boron nitride. But and how do you know that? When you measure the resistance, if you know that if you measure the resistance of graphene at the Dirac point, the density of state is 0 ideally. So when my chemical potential is there, my resistance is large. So this is the backgate voltage is, think of it like a number density or energy. When energy is 0, my resistance is large. As I move away, I have finite density of states till I hit this so-called secondary Dirac point. Okay, at this point, my resistance again, my resistance again develops a peak. Okay, so this secondary peak is coming from when my chemical potential is here. Okay, and this proves to me that, okay, now I have aligned. And as I will show, the position of this peak tells me what is the twist angle in this case. But why be, satisfied by twisting only one? What I can do is I can have the graphene, top HPN is rotated by an angle θ1, bottom HPN is rotated by an angle θ2. And that makes what is called a super Moiré. So let's see what the physics becomes. So this is the top Moiré, this is the bottom Moiré. Each of this is giving me an interference pattern. But then when I put all three together, I get a super Moiré. For top and bottom Moiré, single Moiré, the maximum wavelength for 0 degree misalignment can be 14 nanometers. Now I am having an interference of these interference patterns, and this can be 30 nanometers, 40 nanometers. So what I've done, I've effectively taken the graphene lattice constant from around 2 nanometers to 40 nanometers, and I'm renormalizing the energy structure to arbitrary low energies. So for example, this is my pristine graphene. I have put a boron nitride on top. Okay, this is my band structure. Let me take another graphene, put a boron nitride in the bottom with a slightly smaller angle. I get this band structure. Now let me take this graphene and put boron nitride on the top and on the bottom with slightly different twist angles. And then you get this kind of a band structure. You see that you do not get a unlike the single Moiré, you do not get a single gap, you get many band gaps. Okay, so the double Moiré band structure is somehow greater than the sum of its parts. It's not that I will get only one gap, I get many band gaps, and as I will show you, these band gaps have a fractal nature. And that's what we start out to measure. So how do you know I have double Moiré? Instead of one peak here, now I have two peaks. And the number density at which these peaks come tell me what is the twist angle of graphene with the top HBN and with the bottom HBN. Okay, so now how do I know that? Okay, so let me just digress a minute and tell you something about what are known as the Brown-Jack oscillations. Think of, electrons moving in zero magnetic field through a lattice. It moves in a straight line. Okay, now I apply a magnetic field, and then the electron will begin to curve to cyclotron motion. Okay, but think of it like a Young's double slit experiment. An electron is moving along the lattice. Okay, it's moving along the lattice bonds. When the magnetic flux through these cells will become one flux quanta, the electron's wave functions will interfere constructively with itself, and it will move again in a straight line with a maximum chance of transmission from one end to another. Think of, like an Aharonov-Bohm experiment of a Young's double slit experiment. Okay, that kind, an interference experiment. So what I need to do, I need to apply a magnetic field such that the flux quanta through each cell is phi naught. What is value of phi naught? H pi e. Now the graphene cell is very small. If I need to apply a one flux quanta, I have to apply 10,000 Tesla. I cannot do it in the lab. The boron nitride graphene Moiré supercell is very big. Okay, it's 10 times larger. Area has come down 100 times smaller. So I can apply a 100 times smaller magnetic field, 0.1 Tesla, and I can see these oscillations. Okay, so you measure these oscillations, and I'm not sure if you can see it very clearly, but as a function of inverse magnetic field, this is the number density, this is the resistance or the conductance, and you see this bright and black and white, the contrast. So you see these oscillations, and here I show the oscillations at different number densities. Okay, and you see these oscillations, and from the periodicity of these oscillations, you know what is the Moiré wavelength. Okay, now how do I measure the fractal Moiré gaps? Let's again come to it. So this is my structure. I have the boron nitride, I have graphene, I have boron nitride, and let's think of the Brillouin zone of the upper Moiré. Okay, now so imagine the red one is the Brillouin zone of graphene, the blue one is that of the boron nitride. They are slightly rotated, so that they are rotated, and they also have different shapes because the lattice constants are different. Okay, now at this high symmetry K point, you form this mini Brillouin zones. Remember I told you now the lattice constant has become 2 pi by A, where A is the length scale of the Moiré, and the length scale of the Moiré is 40 nanometer. So the lattice constant or the reciprocal lattice vector of the Moiré is much smaller than that of graphene, because the lattice constant of the Moiré is much larger than that of graphene, and the reciprocal lattice vector is inversely proportional to the lattice vector. So this is effectively the Brillouin zone, very small Brillouin zone of the Moiré. So now that's what I'm showing here. So these are my two reciprocal lattice vectors of the Moiré. Okay, and you know, if I have these two are the reciprocal lattice vectors, this is the primitive area, and what is the number of where will a gap open up? A gap will open up at k equal to plus minus pi by a, and that is given by the number density, which is the degeneracy, times the area of this reciprocal space primitive cell. Again, what is degeneracy? Degeneracy is the number of electrons each k point can hold. In case of graphene, each k point has two values and two spins. The degeneracy is 4. Okay, so it is just the number density at which gap will open is given by 4 times the area of the reciprocal lattice space. That's good. So now this is the Brillouin zone of the upper Moiré. I have its reciprocal lattice vectors. This is the Brillouin zone of the lower Moiré. Means the Moiré that graphene forms with the lower boron nitride. This is its reciprocal lattice vector. Now I bring these two together, and I have 4 sets of reciprocal lattice vectors. The red one comes from the top Moiré, the green one comes from the bottom Moiré. And now I can define 4 areas, not a single area. Okay, so G1 alpha cross G2 alpha, where G1 alpha and G2 alpha are the reciprocal lattice vectors of the top Moiré. Similarly, G1 beta cross G2 beta, where G1 beta and G2 beta are the reciprocal lattice vectors of the bottom Moiré. I can also have, G1 alpha cross G1 beta and G1 alpha cross G2 beta. So I can define 4 areas now, not a single area as I had in the previous case. I can define now 4 areas. I can actually define 6 areas. 2 of them are degenerate, I mean, G1 alpha cross G1 beta, there is another version of it which is G1 beta cross G1 alpha. It's the same thing. So I can actually have 6, of which only 4 are distinct. So now I can define 4 areas. And because if I can define 4 areas, the gap will now open at a number density which is given by a linear combination of these 4 areas. Remember, the gap opens where the number density is gap is the degeneracy times the area of the smallest unit cell. Now the smallest unit cell will be a linear combination of these 4 possible areas. And they, of course, since it's a linear combination, I have these integer coefficients m1, m2, m3 and m4. These are the quantum numbers which quantify the these lattice, and I will give you examples of that. So now you can see I can have m1, m2, m3, m4 to be any arbitrary integers, and so gaps will open up at all these values. Okay, I can put whatever values of m1, m2, m3, m4 plus and minus I want, and whatever number density pops out here, I will have gaps at that. So how do I do it? I take this structure, I make it into a hall bar, and I do the measurements. Okay, and this is a plot of the hall voltage as a function of number density. And you see that you have so many places where the hall voltage changes sign. And at each of these points, if you measure the conductance, you see that the conductance goes through minima. So many places where the conductance goes through minima. And these 4 numbers which you see on the side, those are those 4 quantum numbers, m1, m2, m3 and m4. So you can see where this resistance goes through minima, and you can map them to these quantum numbers. And so you can calculate those quantum numbers theoretically, and you can map it to your experiment. Okay, so that's how you know that these are fractal gaps. So this is the calculation that Manish's group did. This is the calculation of the density of states, and you see that the density of states goes to 0 at several values of the number density. Exactly at those number densities, the hall voltage changes sign, the hall number density has a divergence, and the resistance has a maxima, or the conductance has a minima. So this proves to you that there are several band gaps in the system. Okay, not a single band gap, and the position and the number of these band gaps you can tune through your twist angle. So you can also, of course, also see this in the displacement field, number density field. I will not go into it, the details are in this work. So now, as we heard before, the bilayer graphene is beautiful because you can tune its band with a displacement field. When I apply a perpendicular electric field, I break this layer degeneracy. Okay, I create layer polarization. So now imagine I have two layers of graphene. There is a boron nitride here, there is a boron nitride here. Maybe the lower boron nitride is forming the moire. Okay, I apply an electric field and I can confine the electrons maybe to the upper layer which do not see the moire potential, or the lower layer which sees the moire potential. So in the same system, I can confine the electrons once when it does not see a moire potential, once it sees the moire potential. And if you do that, this is what you see. So these numbers here represent the perpendicular electric field. Okay. So if you see a displacement field D equal to 0, the conductance which is shown by this purple line is symmetric for both electrons and holes. As I start increasing the displacement field at large positive displacement fields, the conductance of the electron side is almost independent of the displacement field, while that of the holes fall very, very sharp, goes to 0. I flip the direction of the electric field and it just flips, just the electrons become holes and holes become electrons. Okay. Which tells you that when I flip the direction of the electric field, I was now confining electrons on this layer and holes in this layer. Now I am doing the opposite. I am confining holes on the top layer and electrons in the bottom layer. So in one case the electrons fill the moire, in the other case the holes fill the moire. How do I justify this? So this was a calculation which was done, which calculates the density of state versus energy, and it shows that look at the red one, which shows the total density of state, and there are some spikes, depends on the number density and the displacement field. Okay, and this is our measured experimental data. Okay, and it just matches one-on-one with what is theoretically predicted. So this is how the density of, this is the conductance which is proportional to the density of states, and the density of peaks follow exactly what is theoretically predicted based on this model of layer polarization. How much time I have left?
You have 14 minutes.
Okay, good, thanks. So, so then the question arises, okay, I have made this moire potential. I have shown you that, there are several band gaps. The question is, how does transport take place in this material and how is it different from a pristine graphene material? The question you ask is, what is the mechanism of scattering in a moire lattice? So now a superlattice, they have a larger real space periodicity lambda, okay, and hence the reciprocal lattice wave vector G is 10 times smaller than that of graphene. Okay. Now we have all learned in our basic condensed matter that when I can have an electron coming, I can scatter, okay, and if the k minus k prime is of the order of G, which is a reciprocal lattice vector, I can backscatter the electron. And all of us know that that is what is known as Umklapp scattering. Now, in the case of single layer graphene, okay, the reciprocal lattice vector is large because A is very small. I cannot have Umklapp scattering. But in the case of moire, where G has become very small, my transport begins to be dominated by Umklapp scattering. How do I say it? Well, this is of course, so I have two electrons which are electrons coming in, K1 and K2. They scatter, I get K3 plus K4 plus the reciprocal lattice vector. And this I can have only when the K's and the G's are comparable, which happens in this case of moire because G has become very small now, lambda has become very large. And Fermi liquid theory tells you that if this is a scattering mechanism, then the resistivity will be proportional to T squared from the not the regular T. So what you do, you make this device, but in this case, we make a single moire device. So the moire is formed by the bilayer graphene only with the top boron nitride. The bottom boron nitride is twisted at an angle more than 5 degrees so that the moire potential is negligibly small. This is the device. From the resistance, you know that, okay, it's a single peak, so it's a single moire. Lambda is 14 nanometer, the twist angle is almost 0 degree. From the Brown-Jack measurements, we know that. So then what you do, so this is the Brown-Jack measurements. Now, someone was asking me, how do I measure the angle? You know that this periodicity you measure these oscillations with 1 by B, you take its Fourier transform, you get the Fourier frequency. The Fourier frequency is related to the Moiré wavelength by this equation, 14 nanometers. Okay, and the Moiré wavelength is related to the twist angle by this equation. Plug in the numbers, you get the twist angle. That is exactly the way you can measure the Moiré angle in the system. Okay, so now I cannot of course see Umklapp at all number densities. I have to satisfy this condition. And to satisfy this condition, it's a simple back of the envelope calculation. You can show that the wave vector must be g by 4, which is pi by root 3 times the lambda. The lambda is a real space periodicity. And which tells you that the number density must be around 0.9 times the number of electrons I can put in a unit cell. N0 is the number of particles.
Experimentally, how do you confirm that your Moiré angle is smooth throughout the sample?
I will come to it in a second. Maybe I'll answer it during the question answer.
Okay.
So this is n by n0, where n0 is the number of electrons in your one Moiré plaquette. And this is the region around 0.9 where I expect to see the Umklapp scattering. So what we do, we measure the temperature dependence of the resistance versus number density at all temperatures. And there is a high temperature phenomena. I don't have to go to millikelvin, so from 5 Kelvin to 300 Kelvin. I just subtract out the background. Background is the resistance at 5 Kelvin. And then I plot R versus T squared as a function of n by n0. And you see that in this part of the plot, all the curves collapse on top of each other, which tells you that the delta R, and what is delta R? Delta R is R at a given temperature minus R which is coming from phonon scattering. And I assume that the resistance at 5 Kelvin is entirely from phonon scattering, from other sources. So I just subtract out that value, I get delta R. I divide delta R by T squared, and all the plots collapse on top of each other, even in this expanded scale. That tells me or indicates to me that in this region, the scattering is dominated by, the transport is dominated by Umklapp scattering. And so this is delta R by T squared. I do it for different number densities for holes and as well as for electrons. I see that the Umklapp scattering strength is slightly different from electrons and holes because of the band structure asymmetry. Now, how do I know? We do the measurements at different twist angles, okay? And we calculate this. Whenever you're doing this Umklapp scattering, people have used this Rice-Kodawaki-Woods analysis, which shows that there is a phenomenological parameter, Fn, which you can calculate, which is just depends on the ratio of the Kb by Ef. And you can plot it as a function of the twist angle, and you see that as the twist angle increases, this parameter drops drastically. And which you expect, because this parameter is a measure of the Umklapp scattering. As my twist angle increases, my this lambda decreases. As the lambda decreases, my reciprocal lattice vector increases, my Umklapp scattering goes down. Again, so this is data, the bismuth, graphite, antimony, these are all data which is existing in previous literature of this parameter Fermi velocity on the x-axis, and this parameter A, which is that parameter Fn multiplied by the thickness of the material, and that's supposed to be a universal parameter. So we took this previously existing graph and put our data on top. M1 and M2 are two different samples, and you see that it follows exactly the same pattern as followed by all other materials over the last 50 years, which shows that it's actually an Umklapp scattering. Okay, so now how does the Umklapp scattering change with temperature? Well, with a displacement field, as I told you, if I apply a displacement field, I can have layer polarization. With larger displacement field, I effectively localize the electrons to one layer, not to another. Think of I have two metal plates or two conducting layers, I apply a displacement field. When I apply a displacement field, electrons will prefer to be on this layer than in this layer, because this layer has a higher energy than this layer. And the two layers are talking to each other. They are not disconnected layers. So electrons go now at high displacement field, electrons are localized only in one layer. And the physics of this bilayer thing which I am talking of, it breaks down. And so what happens? Your Umklapp scattering actually should go as d square. That's what shown by Levitov et al. And this is our experimental data as a function of displacement field, the strength of the Umklapp scattering at several different temperatures. and it nicely follows a d square. It's not perfect parabola. I do not know why it is not so. There are probably some correlation effects which the calculations do not take into account. There is also some plus d and minus d asymmetry which I do not understand. Okay. So this is here reference. Now just over the last 2 minutes.
You have 5 minutes.
Oh, good. So I will take 2 minutes. Last is some experiment which is currently going on, which is a Chern insulator quantization at B equal to 0. You know, as Mandar introduced to you, in these materials I can think of a Chern insulator. Okay. Now Chern insulators, of course, I can have a valid discriminating Chern insulator plus 1 and minus 1, but they will cancel out. However, how do you normally do it in another materials? You apply a magnetic field. You break time reversal symmetry. Here, if you do not apply a magnetic field and you do not break the time reversal symmetry, I must have some other way of breaking the time reversal symmetry. And some experiments that we are currently doing suggest that if, for example, graphene on boron nitride is nicely strained, when we do the Raman, we see that there is strain, and the strain is not very homogeneous. So, and we know that strained graphene field are pseudomagnetic field. The pseudomagnetic field on the K and the K prime values are opposite, okay, because of the similar self-rotation argument that Mandar told us about. What our experiment shows is that when I have these two magnetic fields, plus and minus, there is the interference effect between them, and that can lead to a finite Chern insulator. Okay, so for example, this is a boron nitride graphene heterostructure. When you measure this resistance at zero magnetic field at low temperatures, you see that the conductance approaches E squared over H, while this is for two different configurations, while your the Hall conductance approaches E squared over H, while your longitudinal conductance approaches 0. Now our samples are not yet clean enough. My student believes this is Chern insulator, I still do not believe it. So our samples are not clean enough yet to claim that it's a Chern insulator, but this is something which we are working towards. So we believe that eventually if I can make even better devices, I should be able to see these Chern insulators in this doubly twisted boron nitride graphene heterostructures. Okay, so this is the 2D plot of it. So here it is electric field and number density. This is a plot of the longitudinal conductance. In these parts of the spectrum, large negative displacement field and electron and large positive displacement field and holes, your gxx goes to 0, and in these parts your gxy goes to 1. So there is a large range of parameter space where the apparent quantization is happening, although I'm not very happy with the level of quantization yet. So you can of course see how it tunes with displacement field. So this is and how it tunes with temperature. So this is at 0.5 volt per nanometer, and here is the conductance measured with temperature. And you can see that the conductance stays almost 0 till around 40 Kelvin. So it's actually quite a high temperature effect. It's a high energy effect. How do I know that? Of course I can do the measurement at other displacement fields, and you see that the conductance stays 0 and your GXY reaches quantization till around 50 Kelvin. What are the energy scales? I apply a magnetic field of plus minus 1 Tesla, I cannot break the quantization. Okay, beyond that I go into the quantum Hall limit. So even with a magnetic field of plus minus 1 Tesla, my conductance GXX stays 0, my GXY stays close to 1 E squared over H. So this is a work in progress, and any ideas on this is welcome. I do not see any hysteresis as I sweep the magnetic field up and down. This was surprising because any anomalous Hall effect usually shows, in quantum anomalous Hall effect usually shows a hysteresis. I do not see it here. I do not understand why. And so let me summarize with this. I have shown you 2-3 examples where we can tune the graphene Moiré band structures, and now I can play on top of that. I can impose on this superlattice several kinds of interactions. For example, we have taken this graphene and boron nitride Moiré, and I did not show the data here. We induce spin orbit coupling in this, and we see quantum spin Hall effect. Currently we are trying to induce ferromagnetic interactions in this and trying to see the quantum anomalous Hall effect. Okay, and of course it's a beautiful playing ground because I can have several external parameters like electric field, magnetic field. Currently we are doing strain to tune the bands. Okay, so and their combinations, and we are probing the effect of Moiré potential on the fundamental quantum Hall phases like fractional quantum Hall effect, quantum spin Hall effect in bilayer graphene, quantum anomalous Hall effect, and some indications but not really. I am not convinced yet of quantum Valley Hall effect. Okay. And these are the people who have worked on this project. Manish features prominently. These are my students. Robin is a Manish's student. Shubhankar was a postdoc. Shinjan, Ishita, they are Manish's student. Mohit and Priya did primarily the work which I showed you. Harsimran is currently working. And HRK helped us with it. And thank you very much for your attention.
Yeah, so open the house for questions, please.
Yeah, I had a question, Avik. Why do you call those 4 numbers of this in the Umklappskraft? Why do you call them quantum numbers? I mean, they're just numbers which are integral multiples. They're not, as I understand, they're not quantum numbers.
They are quantum numbers. Okay, that's not my nomenclature. That's how they are known in the literature. But I think the only justification for calling them quantum numbers is that just like you can what can I say, label the energy levels using SPDF numbers. Here I can label those energy levels where the gaps are opening using these 4 numbers. In that sense.
How do you reduce the or decrease the bone and relaxation time?
I cannot do that. Manish does that. Maybe he can answer your question better.
The phone and relaxation time for making the device paper things. Experimental members.
I raise my hand. I don't know how to do that.
Okay, one general question.
Manish, he just threw you under the bus.
Yeah. Manish is supposed to know.
Okay, the next one. What are the challenge for making device if you're choosing this kind of thing?
That my students will be able to tell you better. Success rate is very small. Okay, we work for weeks, and if you get 1 or 2 devices, you're very happy. What happens is that you can make a device and you can have the proper angle, but the biggest challenge is maintaining the integrity of the device after you're actually picking up these atomically thin materials and trying to precisely align them on top of each other without having a single wrinkle. I mean, imagine, I always think when I try to put a screen guard on my phone, I get so many bubbles. Now imagine trying to have these 2-dimensional films trying to align on top of each other. You get all these bubbles, tears, wrinkles. So you get this, you throw out the device and you make another one. It's very hard. I can't do it.
Thank you.
So what kind of band calculations with these? Maybe a question for Manish.
Tight binding in the continuum.
Okay, any like relaxation effects? And quite surprised that you got that band gap agreement and it's such good for such a kind of plain vanilla kind of a calculation. Very interesting. Interesting.
Avik, I'll ask you one question. So can you go back to the plateau that you showed? Or the so-called plateau?
Picks up the weakest point in my data.
Yeah.
This one?
Yeah, so to me it seems like the plateaus between -1 and 2 are much better formed.
These ones?
Yeah. So why minus e square over h? I mean, to me it looks like the other two are probably...
Which one? These ones?
Yeah.
So again, I do not understand what is going on here.
But are you marking the plateau that's below? That's what I'm asking.
I'm just looking at this one and this one, because this is where my gxx is going to 0 very nicely.
Right.
At those points, the gxx is finite.
Yeah.
So maybe it is just fortuitous that something is happening here. I do not know actually what it is. And it's not reproducible. In another configuration, it's not reproducible.
Mm-hmm. But the main question was, is that close to e square over h?
This is E squared over H. This is something, you know.
No, not that one, the one above.
This one?
No, the one to the right.
This
Yeah,
one?
that one. Yeah.
If I am very, you know, feeling lucky, I will say it's 1/3 and 2/3. But no, it's not that. Okay.
So, sir, you showed the carrier density equals to the summation over MIAI. So, what the geometry that this area has? So, what is the geometry? So, the total area M1A1 plus M2A2.
No, that is what I did not show you in the paper. I should have put a figure. When you look at these areas, they become fractal, just like what you heard in the previous talk. These areas have a fractal nature. So you have this M1A1 plus M2A2. You plug in these areas and you put some numbers, integers M1, M2. You plot them. You will see that this becomes nicely fractal with a Hofstadter dimension of 1.2, 1.3. So that's why this gap, so the Brillouin zone of these materials is not a regular shape. It's a fractal.
So it means corresponding to each gap in the electronic spectrum, there will be a different geometrical structure.
Yes. So at every gap, your band structure at that, your Brillouin zone at that point is a fractal.
So it's what kind of fractal? So can we, is it an iterated fractal or KMEs? So how do we calculate the, let's say, the fractal dimension of those fractals?
You can do that, right? You can just look at the fractals, and you fractal dimension, you mean the Hofstadter dimension.
Hausdorff dimension, yes.
So the Hausdorff dimension, the D you can actually calculate by the standard
the box theorem.
Yeah. And it comes between 1.2, 1.3.
Okay.
But it depends a lot on the details.
Thank you.
So you have a question?
Magnetic field, you have gone up to 1.5 Tesla.
Yes.
When at high magnetic field, did you
High
check?
magnetic fields, since these are high mobility devices, you start seeing the Shubnikov-Diaz oscillations. Even at 50 Kelvin, you start seeing the Brown-Jack effects and other effects. So the other magnetic effects come in. So then this effect becomes obscured. So we have gone up to 16 Tesla, but other effects come and kill this effect.
Okay, thank you.
Okay, thank you so much. Yes. Thank you so much.
Thank you so much. Okay, so next up we have a freshly minted doctor from our department, Dr. Disha Arora, and she will talk about polarization controlled optical response of twisted bilayer graphene. And Disha, you have 30 minutes plus 5 minutes of questions.
Good afternoon, everyone. So before beginning with the presentation, I want to thank the organizing committee, which includes my PhD supervisors, Professor Rohit Narula and Professor Sankalpa Ghosh, and also Professor Rahul Marathe, who has served as a student research committee member during my PhD. So in today's presentation, I'll talk about the polarization controlled optical response of twisted bilayer graphene. And the first part of the presentation will talk about the photon absorption in twisted bilayer graphene, while the second half will be about the interference effects in the polarization controlled Rayleigh scattering in twisted bilayer graphene. Yeah, so just to begin with a very brief introduction to 2D layered materials. So as we see, this is a general library of the 2D layered materials, where the two prominent examples are graphene and hexagonal boron nitride, discussed a number of times in the previous talks. Now just coming directly to the Moiré patterns, we have already seen in the previous 3-4 lectures that Moiré patterns are formed when the two adjacent layers, these are rotated or they have a lattice mismatch between the layers. And in the general day-to-day life also, we are able to see the Moiré patterns, be it in the AC mesh windows or in the buildings, even if you overlay two cones. Coming to the system of interest that I am interested in is the twisted bilayer graphene. So Moiré pattern can be seen in twisted bilayer graphene. So we have two graphene individual layers. One is rotated by theta by 2 in the clockwise direction, while the other is rotated in the anti-clockwise direction. So when these two are overlaid on one another, what we see is a beautiful pattern emerging out. As you can see how this pattern is changing as you change the twist angle labeled as theta. And the first theoretical description for such a structure was provided by Santos in the year 2007. So just a visualization, of course we have seen in the previous talk also, this is the real space lattice, two graphene structures rotated by theta angle, and the correspondingly these two larger hexagons are the brilliant zone of the individual layers that have a misorientation of theta between them, while these orange hexagons, the mini hexagons whose side length is increasing as the twist angle is increasing, are referred as the mini brilliant zone or the Moiré brilliant zone. So this is a slide that talks about the Hamiltonian of the twisted bilayer graphene. I won't go into the detail of the structure of the Hamiltonian, but of course would like to mention a few points. So in the figure, if you see these pink and blue layers, they represent the individual layers of graphene, while these two hexagons, they represent the rotated brilliant zone, and this orange mini brilliant zone is the brilliant zone formed due to these two rotated layers. So this repetition of these orange layers leads to something like honeycomb lattice like graphene, as depicted here. Now here these 2 points, the blue one and the pink one, they are the rotated Dirac points of these individual layers. Now if I look at this Hamiltonian, so this is the minimum Hamiltonian of the twisted bilayer graphene. By the term minimum I mean that I am considering only my 4 nearest Dirac points in the construction. In practical, of course, the Hamiltonian of twisted bilayer graphene is of infinite dimensions, and one needs to converge the Hamiltonian according to the requirements. The diagonal terms represent the Hamiltonian of the rotated graphene layers, while the off-diagonal terms are the individual stand for the tunneling matrices between the two layers. For our calculations, so this model was actually given by Bistritzer and McDonald in the year 2011, and over the time many corrections have been incorporated. My work generally deals with the optical energies, for which it was important to understand that how the higher bands are altered if we include certain corrections. So we included 2 corrections in our calculations. The first one was the corrugation, which can be easily incorporated by setting the parameters W0 and W1 that account for the interlaid tunneling between the localized AA and AB rich region not to be equal. And second is the doping dependent Hartree interactions, which is the parameterized form given by Goodwin. So what we observed that the black one is the band structure for the pristine twisted bilayer graphene that comes from the model given by Bistritzer and McDonald. We included the corrugation effects, and if we look in the higher bands from the energy 0.5 to 1, we see that the bands are strongly altered from the ones that we got from pristine twisted bilayer graphene. The second correction, we incorporated the effect of doping, and the higher bands were not that much affected. So for our calculations, we figured out that the corrugation effects give the major changes in the higher bands. Now coming to my work that deals with the single and 2 photon absorption. So these are the equations that I won't go into the detail, but I would like to mention few terms. Alpha 1 is the single photon absorption coefficient when we have a single incoming photon, and we would like to see that how does the single photon absorption coefficient varies with the energy. And the alpha 2 is that instead of 1 photon, now we have 2 photons. So either it can take place via this method, that means both the photons are absorbed simultaneously, or we have other method that it absorbs in a stepwise manner. So the summation over M here, it simply means that we have incorporated all the possible combinations in which these 2 photons can be absorbed by twisted bilayer graphene in a stepwise manner. So coming to the first, we'll see that how does this parameter alpha 1, which is again the single photon absorption coefficient, varies with my incoming laser energy. And what we see, so on the x-axis I have my laser energy, and on the y-axis I have my absorption coefficient, and I start with the twist angle say 1.05 degree, and then I slowly increase my twist angle to 1.2 and so on. So what I see that there is a dominant peak observed at a specific laser value. Now it was interesting to find out that the laser energy at which we are able to see this dominant absorption peak corresponds to the Van Hoff singularities in twisted bilayer graphene. Moreover, the other interesting parameter that we are able to find out from here is that as we are increasing the twist angle, say from 2.5 degrees to 11 degrees, what we are seeing that the energy at which we are getting the maximum of the absorption is shifting from my infrared range to my visible range, which means the twisted bilayer graphene can be used as a tool, as a versatile tool to tune my absorption from a given range to a desired energy range. Then the important question arises that how does this behavior of this absorption coefficient changes from its host material like graphene or bilayer graphene? Yeah. So to do this, first we consider the continuum model to calculate the absorption coefficient of single layer and bilayer graphene, which was the calculation already performed in the year 2022. And if you look at this graph, I would like you to have the attention at the following plots. So the red dashed line corresponds to the absorption coefficient for single layer graphene, the pristine graphene. Then the then the pink dotted line, this one, is for the bilayer graphene, non-interacting bilayer graphene, and these different colors represent for twisted bilayer graphene as the twist angle is varied. Again, on the x-axis we have the laser energy, and on the y-axis we have the absorption coefficient. Now the calculation for graphene and bilayer graphene here are considered using the continuum model, which of course is not appropriate because we are going up to the higher laser energy, and this model does not capture those energy bands. So to modify this, we extended our calculation to the full tight binding model, where we can actually go up to these laser energies, and we found a very subtle change in the absorption coefficient behavior. Now we found this model to be appropriate to compare our results with twisted bilayer graphene, and what we saw that as we are increasing the twist angle, say from 2.5 degrees to 11 degrees, the value of the absorption coefficient is continuously decreasing and eventually reaching to that of two decoupled graphene layers, which is represented by these green lines. Moreover, on reducing the twist angle, the magnitude of this alpha 1 is continuously increasing. Yeah. Now the second part was to see that how does the effect of doping that we incorporated using the parameterized form that was provided by Goodwin actually affect the behavior of this absorption coefficient. So the solid line represents the pristine, the corrugation effects are included but the doping is not considered. Then we slowly increase the doping concentration, and in the zoom in you can see that the blue arrow corresponds to the energy peak of the pristine, the red arrow corresponds to the energy of the pristine twisted bilayer graphene, while the blue arrow represents for the highest filling factor. So if we see a little red shift on increasing the doping, it's not very of a not very large magnitude but a very marginal magnitude. Similarly, on the electron doping we see a similar effect. So that means doping is not causing that much effect in our calculations or in the behavior of the photon absorption coefficient. The major effects are encountered once the corrugation effects are included. Now the second part of our calculation is about the two photon absorption. So now here, instead of one photon like I did in the previous case, I have two photons. They can be either absorbed at a single point, or I can say simultaneously, or we can have one photon that is absorbed, then we have a second photon and that is absorbed. And again, when we do the second, when we have this second possibility, so this M represents my intermediate states, I and F stand for my initial and final states. So we have taken care that all the possible intermediate states are incorporated in our calculations. And these are the equations, just to recall that this is the transition probability when both the photons are absorbed simultaneously, and this is the transition probability when the photons are absorbed in a simultaneous manner, and this is taking care of the interference between all the possible states. Then we can calculate the second order or the two photon absorption coefficient and study its variation again with the incoming laser energy as we did in the previous case. So again, we have on the x-axis, we have the laser energy, that is our incoming laser energy. So we are here considering only the degenerate photons. That means both the photons, the incident photons, are of the same energy. So on the y-axis, we have the second order absorption coefficient. And again, I am increasing my twist angle from 1.8 to higher angles. So in my calculation, I went up to 11 degrees. Now what I observed is, firstly, as the twist angle is increasing, the magnitude of this alpha 2 is continuously decreasing, and this value at which we are getting the maxima is 1/2 the value that we obtained in the single photon case. Since here we have 2 photons, and that too both the photons are degenerate.
The x-axis is EV or what is it?
It's the laser energy, it's the incoming energy.
Of all these plots?
Yeah.
Okay.
And x-axis is the laser energy of the photons. Both the photons have the same energy. Now the question arises, now we have 2 photons and I am studying the polarization control. So is there any specific orientation in which I can get the maxima of this absorption coefficient, or is it arbitrary? So to do this, I have set a notation theta A1, which is my polarization angle, or you can say the polarization direction of the first photon, and theta A2 is the polarization direction of the second photon. And these are set according to the coordinates shown over here. So these are 2 graphene layers. So this is my coordinate system that I am taking into consideration. The orange arrow is my first angle and the blue arrow is my theta A2. That is the polarization direction of the second photon. And the difference between them is something I call as phase difference or phi. So in the case 1, I set that my theta A1 equals to theta A2. That means the polarization direction of both the photons are varying in phase. While in the second case, I say that both the photons have a phase difference of say phi in their polarizations. So what we see that as the phase difference increases from 0 to 90 degree, or I can say phase difference 0 means that both the photons are parallelly polarized, while phase difference 90 means that they are cross polarized with respect to each other. What we see that as the phase difference is increasing from 0 to 90, the magnitude of alpha 2 is continuously decreasing. Similar data can be seen as a polar plot also, that in the first case we have both the thetas to be equal, and in the second one we have a phase difference of phi. So when we have both the thetas to be equal, we get an isotropic nature, but when we have a phase difference phi, we have a maxima and a minima. So this calculation clearly indicates that if one is interested to find the maxima, that a configuration in which we need the maximum value of the absorption coefficient, then both the incoming photons should be cross polarized with respect to one another. Now, after doing these calculations, also from a theoretical point of view, it was also interesting to see that how is the behavior of the elastically scattered electrons interesting. So to do this, we study the Rayleigh scattering in twisted bilayer graphene. A very simple schematic description that we have a twisted bilayer graphene, we have an incident photon, we have an emitted photon, and there's a light matter interaction in the twisted bilayer graphene. Just to recall the directions, since it will be used in the subsequent slides, I am referring this matrix term as the optical matrix term. This stands for the valence band, V stands for the valence band, while C stands for the conduction band. This is my light matter interaction Hamiltonian, and when both the incoming and outgoing have the same direction, be it XX or YY, by X I mean it is along the zigzag edge of the graphene, by Y I mean it is along the armchair edge of the graphene. I call it as the parallel polarization case, since they both are parallel to one another, and when they have a phase difference of 90 degree, that is, the incident photon is along the zigzag edge while the emitted photon is along the armchair edge, I call it to be as the cross polarization configuration. The first thing that I am interested to see is how is the behavior of these optical matrix elements written on the top. How does this behavior change on including various effects like seen in the previous calculation, be it corrugation or doping. So just to mention there, the first matrix element stands for the incoming photon, while the second one is for the emitted photon. And we are considering the elastic scattering, so the electron gets excited from the initial to final some state and comes back to that state. So this is the case when my band structure is pristine. That means I haven't included any corrugation effect. These are the corresponding bands. So for model purpose, I have shown only 2 bands, but in actual calculation, all the bands have been considered, and the energy range depends upon the range in which I am interested in, which further depends upon the value of laser energy that we are varying. So the bands must be well converged within that energy region. Now when I include the corrugation effects, you see this orange hexagon is the Moiré brilliance zone, and these black dots, they represent the location of those wave vectors that is giving me the dominant contribution to the scattering process. That means the scattering, which I will show the corresponding plots, these are the wave vectors that will give me the maximum contribution. I include my corrugation effects, the location is slightly disturbed. On further including the doping effect, there is hardly any change in the location of the wave vectors. Similarly, in the cross-polarized configuration, again, this is the region in the pristine twisted bilayer graphene brilliance zone or the Moiré brilliance zone that is giving me the dominant contribution to the scattering process. And as these corrections are incorporated, this location of this wave vector slightly changes. Now, this is not the only part, again, to repeat, that has been included. This is just for the model purposes, because for this expression I have to choose 2 bands where I can show the demonstration. Similarly, for this magic angle also, I have showed that how the location of these wave vectors hardly change after adding other corrections. Only the correlation effect is playing the major role in altering the location of these dominant wave vectors. Okay, now coming to the quantity that we are interested is the behavior of the integrated Rayleigh intensity. So on the x-axis, we have in the first plot, on the x-axis we have a laser energy of the incident, of the scattered photon or the emitted photon, and on the y-axis we have the laser intensity, Rayleigh intensity. And for representation here, I have chosen only 2 twist angles, 2.5 degree and 3 degree, just to be clear about the figures. Now this is the case of the constant optical matrix elements. So this is a model case in which we have assumed that these matrix elements are not playing any role. That means we have turned them off or set it to be equal to 1. So what we see that this is the variation of the Rayleigh intensity. So we are getting a peak, we are studying the elastic scattering, so we are getting a peak at a certain energy value. And now the quantity that is physically measurable is the area under the curve, or we call it as the integrated Rayleigh intensity, that is plotted in the second figure, and this is shown for the variation for twist angle. So x-axis is the twist angle, while y-axis is my area under the curve. So I did this calculation for various twist angles, and this is the kind of behavior that we observe, that as we are reducing the twist angle, the magnitude of this integrated Rayleigh intensity is going higher and higher. Now the next step is to switch on the optical matrix elements. Again, there are 2 ways in which these optical matrix elements can be switched on. Like we have, first is the parallel case and second is the cross polarization case. So here I switch on in the first case, it's the parallel polarization. That means against the incoming and outgoing photons, they are aligned along the same polarization direction. And again the results are presented for different twist angles. So this is 3 degrees, 2.5. So as I am reducing the twist angle, the value or the magnitude of the Rayleigh intensity is continuously increasing. And again I have plotted the integrated Rayleigh intensity as a function of the twist angle in the corresponding plot. So what we see that for parallel polarization, the integrated Rayleigh intensity increases as the twist angle is decreasing. A similar behavior like this one, that means it is showing a similar behavior as if the optical matrix elements were switched off. Only when we switch on, we are again getting something like this. Now when we set the polarization direction of the incoming and the emitted photon cross polarized with respect to each other, that means something like this. say this is the red one is for incoming and the green one is for outgoing. So what we observed that a hockey stick like curve, that means this nature of the behavior or the nature of the integrated Rayleigh intensity is exactly opposite to what we have observed in the case of parallel polarization, and the reason lies because we now have interference effects which are mediated by these incoming and outgoing matrix elements, which were absent when I considered that both the photons are polarized along the same direction. So these results confirm the interference effects which were mediated by the optical matrix elements, and of course these are polarization controlled because this is only demonstrated when we switch on the polarization or we change the polarization between the incoming and outgoing photons. Now it's important to see that is there any change with respect to graphene or it's showing the similar behavior. So to do this, we define a quantity Ra, which I refer to as integrated Rayleigh intensity. It's a ratio of the integrated Rayleigh intensity for parallel and cross polarization. And what I see that I first comparing with SLG and BLG, single layer and bilayer graphene. So the pink curve is for the parallel polarization and the blue curve is for the cross polarization. So one can see that this blue curve, the area under the blue curve will be 1/3 of the area under the pink curve. But when I plot the similar ratio Ra for twisted bilayer graphene, I see that there is a strong enhancement. So firstly, these different colors, they represent different incoming laser energies. So there is a strong enhancement with respect to single layer or bilayer graphene. So in these systems, the ratio was 3.3, which is achieved for higher twist angles. Yeah, for higher twist angles, this ratio is 3.3 because the interlayer coupling is weakening. But as the twist angle is reduced, the ratio is strongly enhanced. Now what can be the experimental relevance? So we have the laser energy, this quantity is easily measurable. So when one can vary the twist angle, say from 0.6 to 4 degree, we see that each angle is characterized by a series of peaks which is unique in itself, and this can be used as a fingerprint to identify the twist angles. Again, we had to study that how it is changing with respect to polarization. So we have two cases. First, phi is 0, that means there is no phase difference, or we have a phase difference of say 90 degree between the incoming and emitted photons, and we see that integrated Rayleigh exhibits isotropic behavior. That is, it is independent of the phase difference between the two photons. Yeah, to summarize, we have the demonstration of alpha 1, the absorption coefficient with respect to laser energy in case of both single photon and two photons, and we have seen that to achieve the maximum two photon absorption, one needs to check that both the photons have zero phase difference between them. And again, the evolution of this quantity Ra with respect to the laser energy for different values of twist angles give me an experimental signature for the prevailing angle. Yeah, that's all. Thank you.
Questions, please.
So you showed the data for this decreasing of the intensity of the absorption for different, this one. What happens below 2.5 degrees? It's a is it a monotonic behavior or anything?
Below 2.5 degrees. No, so it will continuously keep on increasing. For just for representation, I
see. So nothing special happens.
No, not because the reason is that we are interested in the higher bands.
Very high, which are above 0.5.
Yeah, because we are interested in optical laser energy.
I see.
Yeah.
So I have a quick question about this. So the change in the optical absorption is pretty small here, right? I mean, it's
right in the one photon. It's
in the one photon, it's very small. But when the two photon, you showed a very large difference in the.
No, even in the two photon, if I have that slide where I can show you the comparison. I don't know if I have that slide, but even in the two photon case, that it is twice that of bilayer and a notable increase with respect to single layer. Not a very giant enhancement.
Not a very giant. Yeah. Okay, thanks.
I mean, since you have the framework, would be interesting to see what happens in terahertz for this kind of absorption. If there is any way to sort by terahertz far field measurements, twisted bilayer around certainly less than 2 degrees. So
in that case, it's not that challenging, because we already if you want to study these kind of calculations, that primarily requires the band structure, but that should be well converged in the region that you are trying to study. So if I have a well converged band structure, that is the only thing that is a bit complicated to achieve. So in that case, it can be studied.
Otherwise, I think we'll thank the speaker.
Okay, so we shall be starting this afternoon session, and this session will be chaired by Professor Ajit Balaram from IMSC Chennai.
Okay, so first off we have Manish Jain from ISC, and he'll tell us about phonons in Moiré materials.
Okay, thank you for showing up after lunch. I hope to give you a story so that doesn't make you all sleep during the talk, but I'll understand completely if you do. So, I'll be talking about phonons in Moiré materials. Okay, so here's the outline of the talk. I'll first talk about, I'm sorry, this is looking very low resolution. It looks fine on the screen. It somehow doesn't show up. The fonts are not showing up very well over here. In any case, so I'll first talk about some ideas as to why one should care about phonons in these Moiré materials.
No, but just 1 minute.
Then I'll talk about low frequency phonons in transition metal dichalcogenide bilayers. I don't think anybody has talked about transition metal dichalcogenide bilayers so far. Then I'll talk about Raman active G modes, and then the Raman line with twisted bilayer graphene. Okay, so you've heard a lot of discussion in the talks in the morning before lunch about flat bands and strongly correlated physics that comes about because of the fact that they are flat bands. And now these flat bands could be in twisted bilayer graphene, which could be because of the magic angle at twisted bilayer graphene. But you also had other things which Avik was talking about, where the bands weren't completely flat, but there was some very interesting physics that was happening. But these are all electronic properties that he was talking about. Okay, but it turns out these Moiré materials also have some other very interesting physics. So it turns out that there is also this very interesting thing about if you measure the friction in these materials as a function of rotation angle, you find that this is almost no friction from, let's say, from about this angle to this angle. These materials are actually just sliding freely with respect to one another, right? And the other thing is, and which a lot of speakers, Bandar and Avik alluded to, was the fact that these materials have these domain wall networks, right? So the point is that once you put two materials on top of one another, you actually end up forming these domain wall networks. And if this is I think an STM micrograph, or I don't quite know what is the image. This is probably not an STM. But some other picture, I have no idea how it was taken, but it shows you these very nice domain wall networks which are colored differently, these triangular networks which are formed, which show you that these materials actually, once they reconstruct, they have these hexagonal symmetry. So I'll be talking a little bit about where do these things come from and what is the underlying physics of all of this. And essentially the main idea of the talk is to talk about how does twisting affect phonons? Okay, that's the main idea of the talk. Okay, I should stop using the pointer. Okay, so transition metal dichalcogenides are much like graphene. They form a hexagonal the unit cell is hexagonal, or whatever, 120 degree angle between the lattice vectors. So it's much like that, except that instead of having a single layer, just like in graphene and hexagonal boron nitride, you actually have 3 layers which form the structure, right? So you have, an example of this would be molybdenum disulfide. So you have 2 sulfur atoms, right, and a molybdenum layer in between, and they form exactly the same kind of structure that you form in graphene. And so just like you could actually exfoliate graphene, you can also exfoliate these layers, and you can actually make twisted heterostructures out of these. Unlike graphene, here when people talk about graphene, they talk about 0 degrees twist angle. Mandar alluded to the fact that you could actually form something which is at anti-parallel, which is at 180 degrees twist angle, and he said it might have different topological properties. In these materials, because of the fact that you have a sublattice symmetry breaking, you always have the angles near 0 degrees. So for example, this is around 2.9 degree angle, twist angle. So you have some stackings, high symmetry stackings that show up in the structure. Near 60 degrees, a different set of high symmetry stackings show up in the structure. Okay, so this actually leads to slightly different kind of physics than from graphene based heterostructures. And also, this is not a semi-metal. In the single layer is not a semi-metal, it is actually gapped. Okay, so therefore it is not, it's in the valence band, or if you look at the electronic properties, people just dope these systems and look at what is the interesting physics that will come out of it, or do optics in this, and so on and so forth. Okay, so if I look at, if I were to just ask you the following question, if I take these two layers and I put one on top of another, and then I'm a theorist, so everything is in a computer, right? So and I let the system relax, what would happen, right? So what happens is, what is being plotted here is the distance between the 2 layers. So I have 2 layers, right? One I have put on top of the other, and I have let the system relax. The system has formed these Moiré patterns, right? But if I look at the distance between the 2 layers, you will find that the distance between the 2 layers is not constant everywhere. Okay, it actually is. It is changing as a function of where you are, which kind of stackings that you have, right? And what is interesting is that when you go from, let's say, a higher angle down to a lower angle, all that is happening is that these high symmetry stackings, which is this AA stacking, which I had shown, there's a stacking called A, that's the high energy stacking. It is also an unstable stacking that you wouldn't be able to realize if you were to form 2 layers and you said, okay, that's actually unstable. It'll actually be, it'll just deform from it. It just keeps going further and further apart, right? That's essentially all that is happening. The other thing, which I don't know how well you can see it, but you can see these dark blue triangles over here, right? These dark blue triangles are nothing but this highest, these stackings, the AB and the BA stacking, these are the most stable stackings in the system, right? And if you remember, AB and BA are exactly the same stacking, except you're looking at it from the top or from the bottom. So it doesn't really care, right? So as a result, what happens is, the energy of both of these stackings is exactly the same. They both show up in the structure, but they are separated by this domain wall, right? So the thing that is happening is, as the angle is reducing, right, these red dots, which are the high energy stackings, are becoming further and further apart, and these domain walls, essentially you are forming a network of these domain walls with AB and BA stacking over here, right? This is what Disha was referring to as the reconstruction, as the Moiré reconstruction that happens inside the system. Yeah. So this actually has some very interesting consequences. That as we
hello.
discussed. Yeah.
Just I had a doubt. Yeah.
Yeah.
So are you only talking about commensurate angles?
This is all. I'm only talking about commensurate angles because all the calculations that I'm doing are atomistic and can only be done with commensurate angles.
So while relaxation, it can be. The angle can it change?
No, it is fixed by construction.
It's fixed. Okay, thank you.
Yeah. Now, if you go to an angle near 60 degrees, which is very different from what can happen, let's say, in graphene, something very interesting happens. Here, what happens at 60 degrees, the stackings that you have, this is the unstable stacking, but you have 2 stable stackings which are not the same. There, AB and BA were exactly the same. Here, they are not. And essentially, what that leads to is that they have different areas. So because the stacking energies are different, the systems relax in such a way that the domain wall network still forms, but the domain walls are no longer straight, but they are actually curved. And this is what is called as a rouleau triangle. And if you have some time, you should actually look at these rouleau triangles. They have those fantastic properties. People make cycle wheels out of them, and all kinds of interesting things are done with them. But essentially, you form these very interesting networks where one stacking, which is the most stable one, in this case the 2H stacking, is the one that is growing at the expense of the other one as well, because it's not as stable as the 2H one. Yeah, you can't get rid of this one because it's topologically you can't. This it has to be there. You cannot get rid of it, but its area can become as small as possible, and it stops when there's an energy associated with this line, which actually prevents it from going all the way. Okay, this is true not just in MOS2 or WS2 on TMDCs, which is where I'm showing this example from. Anywhere you have a sublattice symmetry breaking, this will be true. This will also be true, for example, in boron nitride systems, right? Or also true if you look at tri-layer graphene, ABA stackings and all those kinds of systems, you also start seeing such things. Okay, so the thing that that was about the structure of how the systems relax and so on. So the thing is, we are interested in calculating phonons in this system. Yeah.
So if I look at graphene on top of boron nitride, where by proximity I'm breaking the sublattice symmetry.
Right.
Should I see?
Yeah, you should see something about the domain wall bending there as well. You will see very similar things, because the stacking in one region and the other will not be exactly the same. So I said that very confidently, and now I'm not. I think you'll see it. Yeah. Okay. So the thing is, so what we would like to do is we'd like to calculate phonons on these systems. And phonons, we have to do everything atomistically. But to calculate phonons in these systems, we have to first construct a structure, and we are always going to construct a commensurate superlattice. In principle, the commensurate superlattices are a set of measure 0 because of most of the numbers are. Most of the angles will be incommensurate, but that's what we can study, so that's what we'll study, and hopefully nothing crucially depends on it. Okay, it more or less doesn't, except for some things which I'll talk about later. We will be doing small twist angles, so the number of atoms typically will be thousands, right? So if you want to do any calculations, first principles calculations like density functional theory and so on and so forth become extremely difficult. Right? It has been done, it can be done, but it is very hard to do them on a regular basis. Okay. So what we will do instead is to figure out how to do phonons in these systems. We will actually go to an atomistic description and integrate all the electrons, which is a fancy way of saying that we will actually go to force fields. Right. So we'll parameterize the interaction between the atoms from DFT and then go all the way, and that parameterization has to be done a little carefully. It can be done, and we've done that for TMDCs and it works out reasonably well. But even so, if you think about it, if you have 10,000, 20,000 atoms in your system, the dynamical matrix, every atom has 3 degrees of freedom. It's 2D embedded in 3D space, so you have 3 degrees of freedom. You end up with a large matrix that you need to diagonalize. First construct and then diagonalize. I mean, if you have 10,000 atoms, that's 30,000 by 30,000 matrix, right? So we have actually written a code called PARFORM, stands for Parallel Phonon Calculator for Moiré Systems, which enables you to actually do all of these things, to calculate the phonons in these systems. Okay. Let's say you went ahead and did this calculation, right? You went through all the trouble and you did this 10,000 atom calculation. This is, I'm showing you for a real system. For a real system, which is 2 degrees twisted bilayer WSE2, tungsten diselenide. This is what you get. Okay. Now I don't know about you, but this is spaghetti, right? Good to eat, but it doesn't talk to me. Right? I don't know what it means, right? You do this phonons, you have so many lines, there's so many phonons. What am I supposed to make out of it? So one way that we have thought about in making sense out of this is to actually, so let me just point out, this would not be just because I did 2 degrees, this is nothing special about 2 degrees. If I have large number of atoms, I'll have 3n modes, right? If I have n atoms. So there'll be some acoustic modes, the rest will be optical. That's how you'd expect in a standard crystal. I can't, when people talk about phonons in a standard unit cell, the number of phonons is very small. You're talking about, you use group theory to characterize, okay, this one is Raman active, this one is not Raman active, and so on and so forth, right? I can't do any of this. I have 30,000 phonons here, right? None of that is going to work. But on the other hand, you can ask the following question. How are these phonons really different from the phonons that you got from the unit cell in the first place? And one simple way to think about this is to argue that, look, when you increase your length scale, all you did is you folded your bands. That's what you learn in condensed matter 1, right? As you increase, you double the cell size, phonon bands fold. That's essentially what is happening. It's happening multiple times over here. That's one aspect of it. But another aspect of it is that many phonons are mixing together because there's actually a potential between them. There's an additional potential, which is the Moiré potential, which is actually mixing because for the phonons as well. Okay. So in order to make any connection with experiment, what we are going to do is we know that the original unit cell phonon, which one was Raman active, right? So what we'll do is we'll project the phonons that we get onto the original unit cell phonon and then try to see if we can learn something from here. Now you can say, look, this is really cheating. How do you know that that is the right way to look at this? And you're right. The correct thing to do would be to calculate Raman tensors if you want to compare to Raman experiments. But that's too hard. So this is sort of a poor man's way of getting around this problem. Yeah? Okay. So that's sort of the general scheme of things that we'll follow in all these three things that I'll talk about. So now let me talk about low frequency phonons in transitional metal dichalcogranite bilayers. So what we know from standard monolayer calculations in any system actually, it is 2D embedded in 3D space. So basically you have the longitudinal acoustic, you have the transverse acoustic, and then you have these ZA phonons as they're called, which are nothing but your drum modes, right? If I give you a sheet of paper, it can flutter, right? That is, they're called flexural phonons, which are these quadratic modes that you see over here. Okay, you bring another layer close to it. Now the whole system has, one translation, two translation, and the third is a drum mode, which are these three modes. And then the other set of modes are basically gapped out. These are basically the layer breathing modes. So it's relative translation with respect to each other, right? So originally this could move this way, and drum mode, right? This could move this way, and had a drum mode. But when I put them together, both can move this way, and the drum mode. And then I have relative motions, this, and the relative drum mode of the two, which is basically this, which is the breathing mode. So essentially what you end up getting, you get these shear modes and you get these breathing modes. In the shear modes, the two layers are sort of moving opposite to each other, and in the breathing mode, they're moving away from each other, like this, close together and so on. Yeah? Okay. So what we're going to do is we're going to calculate the phonon spectrum, and we're going to project onto the shear mode and onto the breathing modes, and ask what does it look like as a function of angle. So what I've plotted here is the projection weights as a function of angle. So this is this is frequency in centimeter inverse as a function of angle. This is twist angle. This is done for MOSE2. The stars show you when I project it onto the shear modes, and the dots show you when I project onto the breathing modes. And here's the first very interesting thing that you notice. Normally when we teach condensed matter, we tell everybody there are 3 acoustic modes and everything else is optical. Yeah? Besides the 3 acoustic modes, I am finding that the shear modes here are also zero energy. This is weird, right? This is very weird. Okay, so and something very interesting is happening. As the angle reduces, these shear modes, which are zero in energy, at some point they become finite in energy and they become gapped out. Okay, so this is the shear modes. The layer breathing modes, on the other hand, sort of come down, they sort of split, and all kinds of weird things are happening. Yeah, so you start asking yourself, what is happening? So I divided this region into region 1, region 2, and region 3, and these are sort of these ultra soft shear modes are showing up.
Shear
is the relative motion. relative motion of these two.
And layer breathing are the ones.
Are the ones which are these ones, yeah. Now you can say, look, I mean, maybe your calculation is all garbage. Maybe it's just an artifact. For all you know. But it turns out, that's not the case, because we can actually compare the values of the layer breathing and shear modes when they are finite, when people can actually measure them. And it turns out that our numbers, the green here are experiments from this experiment, from this paper, and the red are our calculations, and they're pretty good. They're in pretty reasonable agreement with one another, right? I mean, given that this is 35 centimeter inverse is a scale. So the question that you can ask is, what is going on? And the way to understand this is to realize that there is actually another set of zero energy modes which can come out. These are Goldstone-like modes, and I'll tell you why I call them Goldstone-like modes, which are called phasons. Okay, and the idea is the following: if I give you two incommensurate systems, two systems which are absolutely incommensurate, there's no repetition of stacking. It doesn't repeat. There's no unit cell over here, right? And I shift one with respect to the other. What happens? How much is the energy cost? I look at the stackings here. I get all stackings. I move this. It's still incommensurate. So I still have all the stackings. Which means what happened? What happened to this movement? It was zero energy, right? So I actually have two extra zero energy modes in the system, and these modes are actually called phasons. Okay, this is actually known in a long time. This has been known for a while. If you read Chaikin and Lubensky, you will actually see this. This is all interacting. This is phonons, right? Interaction has nothing to do with interaction. This is a very physical argument. Is basically related to the fact that if I have two incommensurate systems, I shift. I don't pay any cost.
There is nothing like mode softening or anything like that.
Mode softening of what?
Of some type of phonon mode.
No, these are all shear modes. I'm giving you the energy of the shear mode, right? Relative energy, relative motion doesn't cost me anything. Yeah. As the angle reduces, what one finds is that these shear modes start localizing. And if I can actually show that picture, we had this. There it is. You can look at this. And I don't know whether you can see it or not. So I've plotted the eigenvector of this shear mode at a small angle. I don't know if you can see this, but if I follow my hand, this is basically what is happening is this Moiré spot is actually moving left and right, right? So there is actually an effective, the Moiré lattice of these AA regions is acting as if they were atoms, and there's an acoustic mode of that, and that is what is becoming of my shear mode as the angle becomes smaller. And that's, wait, where did my presentation go? Control L, right?
Yeah.
Yeah. So that's essentially what is happening, and that's where the zero energy mode is actually becoming finite. And this actually has some very interesting consequences on the super lubricity, as I had shown you before, right? So what happens is, when these shear modes exist at zero energy, it doesn't cost me anything to slide the two layers with respect to one another when they are at zero energy. But the moment these become, as the angle becomes smaller, and I start developing these high energy stacking regions, right? They sort of act like pinning spots, because there the mode has to be gapped out, and there if I, in the AB layer, if I shift one with respect to the other, in the high symmetry stacking, it costs me energy. And that's essentially why you actually start seeing this very interesting behavior, and this is sort of, so at low angle, at high angles, you should actually have frictionless sliding, right? And this actually you can see if you plot, anyway. So this is something that you can see. You can actually see the ultra soft shear mode splits into two, and that is basically responsible for the superlubric behavior, and it goes from superlubric to pinning behavior as the angle becomes smaller. Okay, and this has nothing to do with. This really has nothing to do with the MOS2 per se or any such thing. This would be true for any, even for twisted bilayer graphene, you should see something very similar. Okay, so next let me move to Raman active G modes in twisted bilayer tungsten diselenide. This work is actually done in collaboration with Anando and Ajay. Essentially what they saw in the lab is that they were able to measure as a function of angle the Raman frequency for twisted bilayer tungsten diselenide, and they found something very interesting, which is that at around 2 degrees you saw a splitting increase in the peaks. This is the Raman mode. This is the G mode in this is the G mode frequency of twisted tungsten diselenide. And as a function of angle, you saw a splitting between the modes. Let me show this more easily. So if you take all these spectra that they have as a function of angle, they've gone from 0 to 7 degrees, and you fit this with the Lorentzians, and you see where the peak of the Lorentzian is, right? You will find that there are two peaks that you need to split to understand the data, and the two peaks, the splitting of the two peaks is plotted here. So it peaks at around the splitting of the peaks at around 2 degrees, right? So the question that we started asking ourselves is, why is this peaking at 2 degrees, and what is going on over here? What is the physics of all of this that is happening here? So the first question is, how do I even start thinking about this problem? And for us, the experimentalists tell us this is the Raman G mode, right? There is no single mode in my calculation of 30,000 atoms which I can identify as a Raman G mode. So what am I supposed to do, right? So what we came up with is that we know what the G mode looks like in a bilayer, right? So what we will do is we will take this mode and we will replicate it in all the atoms inside my Moiré cell in both the layers, and I'll combine them and I'll call that as my G-like mode, right? Hopefully this is the mode that is Raman active, and maybe by looking at this we can understand what is actually happening in their measurement. The interesting thing here is that there are, as I point out, there are different regions, stacking regions in this relaxed landscape. There is the AA region. These boundaries they call as the SP region. I don't know what the SP stands for, but do you remember what SP stands for? I don't know what SP stands for. These are domain walls, okay? And the rest is AB and BA.
Those are small AA one, right? This is SP.
SP is sort of the domain wall.
But these are some part is AA kind of.
Some, I don't know. It's a place where I don't know where the nomenclature SP came from. It suddenly occurred to me. I don't know where that comes from, but okay. So now what we're going to do is we're going to take our phonon modes at the gamma point, right? Because eventually Raman only measures the gamma point. We're going to project it onto all of these regions and ask, is that the reason for seeing the splitting in these modes? Why, Raman mode in the ideal bilayer is a single frequency. We see some splitting of the peaks. Where does it come from? Our idea was that maybe it comes from different parts of the region, different parts of this Moiré landscape are giving you different Raman frequency of the G modes, and that is where it is coming from. So when we do the projection, we see something like this. It's a messy plot, made more messier by the projector, but okay. What you see is that you will see that there is actually a splitting here that we are seeing. Now, namely the G peak, which was nominally the G peak. When I do the projection, I see a large number of weights. What I've plotted is the projection weight. You can see that there's a large number of there's a large spread in the weights, right? The AA region hardly contributes, which is not surprising because the AA region is a very small region anyway. So on a per atom basis, maybe it will contribute, but otherwise it doesn't contribute. But you can see that the peaks in this are coming from SP and AB regions, right? So indeed, it is as if the entire thing is sort of SP is contributing these peaks, and this is contributing a different peak, and that is where the splitting is coming from. So then we started looking at, we have done this as a function of angle, so we started looking at how does the splitting look like when we fit our data to Lorentzians, and we find that we are actually able to explain the experiment reasonably well. Okay, we also see around 2 to 3 degrees the splitting is larger, then it goes down, and which is somewhat like what the experiment is actually also seeing. So this is basically spatially coming from different regions. That's the reason why you're seeing the split. Okay. Lastly, let me talk about the Raman line width of the G mode in twisted bilayer graphene. So, there's something very interesting that happens in twisted bilayer graphene near the magic angle. We've all heard about the electronic physics, but it is interesting from another perspective, which is that what you find is, if you look at, let's say, AB stacked graphene, the Raman line width is around 15 centimeter inverse, right? But in twisted bilayer, the Raman line width is about 25 centimeter inverse. Okay, so the line width has increased a lot. Okay, now you might argue, look, there are many modes, so maybe that's how it has increased. But we'd like to understand, where is this coming from? Okay, at a large angle, this looks more or less like the AB stacked. The line width comes down again. So what we wanted to do was calculate the line widths, the Raman line widths, so the line widths of the phonons in twisted bilayer graphene samples. Calculated. So now, of course, the line width can be given as a sum of the electron phonon line width, the phonon line width, and the disorder line width. Okay, we know nothing about the disorder, so we'll have the ostrich solution. You know what the ostrich solution is? If there's a problem, if there exists a problem, if I close my eyes, the problem doesn't exist, right? That is the ostrich solution to any problem. That's what we're going to do. We're going to say, I don't know anything about it, but I don't know how to model it, so I'm not going to worry about it. Let's hope that experiments, that when they do it, this is all very good, so this is not an issue, right? Probably not true, but okay, let's just see what we can do even without it, right? So now the question is, we got rid of all the electrons to begin with. That's how we did all the phonons, right? But now I want the electron phonon coupling in this material. So I got rid of the electrons. So how am I going to get the electron phonon coupling? So for that, what we do is we actually go back and do an atomistic tight binding, where we make our tight binding hopping parameters distance dependent. Okay? The phonons are done in the standard way. We also use exactly the same paper that Disha talked about with Zachary, with Goodwin for doing the Hartree approximation for the doping dependence and so on. And we use standard classical force fields for the phonons. So we're going to do tight binding for the electrons. We're going to do standard interatomic potentials for the phonons. But because we make our tight binding parameters distance dependent, we'll be able to calculate electron phonon coupling. So how do we do that? So the electron phonon coupling, if you write out in the tight binding approximation, can be written in terms of the derivative of the hopping parameter and the phonon length, the phonon eigenvector and electronic eigenvectors. All of this we can compute. Okay. So based on this, we can actually calculate the electron phonon coupling, and once we have the electron phonon coupling, we can calculate the electron phonon line width. Just a standard Mithgel formula, right? So all the quantities that we need are the electronic band spectrum, the phononic band spectrum, and the derivative of the hopping parameter, which we can do very easily. Okay. So based on this, we also have to define the G mode. We define it exactly in the same way as we did for twisted WSE2. So I'm not going to spend any time on this. But now we have another thing to worry about. Huh?
These are all for TVLG.
This is for TVLG, yeah. So here now we have to worry about one more aspect. For every phonon, I'll get a line width, right? So to get so for every phonon, I'll get a line width. But to get the line width of the bilayer G-like mode, we're going to construct a spectral function where we essentially take a Lorentzian for every one of these line widths, and whatever is the weight that comes about from overlapping this with the eigenmode, we're going to just use that weight and weight it in this way. So what we're going to get is nothing related to the Raman spectrum. Our intensities have nothing to do with the Raman spectrum, right? But hopefully our line widths will still turn out okay. That's the hope. Okay. So when we do this, we find that when you project it, we actually find that there's a large variation in the frequencies for the bilayer G-like mode, and if you take all of this and construct the spectral function and you plot it out and you fit it, you will see that you need two Lorentzians to fit it. Okay. We call this EG plus and EG minus, just like we did in twisted WSE2, right? So far, when we had done this, people hadn't seen two peaks, so we were a little nervous, and I'll show you that what we are doing is not hallucination. Actually, Anando's lab measured this and they actually saw 2 peaks. So we feel okay. So you take this, the upper peak has some line, you can actually do this as a function of doping, the line width as a function of doping you can get, and you can get for the lower one as also line width as a function of doping. You can also actually do the phonon-phonon line widths. Because we have interatomic force fields, we can actually calculate the velocity autocorrelation function, right? If you do a mode projected velocity autocorrelation function and you Fourier transform it, the velocity autocorrelation function, if you Fourier transform, you will get the phonon density of states. If I do the mode projected velocity autocorrelation and Fourier transform, then I should get the corresponding line width that comes about from the phonon-phonon interaction. So that's essentially what we use. So based on this, you can actually find out how, based on temperature, how the lines will move, how the Raman lines will move, and what the line widths corresponding to this will be. And just to show that this is not hallucination, this is actually at around 1 degrees, which is where we did all the calculations. You find that even in experiment, actually Anando and Darshit found that there's actually a splitting of the peaks, which is much like what we had predicted. Okay, so to conclude, I have shown you that phonons in these Moiré systems can get significantly modified or hybridized due to interlayer interactions. Low frequency phonons show some characteristics of incommensurate systems. So the difference between commensurate and incommensurate here is that if the system is commensurate, the phasons are gapped out, but the gapping there is of the order of 1 or 2 centimeter inverse. Nobody can actually measure that, at least with the Raman kind of measurements that people do, because that's within their laser line width. In the truly incommensurate systems, this would be gapless and these would be Goldstone modes. We also showed how high frequency Raman active phonon modes in WSE2 split, and that's because of localization in different high symmetry stackings. And we calculated line widths and for G modes, and we find that near the magic angle there's an increase, but we also find it splits into 2. So there are multiple peaks inside there, which is causing the line width to increase. So with that, let me just acknowledge the people who actually did the work. Most of the work that I talked about here was done by Shinjan and Indrajit, both of whom are former students now. And I have long-standing collaborations with Prabal and HR Krishnamurti, and the money for this computational resources, because these require a significant amount of resources, came from National Supercomputing Mission, and all the calculations were run in SERC, in ISC. Thank you.
Questions? Avi.
Manish, the question is, see, I know that in graphene, I can also have splitting and redshift of these Raman peaks when I have a non-uniform strain.
Yes.
So how do I deconvolute these? I mean, do you see a shift of the peaks?
No. So we have not. See, the calculation gives me the splits correctly. You notice I didn't put experiment and theory on the same plot. I plotted the differences on the same plot. That's because the force fields are actually not very good. So we get that qualitatively the right physics, but quantitatively our numbers are not exactly the same as experiment. So it's very hard for me to say what will happen because of strain. Indeed, strain will cause these to shift, but this is without any strain. Because of Moiré reconstruction, this is happening.
Okay. So the follow-up question now, because I have this lattice mismatch, I will have inhomogeneous strain in the system.
Right. So it will lead to another inhomogeneous broadening, which is something that I have
to compare.
It is not. Right now it is not possible to compare. Yeah. But there will be some contribution from the inhomogeneous broadening as well. Yeah, absolutely.
So Manish, this phase-on mode.
Yeah.
So this Goldstone-like mode, what is the consequences in transport? What do you expect to see?
So that's. I think Shahal might talk about this in his. If he talks about this part and not the newer stuff that he actually sees these modes. He sees them at the zone boundary.
But those are not exactly zero energies. They still
in
find.
In this case, see, there's a dispersion, right? So at Q equal to 0, it is 0 energy, but it disperses, and he sees it at actually the zone boundary. It should have some consequences on transport, right? Absolutely. In fact, I think Shankar Das Sharma has a paper where he talks about how the transport will get modified because of these phase-on modes. I'm not quite sure exactly how it works out, but something.
So my question related to electron-phonon coupling.
Yeah.
Usually electron-phonon coupling gives rise to
asymmetry of the existing phonon peak,
Mhm.
not really the separated phonon peak.
The splitting, you mean?
Yeah, splitting.
Yeah.
So what is your take on this?
So the thing is, here it is not just electron-phonon coupling. It is also the fact that we have, the system is inhomogeneous. The unit cell is very large. There is different stackings present in the system. So that is convoluted with the fact that you have a broadening of the peak because of electron-phonon. So, there are many phonon modes. Just like in twisted WSE2, we found that this split because of different regions. I didn't talk about it over here, but we see that similar things happen over here. So it is actually both things are happening at the same time.
So if you dope or undope, so you should be able to see that.
So we did do the calculations for doped system. Let me see if I can find that. So as a function of doping, this is we actually see the change in the line width. All these noise that you see, actually we can relate it to the fact that the joint density of states just matches or doesn't match, those kind of things. So the line width is actually very strange, behaving in very strange ways over here.
And another question is the splitting is about 1 to 2 centimeter inverse.
That's correct.
It's a very low energy scale.
They measure it, right?
Splitting 1 to 2 centimeters.
Measure.
So you should still see some transport behavior or any impact of this splitting on any other experiments.
On transport, I don't know, but I think you will see. I mean, the splitting can be measured in Raman.
Yeah, that is.
That's essentially all. What its consequences will be, I'm not. Yeah, that's a good question. I don't quite know what the consequence will be. Yeah.
Excuse me. I hope my question is related of the two faculty things. The layer breathing mode you mentioned, no?
Yeah.
It's yes or no question. It will affect the thermal conductivity.
It does. Actually, we calculated the specific heat, and it should also affect the. It affects the specific heat, right? And it affects the density of states. So anything that you want with respect to density of states, everything will get affected. Right? The layer breathing mode will actually have a peak in the. It has a Van Hoff singularity. Because if you look at this, right, even in the bilayer, right, if you look at the, even in the bilayer, it's right at the beginning, I'm sorry about that. Even at the bilayer, right, this is a Van Hoff singularity, right, in the density of states, when you see it, you will see a Van Hoff singularity. So it does affect everything. Specific heat, it will affect, everything, thermal power, everything. Yeah.
Anything else? Okay. Can you come to mic?
Hi. So for the case of transition dichalcogenides in the 3D transition dichalcogenides, which have very very localized wave functions. So would there be any difference?
So 3D. So typically people will do 4D and 5D. MOS2 and WS2. If you go above on the periodic table, it is titanium. I don't think titanium forms selenide or sulfide. I'm sure some chemist can correct me if I'm wrong. It does form. Huh? Okay, so I don't know whether it forms a single layer of that or whether it can be exfoliated or not. But having said that, it will lead to some differences in the electronic structure. Right? We were looking at mostly at the phonons. The phonons, usually just based on the square root of the mass, they'll be higher.
And also the coupling was the derivative of the hopping.
So there, electron-phonon coupling, it will definitely get affected. Yeah. That depends on the details of the band structure as well. Yeah, absolutely.
Thank you, sir.
Go ahead. One second, there's a question.
So all these calculations were done at which temperature? Okay.
So different temperatures. The electronic calculations are always done at T equal to 0. But the
because in TMDs, what you see in most of the TMDs, there is a CDW transition at lower temperature. So that will also affect a phonon dispersion and all. So the phonon mods will get.
So which TMDs are you talking about?
Yeah, like
tantalum diselenide. Those systems have.
Yeah.
But those are different. See, this is This is tungsten, right? Not tantalum.
No, if we
that is D plus. That is actually this is D4 system. That is actually D5 system. So there is one extra electron, and that leads to the electronic
instability.
Instabilities in that system.
NBSE2.
NBSE2, which is actually below that, the same. Yeah.
Okay, so we are done. So let's thank Manish. Yeah, so that is it.
Thank you.
Ananya? So then I'll let you know 30 minutes. So then you'll have 5 minutes.
35 plus 5?
35 plus 5. So I will let you know at 30 minutes. So you know 5 minutes are left for you.
You can copy so we can plug this again with this pointer.
We have to copy.
Okay, next we have Anindya Das from IISc, and he'll tell us about thermopower probing the local movements in magic angle twisting.
If I press this, is it?
This will
Okay.
Twist.
Go ahead.
Okay, thanks, Ajit. First of all, I would like to thank. Can you hear me from the back? Yeah. I'm feeling so sleepy. I hope I'll be able to finish this talk. Thanks to the organizer for inviting me, and particularly I'll thank Shankar Kuda for this very nice meeting. So what I'll be talking about, though I have given this talk several places, many of you might have listened this talk. I'll try to keep it simple so the students can learn something from this talk. So I'll be basically focusing this thermopower. Do you have a stick here? No, stick is not allowed. Thermopower probing the local moments in magic angle twisted bilayer. Which this pointer is, there's a time delay, so it is synchronized. So what you see in this picture, that the twist, which will come in a moment, twisted bilayer, but there are some fancy picture. What you see, these are sort of moments, or something has some sort of angular momentum, like in this case either spin or this thing, and they are localized. So that's the meaning. And what we are going to show, that how can global transport like thermopower can probe these local moments in this kind of systems. So the way I have designed this talk, then I'll give you some, what is this twisted bilayer graphene, what are the experiments going on, and how the thermopower can probe, particularly this local moment physics in these systems. So the twisted bilayer, I think today, probably since morning, there are several talks we have heard about it. And Mandar, Abhik and Manish, and so this several talks, and we learned about these systems. So as the name suggests, so there are two graphene sheets, and you have a relative angle between them, which is called twist angle. And once you have that, you can see there are new structures forms, which is called super lattice or artificial lattice. And because of that, this is a real space picture. So if you go to the now reciprocal space, we have original two graphene sheet, which are like this blue and red, Brillouin zone. Now we have a new mini Brillouin zone forms in the systems. And there are a few things to be noticed, and as you can see, the superlattice size depend on the twist angles. For example, 1.1 degree, the Moiré wavelength is around 12 nanometer. And further, these are the numbers I'm going to use, that this, in a condensed matter physics, we talk about a band, and you can ask how many electrons band can allow to fill. So for example, then the answer is the number of unit cell is basically determines your number of electrons. In other words, for example, in a conventional band, if you have 2 electrons per unit cell in a real space, you fill the band. In this case, not only spin, there are other degrees of freedom. So for example, there are these are K values, top and bottom bilayer, top and bottom layer graphene. These are K prime value, top and bottom. So you can see there are values and the layer degrees of freedom. So eventually there are 8 flavors comes in the systems, and so total 8 electrons required to fill a unit cell in real space. So this is required, and this nomenclature I will be using throughout my talk. So the important question which I showed here, 1.1 degree. So the point is why 1.1 degree is very special, because that's sort of known as called magic angle in this system. It turns out in that particular angle, you can show also very intuitively. So you can, what is shown here, that there are 2 graphene linear dispersion. We know the graphene has this linear dispersions, and because the twist angle, they are intersecting at some point, some energies. And we know once they intersect, they will hybridize, the energy will hybridize, and they will make a new structures. And one can show very intuitively that 1.1 degree, the separation is such that the hopping energy between the top and bottom layer is such that they hybridize such a way, they will make a unique band structures. So this was like your mother graphene, let's call mother graphene band structure. This is the band structure of the new system of the twisted bilayer, and you can see they are quite distinct from the parent system. And you can, in this case, you can see there is a low energy band which is very tiny, few tens of MeV, which is almost flat. As you can see, flat in the sense you are changing the momentum, but the energy almost not changing. So that's very unique for 1.1 degree. If you go away from that, this flatness become even wider and so on and so forth. So that's one of the reason this 1.1 degree, particularly for twisted bilayer, is very important, and they are disconnected from the high energy band, dispersive band. And when I say 8 electron required, so there are actually this, what you see here, there are 4 copies of this. So there are 1 conduction band, valence band, there are 4 copies of that. So you can think of like 4 conduction band and 4 valence band, they all are degenerate. This is, by the way, this is a BM model which we have been talking since morning, and this is a non-interacting picture. So because this is just a hybridization physics, single particle physics, and this non-interacting band, you have basically 4 copies of that, which is degenerate here. And when I say 8 electron required, the 4 electron required to fill up your conduction band, and 4 electron basically valence band. So I'll be talking about this filling convention. -4 meaning I'll be here in this trivial gap, or +-4, 0 will be here at the 0 energy, and +4 will be this trivial gap between the flat band and your dispersive band. So now this continuum model, as you can see, this gives you large density, because it's a flat band, density of state very large. So it gives you, because if the system has a more density of state, system will conduct more. So you will expect it will give a more metallicity behavior, but it turns out experimentally that's the way the magic started, and this field started 2018 by this MIT group. They saw that this is the zoom version of this flat band. So basically you have a conduction band, valency band, and you tune your Fermi energy at the middle of this band where you have the density of state is large, but it turns out that your conductance is 0. That's very unusual, right? Because conductivity goes proportional to your density of state over diffusivity. So if the density of state is very large, you expect the conductance to be large, but on the contrary, this -2 and +2, which is the half of this band is filled, the conductance goes to 0. So this is, you cannot explain. So which means it is not, this is something diffusivity is sort of 0, and this is sort of, you cannot explain by single particle picture, the continuum model I showed you, and it turns out the single particle picture fails, and that's the way this field started. People talk about the many body physics, correlated physics phenomena, and that's the way this field started. Not only that, in the same volume there is one more paper that they see the superconductivity around this -2 and +2, which is known as called half filling, as a Mott insulator peak and so on, and that's the way this field started. And since then there are many, you can name whatever, condensed matter physics, all of them can be seen in a same platform, like superconductivity topology. So this is another interest, the topology and correlation and coexistence in the systems. And then the orbital ferromagnetism, quantum anomalous Hall, strange metallicity, large electron phonon coupling, and so on and so forth. And many of these, this phenomena, what has been seen, emergent phenomena, it turns out, although this non-interacting band structure is not very, that's the starting point, but there are interaction effects is very important. But understanding the non-interactive band itself is quite, can give you to understand many of this, and which is not trivial to even find the the non-interacting band of these systems. And sometimes what is happening recently, last few years and so on, there are like a unusual combination of properties which has never happened like other physics. For example, if you talk about like Hubbard model, for example, Hubbard model, you have it's a manifestation of strong localization. So if you look at the system, they're like a localized manner. But in this case, there are some phenomena, some experimental evidence that tells you like a localized nature. For example, STM experiment, when they do on this, Manish talk about the different stacking like AA, AB stacking. So if you bring your STM tip on AA stacking, you see large on-site repulsion energy. So that tells you that your carriers are basically localized, like a quantum dot. This experiment tells you it's like a quantum dot phenomenon. On the other hand, in the same systems, there are, for example, you have a Landau-Fine diagrams, Dirac-like compressibility. That tells you that actually electrons are delocalized. That doesn't happen like a Hubbard model. Hubbard model, everything is localized. But here, it tells you that you have a localized nature, you have also dispersive natures. So that's very unusual. Like in the same system, you have both type of carriers, and there are experimental evidence also for showing this, by compressibility measurement. Yeah. So these experiments has been seen, some of them, and the point is there any unified theory to understand, in fact, these both of them? And it turns out there is, people have approached, beyond this, of course you have to go beyond on this non-interactive picture, and the way though the theoretician can give a better answer, so the way I understood is following. It actually comes from the stacking physics. As Manish was saying, there are AA stacking, there is AB stacking. And if you look at the dispersion at AA stacking gives you almost like a flat kind of energy versus momentum relations. Whereas the AB stack area, it's like a bilayer, the Barnwell bilayer, how the spectrum is. So one can formulate this, this BM model by hybridizing these two. And this is they call like heavy fermion pictures. So in this case, the electrons are localized in AA side, but on the AB area, the electrons actually they are mobile, or they are like a delocalized nature. So you can see sort of like there are localized, also there are mobile kind of carriers one can have. And this is sort of one of these Andrei Varnovic and co. They have established this kind of theory to understand that these are conventional heavy fermion. So there are flat band kind of things. There is also a little bit of dispersiveness. So initially there is a blue and the red line. So you hybridize and you have this kind of band, and you can have this itinerant electron coming from this blue part, and the red part can give you the localized natures. So so this is one of the theory, and then it turns out that if you have this kind of part, since you have this flat band where the electrons are localized, you can ask what are the signature, experimental signature. It turns out that if you have this kind of physics, so you can think of like this Hubbard model kind of thing, that your on-site repulsion, which we are talking about on the AA side, that you cannot allow two electron to add in a same site. So basically your electrons are localized, but what you have the flavor degrees of freedom. So if your temperature is above the ordering temperatures, so if the temperature is above the ordering temperature, your charges are frozen, but your moments are fluctuating. So for example, in this case spin, in these sites, they can have either plus half or minus half. So this moment fluctuation can give rise to, for example, entropy, right? The spin entropy. And okay, how do you see that? So these are called local moments. So what I mean local moment, these are localized and they have these moments, this in this case spin is easy to understand. Now the way to understand, one can experimentally understand that if you apply magnetic field, earlier the plus half or minus half was equal probable, but because of magnetic field they will like to polarize now. And if you try to measure magnetization, you can show that magnetization will be something like B by KBT. Okay, and this is called the Curie susceptibility. If I remind you, the band fermion, band electron, the susceptibility is called a Pauli susceptibility, which is independent of the temperatures. So this gives you like a inverse of temperature. So that's a unique way to, to know even whether local moments are formed in the systems or not. And so this will be like a smoking gun evidence, like if you measure the Curie susceptibility. However, these are mesoscopic device. These are samples are micron by micron. You cannot measure magnetization to show whether to measure the magnetization in the systems. I hope in near future it will happen. But right now these are not available. So this is another theory. In fact, this is I learned. This paper came out very recently, and it turns out heavy fermion is not only the only theory. This is something Ashwin and co. They have come out with a theory, and what I understood, the theory is a subtle difference. In the heavy fermion theory, there is a connection between the flat band to the dispersive band. They are like hybridizing, and in this case, it only happens if your interaction energy scale is much higher than even the gap between the bottom and top dispersive band. But in reality, it turns out that majority of the device probably lies in this kind of regime. But I mean, some device may be lying in this regime. But if the device in this regime such that from here to here, this distance is bigger than you, then you don't need to consider that your dispersive band. One can actually, construct again the itinerant electron localized nature from the flat band itself, and they call like a decoupled non-local moments. Although it's a non-local, but it's a local moment they are talking about. Only thing is, what I understood, in this case they have a proper one-year representation that which exponentially decay, but here like the orbitals are power law decay from one AA side to other AA side. But the most important thing, the spectral function look like this. As you can see, at the mu is equal to 0, you have this flat band, but there is a dispersive nature, which is very similar to heavy fermion physics, and they also talk about large entropy. So these are the two theories which can understand these unusual properties, what I said, localized coexistence with the delocalized natures. So what are the experimental signatures? Of course, the STM is the first one. They show that on AA side you have a large this on-site repulsion. So that tells you there are carriers which are localized, and this is a first ingredient to require for local moments. And these experiments for Sahal in his group, from compressibility measurement, they see the large entropy, because as I told you, these are the spin, in fact these are like a 2 to the power n, and here your 2 is like this 2 state, and n is your electron. So instead of 2, because there are two electron valley this flavor, so actually it will be 8 to the power n, so it will be log 8 so this is normalized in kV per Moiré, so this could be so it could be large entropy. So they have measured the large entropy, and this is of the order of kV. By the way, the band fermion, if I give you the entropy, they are reduced by T by TF, typically kV times T by TF, and T by TF is very small number. But in this case, you see entropy is like all the electrons have contributed to entropy. In a Fermi surface, only near the electron, near the Fermi energy of the order of kBT, they only contribute to your entropy. But in this case, all the electrons are contributing. So that's the reason it's a large entropy. So that's, tells you that you have this some sort of interesting things. So these are fancy experiments what we have seen before. So I'll be talking about another set of experiments, a global transport called a thermopower, trying to see whether there are signature of these local moments or not. As the name suggests, so it's a thermopower device, so thermopower measurement. So you have a device, you create a temperature gradient. So once you create a temperature gradient, the carriers will migrate from hot end to cold end. In this case, I'm showing the electrons. So there goes from left to the right end. So you can see now there are deficiency of the carrier, there will be accumulation of the carrier. So you can see there will be positive and negative charge. And that's the thermoelectric voltage. And the way you define a thermopower called a Seebeck coefficient, nothing but whatever voltage you generated divided by your temperature difference. So that is called Seebeck coefficients. And so just to give you the band fermion or the non-interacting electrons, what do you expect for Seebeck coefficients? So as I showed you that in a Seebeck measurements, you have a one end, you have a high temperature, so Fermi surface is broadened here, and there is a cold, here the Fermi surface is sharper. So what is happening, your basically both electron and hole carriers are moving in your systems, and if you have a particle hole symmetry, same number of electron hole moves, so as a result there is no resultant voltage will be generated. So as you can see at the Dirac one, you have a equal number of electron and equal number of hole, so they will give you exactly thermopower 0, and that which means if your particle hole symmetric point, if your band, that will give you thermopower 0. And it is, so that's the way to understand thermopower. So basically thermopower proves, in other words, particle asymmetry in the, so wherever there is a particle asymmetry, that's the reason, thermopower device, either p-type or n-type device, right? It has to be semiconductor. So if you break the particle symmetry, then only you can have a large thermopower. So if you, for example, if this is my band structures, for example, so this is your Dirac point, this is a conduction band of singularity, this is your band of singularity, your valence band. So these are the 3 particular symmetric points, and you can see that 3 crossing point you would expect in these systems. However, this picture what I told you in a band fermion, this is not true if the electrons are strongly correlated like the Hubbard model kind of physics. And it turns out, how do I see this difference? Because in a band fermion, as I told you, particle asymmetry brings you all the physics. But in this case, which I'll come in a moment, that in this case the entropy comes because of there are 2 reasons. One called configurational, another is called spin or the flavor movement part. The configurational meaning how you can rearrange the, because you are feeling the carrier, but there are many ways. Instead of this, I could have filled this or that, right? So there are many ways I could have filled. So this is called a configurational part. How many ways I can fill up, like, so that's called configurational entropy. Other is the spin, and for example, the moment entropy, spin entropy. So those 2 you have to consider if you have this kind of localized manner. And it turns out if you have these 2, the crossing point which I explained you previous slide in the particle asymmetry, this thing, they have a distinct features. For example, so this will, my whole talk will be on based on how these crossing points are, their temperature dependence are, and how they behave like in presence of some external magnetic field. So coming back to the device, I hope so this is good, towards the end of the talk. So I don't have to describe all this device making. Mandar and Avik already said how to make this kind of devices. As already they also say that it's a very extremely challenging to make these devices. But what you see here is a typical twisted bilayer device. The dimension will be maybe this scale, I think around 4 to 5 micron. And what you see the color, these are boron nitride color, because these devices are encapsulated by bottom boron nitride and top boron nitride. And what you envision, basically you have this twisted bilayer, there are contacts. And the way we measure thermopower, there is a heater line. So you basically you pass a current through this heater. So that creates a temperature gradient across this sample. And you basically measure the temperature difference and the thermoelectric voltage generated across this sample. So without going details, so we have now used 5 devices, and they are classified in 2 different categories. 3 of them now. So they are on. Of course, they are encapsulated by boron nitride, but they are on SiO2. So we say that they are probably lessly screened, or maybe the expected U by U is the interaction strength, W is the bandwidth. So maybe the U by W expected for these devices higher, and we have some indirect evidence because the temperature dependence. We know these peaks for the unscreened devices, for these peaks survive larger temperature compared to the screened devices. And other class of devices, these are, for example, either on graphite gated devices, which typically boron nitride thickness of around 25 or so, and also use a twisted double bilayer graphene at 0 displacement field, which has a larger bandwidth, and the U is expected to be low. So there are 2 kind of devices. What I am trying to say that there are device which is U by W is expected to be larger. So these are the, you can say, interaction may be dominant in this device. So this is, it's not the interaction 0, but the interaction might be less dominant in these systems. So without going detail, so I think measurement technique I'll skip now. So this is one of the device, how the thermopower, if you measure as a function of filling I was talking about. So the filling meaning the number of carriers per unit cell. So this is your Dirac point, and +4, if you recall, there was a dispersive band. This is your flat band, there is a dispersive band. So +4 is the trivial gap between your flat band and dispersive band, and -4 is the this bottom of your flat band and the dispersive band. And that's so Dirac point, and these 2 crossing points are that's very one can expect. But most importantly or more interestingly, there are 2 other crossing points was there. if you think out band electron, so if this is my density of state, I told you the particular symmetric point will give me the crossing points. So which means Dirac point, I should have particular symmetric point, and this band of singularity has a particular symmetric point. So I would say crossing point not only at the Dirac point plus this symmetric point, which is typically happen plus 2 or minus 2. That's typical band of singularity. So one would expect the crossing point plus 2 or minus 2, but experimentally we see plus or minus 1. However, this position of band of singularity, that's again, it depends on lots of relaxation and all, but people have seen mostly electron, the band of singularity around plus 2, minus 2, but here the crossing point not seen plus 2, minus 2, but it's plus 1, minus 1. It's not only one device, all of the devices, crossing points are close to plus 1 and minus 1. So that was unusual. Next unusual is, if you do temperature dependence of the thermopower, so these are the resistance, how they changes. This is the way the thermopower changes. So let me again focus on this crossing point from this temperature to let's say 6 Kelvin to your 50 Kelvin. What we see now, if I plot this, the crossing point in the flat band as a function of temperatures, you can see for the magic angle devices, they almost remain constant up to 60 Kelvin. This is 1.05. The other devices, which is 0.95, again these 3 crossing points survive, but there are a little bit of changes. So not only that, this is another device, unstrained device, the third device. Again in these devices, the crossing point at plus 1, minus 1, they remain robust even up to 40 Kelvin without any change. Although the crossing point plus 4, minus 4, they keep changing. So this is, I'll tell you why this is anomaly. First of all, appearing at plus 1, minus 1 was an anomaly, and second, they do not change the temperature, that's also an anomaly. And by the way, to just compare with other kind of devices, which is I call like a second class, like it's not a second class it's a screen device. So there you see these crossing points are highly sensitive in the same temperature range. In fact, this 3 crossing, they become single crossing. Even the graphite grade device, again 3 crossing became a single crossing. Yeah, so that's the experimental data, 5 devices. So question is, how do I understand? And it turns out that thermopower to understand theoretically is very challenging. So first you have to understand, start with the non-interacting band Fermi, like the way we understand the Fermi surface and those kind of single particle pictures. Then one can add the simplest interaction, like mean field level, like Hartree-Fock level. Then you can higher order complexity, like okay, then you can use the DMFT kind of thing. So that takes care of bandwidth plus the strong correlations. The simplest one, or the minimal model, called toy model. So in this model, advantage is, although this is not a realistic model, but the advantage in this model, the bandwidth is 0. And you have only the many body correlation, and one can use, it's called atomic limit theory. So this theory is easy to calculate. These are expensive calculations. This is also one can do easily, but the DMFT is very expensive. But however, so this is, I'll say, much more exact DMFT. DMFT is much more exact to understand experiment. But this is a minimal model. One can understand what is going on in your these things. So the band electron, if you do the theory, just a simple non-interacting theory, if you increase the temperature, this is the blue curves which give 3 crossing points, they become a single crossing. And one can understand very easily, because the non-interacting, what is happening, what you should look at, density of state times the derivative of the Fermi functions. Because that gives you the non-interacting physics. Now because of your temperature is high, the derivative of Fermi function is so large, even 50 Kelvin, you can see that you will not see these features of your band of singularity in the spectrum. So you will see like this kind of picture, and because of that, it will give you only single crossing. So the band electron, if you do the physics, because of this Fermi function broadening daily by daily, you will get a single crossing. There is no way 3 crossing will be independent of the temperature up to 50 Kelvin. On the other hand, if you are at the extreme limit, the minimal model, atomic limit, one can show that if you have, since I am running out of time, so if you have U is equal to non-zero, you can show that because the double occupancy is suppressed, the entropy will be suppressed. Because at this point, all the side have one electron, and you cannot have rearrangement in the problem. So rearrangement has been stopped. So as a result, the entropy will suppress. So if you do the atomic limit, the crossing points, the 3 crossings survive much higher temperatures then your this thing. So this is the all theory in the same slide. This is so what I'm showing here, there's 3 crossing points. So there's crossing point around, by the way, band electron gives you crossing point around 2 and -2 and the Dirac point. And these 3 crossing points, as you can see with temperature, they're merging to single point within 20 Kelvin. This is true for non-interacting band as well as if you add the Hartree form. DMFT gives you this YOLO result, so that tells you that a large temperature, first of all, they're coming close to +1, -1, and they even survive much, larger temperatures. And this is for atomic limit, these are the case, and these are the experimental results for different devices. These are, I'm calling it unscreened devices, which they survive. These are the screen devices, they merge together. So not only that, you might have got a feeling that if this is a moment, if I apply magnetic field, I should polarize something and entropy should suppress, and thermopower is basically, I probably didn't emphasize much, thermopower basically probing some sort of entropy, right? So and indeed we see this is the in-plane field, we see there are some reduction in thermopower even within -1.5 to this regime, and almost 30% reduces with parallel field. And this has been shown earlier, consistent with literature and as well as this compressibility measurement. So I think, so this is the story here. So I think what we have shown, I will not say we have a strong evidence of the local moments, but our global transport for the first time is shown some signature of this, local moment physics in this kind of systems. And still there are lots of puzzles to understand what is going on in this system. Yeah, with this I would like to thank.
Thanks. Questions? Manish.
So Avik, this Anindo, this crossing at +-1. So this DMFT captures that? It does capture it, huh? I see. So any intuitive understanding why it shifts from 2 to 1?
So very good question. So intuitive answer. So apparently pseudonym not +1 -1. What I understood, pseudonym -1.33 and +1.33. I don't know the intuitive answer, but that's the answer. That's something not exactly 1, but close to 1.33.
Second question is, do you expect to see quantum physics in this system?
So it turns out people are talking about some quantum physics in this kind of systems.
Okay, simple question. How does the resistance versus temperature look?
Yeah, so resistance versus temperature is almost linear in this, this particular part. So they are not that way, but people are. I have reviewed some part, but I have seen that people are talking about quantum physics. But yeah, resistance versus temperature is mostly linear.
So just wondering, can you give some details about the DMFT calculation? What is the configuration and how expensive are these?
So, okay, I am not the expert, but I can tell you, I try to, so these are, okay, first of all, in this case, these are not a strong limit because the bandwidth was around, varied 20 or 30 MeV. The U was not larger than that, U was also, because apparently DMFT, they cannot do the U if it's bigger than the bandwidth. I think U was comparable. I think for this calculation, U was mentioned somewhere.
20 MeV.
U also was around 20 MeV. So I think bandwidth around 20 or 30 MeV. We did a even larger bandwidth. The U was slightly lower than that thing, and the calculation based on SU4 kind of thing. And yeah, I don't know what details you have. These are the numbers I know. Yeah.
Go ahead.
So I was asking that what is the effect of the magnetic field on the thermopower, because in the presence of a field the degeneracy will be split of the Dirac cone will get split.
Yeah. So if it turns out if you have band electrons, yes, there will be some Zeeman splitting will happen.
No, Zeeman splitting as well as the Dirac cone degeneracy corresponding to time reversal will be broken.
Yeah. So you can see the shift of these two band kind of thing, right? Because one will be higher and one will be lower kind of things, right?
Yeah, on energy scale also and on the K.
Yeah, one can think in a K also. Inversion, that is, yeah.
And have a displacement because it causes V dot T.
Right.
Okay. No, because in
But if it is like a Zeeman kind of term, like a Zeeman kind of term, if you do at this temperature, let's say 20 Kelvin, what we are doing, we have one can calculate the how much from the band electron, and you don't expect anything to change. Because again, the Fermi for DL, the del F by del is so large that Zeeman splitting, you can see 20 Kelvin. I am doing experiment at 25. Your Zeeman 10 Kelvin Zeeman is like how much? It's like a less than a milli electron volt. So because of that, you don't see much effect if the band, just to consider non-interacting band electron. Okay. But here I am talking about the effect is more, although it's very, people talk about, because even in plane pre-twisted Bailey, people are talking about orbital effect. Although I am applying an in-plane field, but people talk about, which I do not understand. There are some orbital effect also come in the pictures. Okay. So people say that it's not only spin polarization, the way I explain that moments are polarized, but may not be case. There might be some other effect also. But band electron cannot explain the effect, what you see.
Yeah, final question.
Hi sir, with regards to the Kondo effect that sir asked, has there been a specific heat study as such? Because for specific heat in heavy fermionic systems, the linear coefficient is very high.
Right, exactly. That's the way we teach the condensed matter physics. No, the effective mass very high. Right?
Yes, sir.
Again, the sample. I don't think people have. The sample size is mesoscopic size, like 10 by 10 micron. So I don't think specific heat or like I told you magnetization. This kind of measurement is probably we need some unique technique. But the thermal conductivity can be done. Something we are also looking at this kind of device in this mesoscopic device.
Okay, so let's go ahead and thank Anindya. Yeah, why don't you catch him? You are tall, right? Okay, before the next talk, we'll have few words by Efrat on Assa.
Hi. Hi, Efrat. Hi.
Good to see you.
And hi, Naraf.
Hello.
Hi. So, if you can say a few words, Efrat, that will be nice. Yeah, if you can just. Yeah, can you hear me? Hello, can you hear me?
I can hear you. If I can hear.
Yeah, Efrat, if you can briefly tell us a little bit about this, means. So I just wanted to point out that Professor Efrat Simpsoni, she is a part of this project, and she played a very important role in organizing this. Particularly, we all know that this particular symposium is dedicated to the memory of Professor Assa Auerbach. So Nadav was of course at that point of time was in a very difficult situation, but he kindly agreed to give this talk at our request, and Efrat particularly talked with Nadav, and also we are going to hear Professor Shahalilani at the later stage of this symposium, and so Efrat was a very important part of the organization. We unfortunately could not make this entire things in the full hybrid mode by both online and offline access, but we are recording it with the hope that we'll be able to share it with our Israeli friends, all the details of the lectures. So now if Efrat, if you can say a few words, that will be great.
Okay, I didn't quite prepare, but first of all, I want to say that I'm very sorry that I'm not with you. I would be happy to attend, and I really want to hear the other speakers. I would love to visit India, but somehow it didn't work out. And I'm very sorry for the circumstances. It was a shock for all of us to miss Assa. He was really a very central figure in physics in Israel, and in particular in condensed matter physics. I think he's really behind a big change that had happened at the frontier of this field in Israel, and almost all of us are, in our entire condensed matter community is seeing him as a kind of mentor, even those of us who were not under his direct supervision and colleagues of the same age group, more or less. So I'm very happy that actually will show us very interesting new work, which I'm eager to hear. So, and thank you for organizing this in Haifa. I really appreciate it.
Okay, so the next talk will be by Assa Auerbach, and he'll tell us about imaging quantum oscillations and millitesla pseudomagnetic fields in graphene. Go ahead.
Okay, you can see my shared screen, right?
Yes.
some lambda level interference. And this really tells us that we're breaking some symmetry in the system and we have more than one Fermi surface. And so two slightly different Fermi surfaces in area would lead to slightly different lambda level frequencies, quantum oscillation frequencies, and similar to in light, interference in light, we will get some destructive interference. So then we can also do this measurement at 170 millitesla, and we see that we actually form several more of these BD nodes. So we tried out different theories for forming more than one Fermi surface, and I'm just going to discuss the one that we found consistent with our results, which is strain-induced pseudomagnetic fields. So this is work from Paco Guinea in 2010. If you take a graphene sheet and you bend it by an angle theta over an angle L, and you get an effective gauge field, which couples in a similar fashion to an external magnetic field, but does not break time reversal symmetry, so it must couple with an opposite sign at value k and k prime. And if we put numbers for 1 degree bending angle over 1 micron, we get something like 1 Tesla pseudomagnetic field. So now how does that explain our beating? So if we look at the spectrum of the Dirac cone at value k, the fields add up, while at value k prime the fields will subtract. This leads to a small shift in the spectrum. And we can go and calculate the first beating node, where we'll get destructive interference from the oscillations. So I do that analytically. So it's basically just the external field divided by 4 times the pseudomagnetic field. So now we can try to fit our experiment to this model and calculate the pseudomagnetic field, and this is what we get. And for consistency, and now with no additional fitting parameters, we can do the calculation for 170 millitesla, and this is what we get. So we see that we retrieve not only the first beating node at 170 millitesla, we also retrieve the second and the third, and maybe even the fourth beating nodes. And so now we can do this as a function of space and get a map of the pseudomagnetic field. We see that we get these kind of 1 micron by 1 micron regions near the edges of the sample, and the pseudomagnetic fields that we measure range between 1 to 6 millitesla, which would correspond to around 1 to 10 millidegrees. If we put that in numbers of strain, we'll get very small strain of around 10 to the minus 5. And I would like to mention that in magic angled graphene, for example, in twisted systems, twist angle disorders on the order of 0.1 degree, which in this case would lead to pseudomagnetic fields of around 0.1 Tesla, and this is already quite significant, and perhaps another type of disorder one should consider in these twisted systems as well. So this is my last slide. I just want to show you the consistency of this pseudomagnetic field model for the measurements as a function of displacement field. So you can see now we take a point measurement. Before I showed you point measurements from, let's say, regions with no strain, and now I'm showing you a point measurement at a point where we do measure a pseudomagnetic field, and you can see the interference at these curved lines here, and they match the calculation as a function of displacement field as well. And also, it's more difficult to resolve in the bilayer, but a pseudomagnetic field will also couple to the bilayer band and shift the lambda levels in the bilayer band as well. It's a much weaker effect, so hard to resolve, but we can resolve it. I'll take a line cut at 0 displacement field and point you to the where we measure the interference. So we have this interference in the fast oscillations at these 2 points. And when we do the calculation with the same 4.2 millitesla, we can capture this interference in the bilayer oscillations as well. So with that, sorry. added this last slide just to show you what we've progressed since then. So you can ask whether this technique is applicable to twisted systems as well. So recently, our group published a paper on bilayer graphene aligned to HBN, where we observed we can both reconstruct parts of the band structure plus observe magnetic breakdown at different filling factors. And in twisted alternating twisted tri-layer graphene, recently published a paper. And in this system, there's flat bands, but there's also a Dirac cone. And actually, by looking at the oscillations from the Dirac cone, we can infer a lot of information on the interactions in the flat band. And last system is twisted double bilayer graphene. This is still unpublished. But basically, we can observe lambda levels both in the dispersive and in the flat bands as well there. With that, I'd like to acknowledge my collaborators, so then experimental side, and my advisor Elizeldov, Haifa postdoc that recently started a lab in China and performed the measurements with me. Matan Uzan fabricated the device, and Sreen made our tips. We have a bunch of master students who helped and did some of the tight binding calculations, and Yuri Misielov was a staff scientist, and basically the head of the lab. And in theory, we have Bing Ayan and electronics for measuring the squid. We collaborate with Martin Huber and Lucy Benver, and the HBN from the But I'll finish with the summary here. Questions?
Thanks.
I don't know how I would read it, but I lost my timer.
No, you were fine. You're fine. Questions?
Okay.
Yeah, please switch on the mic. Please switch on the microphone before asking the question. Then only you can hear. Yeah. Hi, Nadav, am I audible?
Yeah, I can hear you.
Yeah, so you were telling that this particular magnetic field in the case of the TBLG, that will be twist angle dependent, right? So what will be the typical comparison with because this, I believe, these are untwisted tri-layer graphene, right? So in the case of the twist, what can you sort of give an idea that what type of things? If you have a Moiré pattern or some type of super Moiré, what type of things one can expect?
Yeah, so I can talk a little bit more in detail on these measurements. So these two were done in a different system at SPARC, and this one is done by us. And so there's different things you can measure in twisted systems. We actually focus a lot on trying to measure spontaneous magnetism. So this is working at very low magnetic field, like 10 millitesla, and where we don't observe quantum oscillation, but we can observe, symmetry broken states. So, for example, and we have a paper in review now on rhombohedral systems, but we also have measurements in this double twisted bilayer system near the fact that integer fillings, and we see spin polarized states, valley polarized states, and these can all be measured using the scanning SOP. Using the Hasselbalch to really to try to reconstruct the band, and can be difficult in twisted systems, and this is because the dispersion is so low. So when you have a flat band, you apply a magnetic field, the lambda level spacing is very small. And at least currently with our available, so this is kind of technical, but we cannot always measure a base temperature. So
it can be hard to resolve the flat band oscillation. But what I wanted to mention in this work in twisted trilayer graphene, that if you're lucky and your system has not only a flat band but also a Dirac cone, then the Dirac cone oscillations can be easily resolved with the Haspan-Alpin, and just by kind of studying the oscillations in the Dirac band, because you have more than one Fermi surface, right? You have the Dirac band surface, but you also have a Fermi surface in the flat band, and then the filling of the Landau levels in the Dirac band can change drastically due to interaction. And this work really kind of studied the interaction of the due to the flat bands, and just by looking at the Haspan-Alpin of the Dirac cone. And so these are kind of some examples. And in this work of bilayer line to HPN, so they could see some oscillations in the flat bands, but really a lot of the information, at least of the time binding model, you can get from studying the dispersive bands where the oscillations are very clear.
I have a question. So in these, using this measurement setup, can you also measure the, let's say, the magnetization, the local magnetization, and if so, what is sort of the length scale over which you can measure? For instance, I mean, I'm thinking of twisted bilayer graphene. Can you actually measure the local moments that are formed, let's say, at the AA patches, and if so, how big are,
Okay, a good question. So, first of all, what we measure is differential magnetization. So in order to get the magnetization itself, one has to integrate, and that's possible in some cases. And to get something quantitative on the how strong the magnetization is. For example, if you have a quantum anomalous Hall system and you want to, let's say, measure the gap using magnetization, then you really need to quantify it. And for that, you have to kind of integrate the differential magnetization and also perform inversion, because what we actually measure is the magnetic field, not the magnetization. So in order to perform inversion, we have to take a 2D image that's larger than our sample to capture all the magnetic field. And of course, inversion is not a one-to-one. Inverting the BOSFR is not one-to-one, so you have to assume something. For example, the magnetization is out of plane. And in terms of spatial resolution, that's limited by our tip size. So until now, for magnetic imaging, we typically use 100 nanometer scale squids. There's work to try to improve that and have good sensitivity even at lower field, but the field sensitivity is proportional to the area of the squid. So the really small squids that we use, 30 nanometers, at this time, our smallest resolution for magnetic imaging is around 100 nanometers, and that's too large for any of these twisted and Moiré systems.
Okay, thanks.
Okay, if there are no further questions, let's thank Nadav again.
Okay, we'll get back here at 4:30 for Professor Shah Lilani's talk.
I would also be very grateful if you have the talks recorded, if you share them with me as well.
Most welcome.
Okay, thank you very much.
Professor Ajit Balaram will chair this session.
Okay, so the final talk in this meeting will be given by Shah Lilani from Weizmann, and he'll tell us about interacting energy bands of magic angle graphene revealed by quantum twisting microscope.
Okay, hi everyone. It's a pleasure to be here. I'm really honored also because I was invited to give this talk by Assa, the late Assa Auerbach, a week before he passed away. So it's really my small thing that I can do for Assa, that was an amazing scientist for everyone in our community. What I want to talk about today is about new experiments and new techniques. Some of you may have heard about the technique, but I'm going to show data that I guess most of you have not seen, which probes for the first time how the energy bands in one of the most important twisted systems that we have, magic angle twisted bilayer graphene, looks like. And the way we are measuring these energy bands in momentum space is using this new tool, which is called the quantum twisting microscope. This microscope is very similar to the STM that you all know. The main difference is the tip of this microscope. Instead of having a sharp tip, you have a van der Waals device with a flat plateau. This plateau comes in contact with the sample that you want to measure, and electrons can go through this two-dimensional interface at many places into the sample, can tunnel. If they do it coherently, all these tunneling interferences, all these tunneling events interfere, so we get an interferometer on our tip. And I'm going to show you that with this we can do a lot of things. One of them is image energy bands in momentum space. This work was done by two teams that you see here. Most of the work that I'll discuss was done by this two teams, John, Jiwen, and Alon. So, one of another motivation that we had to develop this tool was the field of Twistronics that you all know in this conference, which is that if you take two layers, rotate them with respect to each other, we can build a lattice that has a lot of interesting physics. People twist carbon, semiconductors, high DC superconductors, everything that you can imagine which is 2D. And the interesting thing is that the tuning angle of this field is, the tuning parameter is the angle, the twist angle. And the phases that you get are extremely sensitive to this angle. You can change the angle by 0.1 degree. And you go from a superconductor to an insulator. This is amazing. It means that you can explore many different phases, but this is also the Achilles heel of the field, because it says that if control over the angle, it's very hard to scan through these phase space of twisted layers. So the idea that we had in mind is why don't we have a tool that allows us to continuously in situ scan this important parameter? So we were not the first one to think about it, and before us people invented these kind of devices, which common to all of them is the fact that they have a movable part, for example this wheel in the center, and an AFM tip that can push this movable part and rotate it. This worked very nicely, but with many limitations. For example, you can see that if you push a part like this, you not only rotate, but you also displace it. It doesn't work with monolayers because they are too flimsy to be pushed around. When you rotate to a commensurate angle, let's say 0 degrees, the two-layer locks and it's game over for the experiment. And the most problematic part is that all these experiments work only at room temperature. If you try to cool them down, they get stuck. So what we said is, let's come out with a fundamentally different concept for this kind of in situ rotation. And our idea was that sorry, I'm a bit sick. And the idea was that we will use the AFM itself as integral part of the device. So this is what we do. We split the device into two. One part is on a flat substrate, another one is on the tip of an AFM, ending with a flat plateau here. Then we use the AFM to bring the two together. They hybridize and create our twisted interface, which we can measure by applying voltage, measuring current through the interface, and we can do it while the system is rotating and space connect. do it with really, really high accuracy on the angle degree of freedom. So this gives us a nice twisting machine to basically explore all the physics as function of twisting. But what we found is that with a small modification, we can get another very interesting modality. So if we insert a thin layer of an insulator, this insulator acts as a barrier that separates the two sides, one acting as a probe for the other. Then, just like in SPM, electron tunnel from one side to the other, but now since the contact area is two-dimensional, they can do it in many, many places at the same time. And if all this junction is quantum coherent, all these tunneling events would interfere. An electron would pass only if its phase evolves the same way in both sides. Otherwise, we will get negative interference between these tunneling events. So what does it mean phase evolve the same way in both sides? It means that the wave function is the same. It means that the momentum is conserved. Okay, so we have momentum conserved tunneling. And now we can use the rotation degree of freedom to actually use this microscope to scan in momentum space. So for example, if you consider two graphene whose wave functions are like this in momentum space, if they are unaligned, there would not be any current between the two layers. But now if we rotate, at some point the wave functions would overlap and we will get current going through. So we can basically cut a line in momentum space. So let me show you the simplest experiment that we did when we first built the system. So this experiment is at room temperature, measuring the current between graphene on the tip, graphene on the bottom, 3-layer of tungsten diselenide insulator, and what I'm plotting here is the current as function of rotation angle and bias, and this is what we get. We get a very sharp X-like shape, and if you guess that this is related to the Dirac dispersion of graphene, you are right. Basically, rotation is just like momentum, because we rotate in momentum space. Bias is just like energy, so we get here energy versus momentum. If we want to understand it better, let me take you through this graph. So if we are looking at zero angle between the two layers and small bias, if we think about the two layers in real space, they are commensurate, but they are also commensurate in momentum space, and this is why we get current going through. But we cannot tell if the current is due to real space commensuration or momentum space commensuration. If we now stay at this angle and go to higher bias, you see in real space we stay commensurate, but in momentum space now the Fermi surfaces are not commensurate. And you see that the fact that we lost the current means that we are actually sensitive to momentum space. In fact, what we did was to increase the bias window. There are much more states that want to get through, but none of them do because of negative interference, because they don't match in momentum space. If we now rotate and keep the same bias, then in real space we are at arbitrary angle, but now in momentum space we touch, and you see that we regain the current. So this shows you how this acts as a momentum resolving probe. Now, all these measurements were done with a simple gadget that you can all put in any AFM that you have in the department at room temperature. But since then, we took this technique to lower and lower temperature. We built a microscope that works at 4 Kelvin, and now we have even a microscope that works at millikelvin. What I'm going to show you today are results from measurement that comes from a 4 Kelvin microscope. So, take the experiment that I showed you before and remove the insulating layer. If the two graphene touch, you get what we all know, which is the twisted bilayer graphene system. So what will happen if we do the same measurement here? As I told you, if the angle between the two layers is small, then there are momenta states that overlap and the electron can go between the two layers. But what happens if the angle is large? Let's say it's 30 degrees between the two layers. You see that now there are no matching energy momentum states, right? So you should not get current. And indeed, this is what we get. Negligible conductance at 4 Kelvin and 30 degrees between the two layers. But what we see is that if we increase the bias, the current does increase, but it does it in steps. And steps mean that we are activating inelastic tunneling channels. So what's going on? What are these tunneling channels? In fact, if we apply even a small bias, you can see that once the bias difference hits the branch of a collective mode, the simplest one of them being a phonon, then the tunneling electron has enough energy to emit a phonon, which gives the missing momenta between the two Dirac surfaces. Now, if this whole inelastic tunneling process is also momentum conserving, then we can do something nice, because then we can rotate the two layers, scan the momenta of the phonon that we are emitting, and see at what bias it appears, and by this we can do spectroscopy also of phonons or generally of collective mode. So here is the experiment, two graphite layers rotated with respect to each other from 0 to almost 60 degrees, 4 Kelvin in the measurement, low bias, and this is what we measure, conductance. You can see that we do get at low bias 0 conductance, and then it climbs in steps. Okay, to see it better, let me plot the second derivative, d square I to the d square, and you can see a spaghetti of states here and here, mirror symmetric, around bias and around 30 degrees. And you can ask, what are these states? We see that they are very, very slowly dispersing as compared to electronic states. For example, this is an electronic dispersion with V Fermi. So these are much, much slower states. What are these? These are phonons. Here is the comparison to phonons just from theory. So you can see, we can see phonons with the same tool just doing inelastic momentum conserving tunneling. And the nice thing is that beyond just seeing the spectra of phonons, which is something that some techniques like neutron scattering or X-ray scattering can see, the intensity of the lines here actually gives us the electron-phonon coupling and how it depends on the different phonon modes and on the momenta. And this is very, very important information if you want to make theories of, for example, of electron-phonon creating superconductivity in these layers. Last thing before I go to my main story is to say that we can, until now we discussed things in momentum space, but we can go with the same tool to do an interesting measurement in real space, imaging the electrostatic potential with high resolution. So the best way we have till today to image electrostatic potential of a sample is the scanning single electron transistor that has a quantum dot that is extremely sensitive to potential. You scan it above the system, and then it can give you a picture of how the electrons look inside the system. And in my lab, we've used this kind of scanning nanotube quantum single electron transistor to basically view a big set of phenomena in quantum matter. We observed the first picture of a Wigner crystal. We saw that electrons can be attractive only by Coulomb repulsion. We got the first picture of hydrodynamic electrons flowing like in Poissy flow. We showed that they can flow absolutely without the Landauer-Scharvin resistance, and we image interesting phases in Moiré system. So it's a great detector. The only problem is that it's quite large. Its size is of the order of 100 nanometers, determined by the lithographic size of this dot. And this means that we cannot image potential on this large class of interesting Moiré system, because here the scale is 10 nanometers. So we were thinking how we can take this scanning single electron transistor and invent something much, much smaller that will allow us to look even on this scale. So what is the smallest thing that can act as a scanning electron transistor? This is a single atom. And this is what we do. We use a single atomic defect in tungsten diselenide, or HBr, as our detector. So what we do, we put it on one electrode. We put the interesting physics that we want to scan on the tip of the QTM. For example, here it would be Moiré system. Electrons flow from one side to the other, by single electron hopping. So this acts like a single electron with a Coulomb blockade and so on. But now the fluctuating potential in our system is gating also this defect. So if we scan the system across the defect, we can image this potential in grid space. And this is what you see here. So this is an image of our tip shape done with the single atomic defect. And if we focus on this area and plot as function of x and y and also gate voltage, we look where the Coulomb blockade peak of this transistor appears, we can see these rings. These rings are the isocontour of potential. And from this we can build up a map of the electrostatic potential with very high potential sensitivity and with 1 nanometer resolution. So this is really nice direction of the same microscope telling us that we can really image potentials and thermodynamic quantities on really, really tiny scale. And now I want to take you to the main story that I want to tell today, which is the nature of the interacting bands in magic angle graphene. So magic angle graphene, two twisted layers of graphene, they have this mini Brillouin zone in momentum space, where at the corners you have the original Dirac cones of the top and bottom layer. And at an angle of 1.1 degree, we know that the bands are extremely flat. They are separated by energy gap from remote bands. And they still have Dirac cones at the K of the top and the K of the bottom, where the original Dirac cones went. Okay, and this is actually protected by C2T and C3 symmetry. And the widest maximal width of this band is happening at the gamma point, where the remote bands are also there. So very early on, when people did experiments on magic angle graphene, they had this question: how do we describe the system? Which language do we use? Do we use local atomic-like picture? For example, the first picture described the system in terms of a multi-insulator where electrons are localized in space, or STMs looking on wave function, they saw that they are localized at very well defined positions in grid space. But very soon after came an experiment that showed that if you break the symmetry just a bit, you get something which is topological. You get Chern bands, anomalous Hall effect, which is completely different than thinking of this as local picture. So what people said is, okay, the system can have different ground states. Some of them we can think about them in the atomic limit. Some of them we can think about them topologically. But what we found is, in two measurements that I'm going to show you now, that this is not true. It's even more interesting. And what happens is that at the same time, the system can behave both as localized and as topological. Okay? So the phase diagram, the early phase diagram looked like this. So it's a function of the number of electrons per unit cell we fill in the Moiré lattice, going from -4 to 4, and its temperature. We start from insulated gaps to the remote bands here. And then what was seen at very low temperature, below 4 Kelvin, the appearance of correlated insulating state at integer filling factor of the system flanked by superconducting system. What we found is that there is something much more interesting happening at much before, at much higher temperature. So basically what we called it, we said that this is a parent broken state of the electronic system, and all the interesting physics that happens at low temperature comes out of this parent state. So let me show you what I mean by this parent state. So the first measurement that we did was to use local detector to measure electronic compressibility. And this is what you see here, the inverse electronic compressibility as function of filling factor. And the weird thing that we saw is that the compressibility has these very sharp jumps at integers, very asymmetric sharp jumps. Now, what can these jumps be? Now, if you look at filling of -4 or 4 electrons per unit cell, you can see these large delta-like peaks of inverse compressibility, and this means that we have energy gaps here. At the center, at neutrality, we do have a peak, but much, much softer, that goes like 1/√n, and this is the behavior you would expect from a Dirac cone. Okay, so Dirac-like behavior. So what are we seeing here? What we speculated is that these are Dirac revivals. Basically, somehow the system finds a way to reset back again and again and again to the same neutrality point of itself. So the picture we had in mind, we simplified the band structure, said let's think of just 4 flavors, each having a Dirac point spectrum. And then what we said is that if we start from neutrality and start adding electrons to the system, at first they all add symmetrically, all flavors are being populated, but at some point the system becomes unstable. One flavor takes all the carriers where the others are emptied back close to the Dirac point. And now we need to refill them again with Dirac electrons. At some point, again, reset, refilling again, reset, and so on. Now, if you think about what the states mean, for example, just after we filled 1 electron per Moiré side, and I look on it in real space, you see one full flavor is filled, the other ones are not, so it means that we have just 1 electron per lattice side, and the flavor of this electron is chosen. Okay. But then we did another experiment using the same detector, measuring the local entropy, and we found that the picture is even more interesting. So when you do this measurement at high magnetic field, this is what you see here. The entropy per Moiré unit size is function of the filling factor at high magnetic, parallel magnetic field. When you do the measurement here, it seems very consistent with what I showed you before. You know, entropy in a Fermi liquid is proportional to the area of the Fermi surface. So you can see that if we start from 0 and we start filling up, Fermi surface area increases, and entropy also increases. We do a reset, this becomes inert, small Fermi surfaces here, entropy goes down, increases, drops down, and so on. But the surprising thing happened when we took it to 0 magnetic field. Then we saw that above filling factor 1, there is a giant increase of entropy, which is of the order of kT log 2 per Moiré side. kT log 2 means that you have 1 degree of freedom, completely free, for every electron that you put in the system. And this you cannot get in a band picture. Okay, if this is what we imagine happening near filling factor 1, you see this band is inert, this band has small Fermi surface, and nothing can move. There cannot be entropy in the system. So where is the entropy coming from? One way to speculate is so much entropy can only be explained by local moment behavior, namely that these are free to fluctuate, both spin and value. Okay? So you can imagine that instead of this band picture, you take another picture which is the incoherent Mott insulator, or if you want more simply, you can think that in the quantum dot picture, that at every side we have to put 1 electron, this is P, but we can choose to have the flavor of this electron at different side different. Okay? And this is what will happen to a Mott insulator if the temperature is larger than the spin exchange degree energy. But you can see that also this model incorrectly described the system, because if this was true, we would expect to see Mott insulating gap of the size of the charging energy, and we don't measure them. We measure something which is compressible and conductive even in integer filling factor. So we understood that there is a puzzle. System does not behave like it's described by band or by topology. It's not describable by Mott insulator local physics. It's somewhere in between. And this is what we wrote in the abstract, that the correlated state feature an unusual combination of seemingly contradictory properties. Some associated with itinerant electron, such as the absence of a thermodynamic gap, metallicity, and a Dirac-like compressibility, and other associated with localized moments, such as the large entropy and its disappearance under a magnetic field. So there is something strange. Within the same system, electrons behave both as bands and as localized. How can we get something that does this? Well, we know that there are systems that behave like this. These are the heavy fermion systems. They have one heavy element that gives F electrons, which are flat and give magnetism, and other electrons which are more extended, and then when they hybridize, they create these heavy fermion bands. And very, very interesting phase diagram. But in twisted bilayer graphene, we don't have any heavy elements. We just have carbon rotated with respect to itself. So where on earth will we get heavy fermion? It turns out that if you look carefully on these flat bands and you realize that they are not only flat, but they are also essentially topological, you get it automatically from these bands. So let me show you how it goes. If you look on the flat band, you can see that in most places in momentum space, the wave function, which is plotted here, looks very boring. It just looks like a localized wave function in the center of Moiré set, okay, in the AA side. If it was all across the band, then it's an atomic limit band. You can go into the localized limit, think about it as localized states, right typing model, and so on. Problem is that there is band inversion, and if we look on the gamma point here, the wave functions look different. They have a hole in this side. So with all these wave functions together, you cannot do anything. This is a topological band, and you cannot eliminate that. But if you remember that we also have strong interactions, and interactions can be larger than the energy gap to the next band, this interaction can mix the missing states, the missing atomically localized states that were taken from this part of the band. So if interaction is strong, we might as well change bases and think of it in a different basis, which is the following. You have flat bands and Dirac-like, double Dirac-like electrons at the gamma point. Okay, these are the F electrons of the heavy fermion, F electrons. These are the conducting electrons. They have these wave functions. In these spaces, if you write the right hybridization, you can completely recover the continuum model energy band. But if interaction is much larger than hybridization, then you can say, let's forget about hybridization at first order. Okay? And interaction. Interaction would split the energy level of the localized electrons by U, and then turn on hybridization. The bands would hybridize, and we get a heavy fermion picture. Basically, bands are flat here, but they are dispersive here near the gamma point. And you can see that here topology allowed these bands to give you this heavy fermion picture. And this is in a more rigorous theory, DMFT, that shows you here are the F electrons band, here are the C electrons band, here the gamma point, and so on. So if I summarize what the theory that we have now predict, without interaction we get the BM model single particle flat bands, which have maximal width at the gamma point, Dirac points at the K points, the original K points. But now if we go toward the magic angle, increase interaction, the bands are predicted to be completely flat. At the K points, we don't have any more Dirac points. In fact, this is where we get a completely flat and gap band. And in fact, the gap is now closed at the gamma point. Okay, completely inverted. Okay, so this is what we want to look for. And for this, we need to find a way to image bands in momentum space. Now, the best tool that we have so far for imaging bands is ARPES. The problem with ARPES, it works fantastically well, but the problem is that it works well on really large samples, 100 microns in size and so on. But all the Van der Waals devices that we work with are much smaller. They are 10 microns and smaller, and in fact, they even have angle disorder within this 10 microns. So you cannot use this large beam to image in momentum space. So what people do is they try to make smaller beams, what's called nano RPS, but then you lose a lot of the resolution that nice RPS have. In our technique, we're using the QTM, whose tip size is of the order of 100 nanometer, and we are Heisenberg limited in our momentum sensitivity resolution. Namely, we can measure delta momentum, which is 1 over the size of our tip. This means that even on a really small size, 100 nanometers, we can get basically resolution in momentum, which is as good as like the real RPS. So the experiment looks like this. We have TBG, whose bed structure is here. We put an insulator, and then we have a graphene tip on top, which we rotate with respect to the TBG. So what the graphene is doing is rotating in momentum space and scanning through the circle. If we zoom in, we can see that the trajectory that we are taking in momentum space passes through the Dirac points of the top and bottom graphenes, but also passes through gamma points on the adjacent left and right Brillouin zone. So it goes through here. All right. So if we start with slightly larger angle than magic angle, I'm showing here for 1.3 degrees what nano RPS has measured. And you can see, if you look carefully, you can see that there are here 2 Dirac cones. And if you zoom, and you see the energy scale here is really huge. Okay, if we zoom in on the relevant, interesting part, you can see that there is a hint of a flat band happening at low energy. But what we want to see is something that looks like this, all these details on this scale. We want to see if the band looks like this or like this. So this is how it should look. And you can see RPS gives us basically 1 pixel in momentum and 1 pixel in energy for this entire structure that we are trying to measure. And it also cannot insert the electrons into the sample, so we get nothing above the Fermi energy. So here I show you the QTM measure. And you can see, we can see very nicely all these details with high resolution. So we can see the Dirac point at the K point. I'm plotting the momenta above so you can follow. We're seeing the large opening at the gamma point. We are seeing the remote bands at the gamma point. We are seeing the Van Hoff singularity, just like in the theory. This is the rho, the IDV signal that we measure. And what I showed you before is the signal where we normalize the amplitude of the band such that they are always 1. Okay, so we can follow the energies. But you can see that there is interesting information also in the amplitude of our measurement. For example, you can see there is a difference in the amplitude between the 2 bands. Or if we go from the K points associated with the top layer to that of the bottom layer, you can see that the weight decreases continuously. And this, I would not go into that unless you ask me, but there is very interesting information about the structure of the wave function, their layer polarization in all these amplitudes. This is comparison to theory of the QTM, and it looks very, very nice. So what I showed you until now is the measurement of the energy band at twisted 1.3 degrees TDG, which resemble very nicely the non-interacting feature. But now, this is our sample, and you can see that samples are never perfect. From place to place, the angle change. And this is actually good for us, because what we can do is we can just go with our QTM to a location where the angle is the magic angle, and now repeat the experiment, and that's what I'm going to show you, how the energy bands look in the magic angle. So this is what we measured, near the neutrality of magic angle. There is, again, a lot of information in the amplitude as function of position, so let me show you first the normalized energy band, and this is what they are. You can see very nicely, flat, very, very flat energy bands almost throughout the entire momentum space, apart from one point, which is the gamma point. You see that here the bands are touching. Okay? So these are the bands at neutrality point, but in fact, we can use this technique to measure how the bands evolve as a function of filling. So I'm going to show you a movie. Again, this is like the momentum axis. This is the energy or bias. And now I'm going to change filling from nu equals 0 to nu equals 4 and show you how the bands evolve. And you can see a lot of nice things in these movies. I won't have time to show you everything, but you can see that the blends and everything remain flat, okay? They seem to emerge at high energy and go toward the Fermi energy continuously, again and again and again. You see that if we have high filling, the remote bands, which are here separated by flat bands, are basically get like above filling factor 4. You see that they get populated. And there are much more details that I cannot explain in the time that I have. I just want to say that something nice that we can do now is to show you how the wave functions or energies are looking at different point in momentum space. So what you see here is basically the spectroscopy bias as function of filling factor taken at the K point in the momentum space and at the gamma point. And you can see that the electrons are behaving completely different. Here, at the K point, this is where we have the flat bands. The flat bands are coming from the localized electrons, what we call the F electron. Okay? And you can really see this behavior here. You can see that band appears at high energy and continuously go down to low energy until it gets filled, and a new band appear at high energy, goes down. Appear at high energy, goes down. And then when it's below the Fermi energy, it continues here. So these are nothing else than the Hubbard bands of F electrons. We have a system where we have effectively 8-fold degeneracy. We have 8 Hubbard bands getting filled again and again and again. Nothing of this we see when we look on the gamma point. In contrast to the F electrons that have a gap at the neutrality point, like you see here, and the gamma point, there is no gap at 0 filling. And in fact, what you see is that the bands at the gamma point, which are basically tracking, this is where the C electrons are, where the Dirac electrons are. You can see that if you track it, the bands get filled and then get emptied, get filled and get emptied, get filled and get emptied. So these are the Dirac revivals. Basically, the Dirac cone is going down, getting charged, and then when F electrons are getting filled, there is a reshuffling, what we call population inversion. F electrons get filled, C electrons get emptied, and this process repeats again and again and again. So you can see from this the big picture, which is exactly the picture of the topological half turbulence. Within the same band, we have a different part of momentum space, different behaviors of the electrons. At the flat part of the band, electrons are behaving like localized states, but they are not perfectly localized states, because not the entire bands behave like this. Okay, if the entire bands would behave like this would be the simple Mott system. But now, because of topology, we have the gamma point, where Dirac electrons have to reside, and these Dirac electrons give us all the properties of conductivity, compressibility, Dirac revival, and so on. So it's a system that has these two types within the same band, playing together, shuffling electrons between them as we fill the system up. If you look on the most advanced theories that people can do now, it's kind of similar to what we are measuring. Most of the features are there, but if you look carefully, you can see that there are important differences. For example, here you see that there is one backbone at the Fermi energy where states come from high energy and then go to low energy. We kind of see, but we see that the backbone is always split into two. And there is a mystery energy scale that we now see that is pretty universal, of the order of 15 millivolts, that appears in all our measurement, but is not included in any of the theories. And this is one of the new puzzles that we are trying to now resolve. So with this I want to end. I showed you that we have this new tool, the quantum twisting microscope, that can do many, many different things. It can be used as a twisting machine to basically twist two layers with respect to each other and scan continuously their phase diagram. If we look with a barrier on momentum conserving tunneling, we can image in momentum space the electronic dispersion in any quantum system, and we can put on this tip and sample side any van der Waals system that can be basically peeled off, exfoliated. If we do the same but for inelastic tunneling, we can follow the bands of the energies of phonons, but even more generally, any collective mode that couples to the tunneling electrons, spinons, magnons, Goldstone modes, everything that couples to the electron, we should be able to image their dispersion like this. And finally, I showed you that this technique can also be very nice in real space and allow us to measure electrostatic potential with really nice sensitivity, but with 2 orders of magnitude better than any detector that we have today, with 1 nanometer spatial resolution. So with this, I want to thank you for your attention and get your questions.
Okay, let's thank Han. Questions? So, Manish.
Okay. No, just right.
Shahal, I have a quick question. So in the band structure that you show, we can see that the bands touch at the gamma point. So I guess it is like the second picture that you had shown, the second kind of scenario that you had shown, namely that the band split by the U and then they hybridize.
Yeah.
But is this phenomena? Do you think this depends on really the let's say the back gate, or does it depend on how you screen the thing, or is it something you think that is for all?
So what you see here is the measurement as a function of backgate voltage, right? We are adding electrons starting from -4, going to 0, going to 4, and you can see that at the flat part of the bands there is splitting by U, so the distance between these 2 black lines is U. Okay? Quantitatively, it's 35 millivolts. So this is the charging energy of these local quantum dots, if you want, and you can see them basically extending throughout backgate range. You can see them more strongly on the electron side than in the hole side, but you can see them also on the hole side. So this quantum dot local moment behavior exists for every backgate. Of course, if you screen interaction, let's say if you put an electrode just directly above, you will kill this.
Oh, I see. Yeah. Okay, that's what I had in mind. So depending on the device geometry, you could actually have maybe the other scenario as well, do you think, or is it?
The other scenario I showed you before. If we go to slightly larger angle than magic angle, that's what we get, right?
Yeah.
Right? This is completely inverted bands.
Right.
Right? You have Dirac points at the K points, no splitting, nothing.
Right. Okay, thanks.
Yeah.
Can I ask a question?
Yes, go ahead.
Can you hear me? Yeah, so first of all, thanks for a fascinating talk. Very nice. I have 2 questions. One is, you showed that the compressibility, the all compressibility measurements seem to be ignorant of the F electron, if your picture is correct. So why is that so? Why the compressibility data look like
it's independent, but I think that we are measuring the inverse compressibility. So if you have 2 subsystems, what ends up is their inverse compressibility. So the less compressible system always shows up in the measurement, which is the C electrons, the Dirac electrons. In fact, in the compressibility, you can see now in retrospect, we understand that there is something that we should have understood, which is you know that sometimes in interacting system you get negative compressibility, right? And in fact, we also, and people always say you get negative compressibility because it's interacting system, it's on the verge of getting into first order phase transition and so on. You can see here, it starts from positive and about 0.6, infinity factor of 0.6 is crosses to negative. And then it jumps again. Here it crosses to negative. We didn't give any special meaning for this point where it crosses to negative, but now we understand it, in fact. In this model of kind of Joe Imry's population inversion in quantum dots, of like a wide level and narrow level, which are the F electrons and C electrons. So if you look carefully, you can see here that what happens is that the narrow electrons start at high chemical potential, above the Fermi energy. They go down, 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 down. They are still not in the Fermi energy. But at this point 6, you see what happens. They are touching the Fermi energy. They start to get populated. Once the F electrons start to get populated, you get population inversion with the C electrons. You see the C electron starts to empty up. And this is the negative compressibility. Since you are measuring mostly the C electrons, you are basically measuring negative compressibility because you are adding carriers to the system, but the C electrons are actually getting depleted. So, to your question, you can see the F electron through the C electrons getting empty. That's
Okay, and now another question. So, does this picture of having basically Kondo physics connected to the superconductivity? Is there theoretical?
good question. We don't know. I mean, we have here a few things that, if you are a theorist, you should think whether it's connected to superconductivity. And in fact, I suspect that this energy scale that we don't understand might be something that is connected to superconductivity. Kondo, there are theories that relate Dirac electrons to the superconductivity in the system, but there are many, many theories of superconductivity. So basically here you have a detailed picture, you can choose whatever theory you want. Yes.
Yeah, I was thinking of a Kondo lattice.
Yeah, this is the Kondo lattice effect, right? It's the Kondo lattice.
Yeah.
I mean, if you want, it's a Kondo lattice in the regime that gamma, the tunneling, let's say, to the conduction electron, is 2 to 3 times larger U. So it's really in the Kondo limit, right? Of open dots. Yeah.
Thank you.
Yeah, so I have a very naive question. So I understand that you are probing this sample locally, right, at various different angles. So now if I would like to know, think it in terms of a global picture, the C and F electrons mixing, are they happening at all the twist angles or only at the magic angle?
Yeah, I mean, this behavior of F electrons, this what we call cascades, right?
Right.
These cascades happens at angles which are very close to the magic angle. If I go to 1.3 degrees twist angle, you would not see that. You would see back the single particle picture. So you need to be very close to the magic angle, yes.
Okay.
But the regions that we probe, 100 nanometers, sometimes over a micron, we see the same behavior. Over a micron, you have like 100 by 100 Moiré unit cells. So the wave functions are well defined. Even on 100 nanometers, you can get local physics, which is flat bands and heavy fermions and so on. It's large enough system for electrons to develop these flat bands and so on, even 100 nanometers.
Okay. Thank you.
Okay, if there are no further questions, let's thank Shahal again. Thanks.
Thank you.
Thank you. Thank you both, Professor Shahal Ilani and Professor Efrat Simpsoni, to be with us. And we conclude this particular symposium. And so I hope participants here, they are get a very nice flavor of these happenings in this particular field. So that's what I just wanted to tell on behalf of the local organizers.
We actually have something to
Thanks
thank
again for organizing this, and once again, I'm really, really sorry I cannot be with you in India and do all the other talks.
Thank you very much.
Thanks.
It was a pleasure.
Okay.
Bye.
So we actually have something to thank the local organizers.
Yeah, thanks a lot. No, it's not for me. Give it to me. Yes. This you give it to Neha and you used to go there and where is
Let's take a picture. You need to take a picture.
Yeah.
We need to take a picture as well. Thank you.